and we'll get this show on the road.
Humanity's view of the cosmic tapestry and our place in it is changing. Breakthrough Discuss 2024 follows 3 transformative threads in space science. How AI and data science are scaling up the search for life. From the primitive to the advanced. How insights into exotic environments on Earth, in the solar system, and beyond are expanding the range of possible habitats for life. And how new launch technologies and robotic spacecraft promise to expand our own reach into the cosmos. So welcome to a cosmic tapestry for exploration. Welcome to Breakthrough Discuss 2024.
Thank you. For those of you who don't know me, I'm Pete Worden, the chairman of the Breakthrough Prize Foundation. And I'd like to welcome you all to the 8th Breakthrough Discuss conference. We missed one due to a global pandemic, but this is going to be really cool, and you'll hear a lot about it. I'm looking forward to this conference, particularly this is our first one outside the United States. Here at Oxford University, and I guess this is the examination hall, so there's probably the spirits of many sad students floating around here. But without further ado, I'd like to introduce our host, Vice-Chancellor Irene Tracey, and Chancellor Tracey, thank you.
Thanks, Pete. You're all right to get back. Great. Well, thank you so much, Pete, and thank you again for the visionary idea that you had to bring it to Oxford and to bring it to the UK. So I'm absolutely delighted to be here, and as Vice-Chancellor of this wonderful university, I'd like to welcome those of you who are not members of the university, who are visiting maybe the university and Oxford or the UK for the first time. It looks like you've got an absolute knockout couple of days ahead of you, with, I understand, a nice dinner and a party tomorrow night, so a ceilidh, in fact. So for those of you who don't know a ceilidh and are filled with dread, it's always a massive success, so do go to it and enjoy it. Anyway, a very, very warm, literal welcome to Oxford, and I wish you all the very best for the next couple of days. I'm only just gutted that I can't spend actually the full 2 days listening to you. I actually always fancied myself as somebody that would work in astrophysics. I was that generation that adored Carl Sagan and everything about him, but I was sort of steered down the medical, biological route, so I ended up as a neuroscientist, but I've got this love still for planets, so I'm just sorry that I can't be here. I'm really sorry you still haven't found aliens. Chris and I met many years ago, and he promised me that the search was on and that you would find them, but so keep going. So no disappointment yet, still have great optimism that this will happen. And Chris actually helpfully reminded me that we've got a long tradition in this university, not just obviously for physics and maths and those core subjects that underpin many of the things that you are using to discover things, but also in the 17th century, John Wilkins was very keen to get out there and discover other life, and had a couple of problems. The first was he had to get to the moon. The second was he was quite preoccupied. He was just telling me with how, when he got there, how on earth is he going to talk to the people on there? So then he got preoccupied with what language he would have to develop that would be a universal planetary language to speak. Maybe that's coding, I don't know. But anyway, he failed, but we're still on the search. So we do have a rich tradition. You are in the room that for many of us is quite triggering because it's where we sat our exams. But it's a wonderful venue, and I'm sure you'll you'll enjoy the facilities for the next couple of days. This conference does mark it's the inaugural, really, start of having the Breakthrough Listen project headquartered here in the university. And of course that taps into that wonderful strength that we've got, and a growing strength in the UK, where investment and more funding is putting into the space sector. And I will do, in my role, both as Vice-Chancellor but also in my leadership role academically in the UK in science, to make sure that we champion and we push for the funding to be there for that wonderful, extraordinary, exciting basic discoveries, because I know that when you talk to society, although the rhetoric is often on very translation, cure diseases, of course we must do that, and that's my bread and butter historic academic journey, the public and the people are inspired by just the sheer joy of discovery and finding things bigger than themselves, and you are right in that space. So I congratulate you for that, and I wish you all the very best in that work that you continue to do, and I will do my part in terms of helping to try and steer funding and make sure that you are well supported in that regard. I'd also like to thank the Breakthrough Foundation for the support of the fellows and the students that you do. It's so key in universities and in our research endeavours that we have that next generation, that pipeline of talent that comes through. So thank you for the investment that you put there. I understand there's a new thing with a summer internship programme, and we've got several of those interns here as well. So this is a wonderful opportunity for those of you who are doing a summer project. Don't be shy. Reach out in the coffee breaks, in the lunch breaks. It's very rare that a professor, no matter how senior and brilliant they are, will not want to talk to you because you have full of ideas and you're not sort of brainwashed by the way we think about things, and so it's a great opportunity for you to challenge them, to ask them questions. So I encourage those of you who are in the audience who are on the internship program, or even just new doctoral students, make this a wonderful opportunity to make connections and ask questions and learn new things. So with that, it gives me great pleasure to hand over to a professor and a fabulous woman of science who needs no introduction. She has been not just a champion in this field, but she's been a real champion for women in STEM and just a wonderful academic leader. And I don't know where she is, actually. Jocelyn Bell-Berlin, where are you? There you are. Can we please welcome Jocelyn?
Thank you, Vice-Chancellor, and thank you all for being here, and a very warm welcome. If I say 1665 and 1667, no units, how many of you know what I'm talking about? About 2, 3, 4. The first molecule detected in space, the OH molecule. I was a summer student at Jodrell Bank during my undergraduate degree, and was assigned to work with Garrett, who was making observations at 18 centimeters, 1665, 1667 megahertz, and detected OH in space, and I got to work on that data. There was supposedly a computer in Manchester with a landline, but the landline between Jodrell and Manchester was down. So guess who did all the long arithmetic? Lecturers back in Glasgow commented on how good my arithmetic was the following term. I was one of a very rare beast at Jodrell Bank, a female. They had once had a female grad student. She and a male had put the dormitory to a use for which it was not intended. He bragged. Sir Bernard Lovell got to hear of it and said, "No more women." So I broke that barrier, albeit just for 6 weeks. But it's interesting which sex bears the brunt of these mutual encounters, isn't it? I've subsequently gone on, along with doing lots of different kinds of astronomy, to set up the Athena Swan scheme with some colleagues. It's even now reached the USA. I think it causes quite a lot of hassle, but I'm actually very proud of it. And I'm sorry that we don't have more women here today. I suspect there are more women in astronomy than are represented here, looking around the room. There certainly are more women in the Oxford Astrophysics, aren't there, than are, fractionally represented here. But we've got a female Vice-Chancellor, so congratulations, ma'am, no pressure. So thank you very much to Breakthrough for the opportunity to be here. I'm looking forward very much to what's to follow, and I have to introduce paper, I'm introducing Nikku Madhusudhan.
Thank you. Good morning, everyone. I'm Nikku Madhusudhan from the Institute of Astronomy, University of Cambridge. First of all, it's a great pleasure and a privilege to be welcoming you to this Breakthrough Discuss Meeting 2024, the first of its kind in the UK. We all know that the question, are we alone, has been one of the longest standing and most fundamental pursuits of the human species, right? Given the technological progress that's happening today, there is a realistic chance that we may be the first generation in human history to be able to say that we are not alone, if the alien species are indeed out there, right? So as profound as this is, what is not clear is that what is that species like? Are we going to detect biosignatures of microbial life, or are we going to detect technosignatures of an alien civilization? We don't know. That's a completely open question. And the only way to know is to just look, right? To look as far as we can, as broad as we can, and with every instrument that we can, right? So we at Cambridge have an extensive program in exoplanet science across various areas of exoplanet science, both at the Institute of Astronomy and several other departments, and most recently, the Leverhulme Center for Life in the Universe, where we focus on questions of habitability and search for life and origins of life and so on. My own research is on the search for habitable signatures and biosignatures on exoplanets using the James Webb Space Telescope. I'm also very excited by the developments at Breakthrough Listen for technosignatures. In this regard, I would like to congratulate Oxford and Breakthrough Initiatives to take up this leadership role in this really frontier area. And more generally, I would like to say that these are complementary areas, really, the search for biosignatures and technosignatures, and there are other areas like experimental work and theoretical work, and it's only when we bring all these things together that we can really address this question at the best of human potential at the current time. Finally, if you look at the history of scientific breakthroughs, they usually come by a confluence of innovative scientific ideas and major technological advancements of the time. So the search for life is no exception in that regard. We really have to use everything that we can at this point. And this conference epitomizes that spirit. So I'm really looking forward to next 2 days of extensive discussions, this exciting program, and various talks across multiple disciplines, astrobiology, AI, and space missions, to see what is the best we can do at this time. So I'm really excited for this. So welcome again. Thank you for coming. And we look forward to your participation in this event. Welcome to Discuss 2024. So I would like to now introduce and call on stage Professor Michael Garrett from the University of Manchester.
So good morning, everyone. It's great to be here. If you've never been to a Breakthrough Discuss meeting before, then you're in for a great couple of days. It really is fascinating. I just want to thank the organizing committee for putting together what I think is really a tremendous program. I look at it personally as a sort of discussion also in the wider context. The longevity of a civilization, I think, is actually key to all three topics that we'll be discussing today. So new space, the opportunities that are there to progress and to expand into the solar system. Everyone has a personal vision on that. I think it's extremely important that we do that in terms of the longevity of this civilization, of our species, it's really important to continue that exploration. So that's one topic that we'll talk about. And of course, life in the universe is very much connected, especially the search for intelligent life, which Breakthrough has basically transformed over the last 10 years. That's also all about the longevity of a civilization. If civilizations like our own are only around for a few hundred years, then it's going to be a very, very difficult problem. But if they're around for 1,000 years or 10,000 years, then it's tractable. And as previous speakers said, this could be the generation that will actually make that discovery. And the other thing about Breakthrough Listen is that it's actually not about old guys like me with gray hair, but it's actually all the young people that are being employed and being trained, mostly PhDs at the moment, but in the future postdocs. They're going to make a tremendous impact in this field, and that's what we need. We need people who will be thinking outside of the box. AI, I think, you know, the third topic that we're talking about, also, again, you know, scientific advances will surely come, already come from AI also in this field, but there are some challenges there. And again, I go back to the longevity of a civilization. We are creating a new technology that's completely different from any other technology that we've had in the past. It can be self-progressing, it can be autonomous, it will have an impact, and it will result in rapid change that the young people here will have to contend with, both in terms of the opportunity that it presents, but also in the challenges, and also the challenges it represents in terms of the longevity of our own species, and perhaps intelligence generically in the universe. So it's going to be a great couple of days. Really interested to hear what the discussion will be, and just like to thank everyone for putting it all together, and enjoy yourself. Thank you.
Thank you. Vice-Chancellor, colleagues, friends, attendees. I'm Chris Lintott. I'm co-chair of the Scientific Organizing Committee, along with Jamie Drew from Breakthrough, who can't join us this week. I just want to take 90 seconds to explain what we're doing here. I was looking at the program this morning and getting excited about the talks and discussions that we've got to come, and thought I should try and find a way to explain to you what ties these three things together. You can tell we struggled because of the number of times we say the word strand and tapestry and combination in all of the publicity for this conference. So it's basically things that I like talking about. That's the guiding principle. But I think there's a thread between all three. See, I'm doing it again. There's a connection between all three, which is that each of these topics, our consideration of machine learning, our thoughts about life and the types of life that might exist, and the ways that we might, with new technology, explore the solar system and beyond, there's a thread of optimism that runs through all of those. But it's a sort of very scientific optimism, because we're excited about what we can do. This isn't science fiction. This isn't just about dreaming about what we might be able to do one day. In each of these fields, things are moving fast and ideas are changing fast. And so it's a good time to be optimistic. So maybe it's just that it's finally summer here in Oxford. Maybe it's because I'm excited to see you all. But I want you to go into the next couple of days with that sense of scientific optimism. And we're going to start with Strand 1, which is the machine learning and artificial intelligence strand. And it's my great pleasure to introduce the chair of that section of our program from the University of Western Cape and the South African Radio Astronomy Observatory. I'll introduce the wonderful Vishal Lochner. Vishal.
Thank you very much, Chris. In 1967, Jocelyn Burnell made one of the most important discoveries in physics. But what I want to talk about is not the discovery of the pulsar, but how it was discovered. Because it took a very bright graduate student carefully looking through all of her data and noticing something weird. So the question that's been hounding me for the last couple of years is, how do we still make these unexpected, unknown discoveries when the square kilometer array is going to produce a catalog of 1 billion radio galaxies? When the Vera C. Rubin Observatory, under construction in Chile, will have a catalog of 20 billion galaxies? And perhaps most importantly and most dauntingly, that same telescope will detect something changing on the sky 10 million times a night. How do we discover new phenomena? And of course, in the radio, we have signals that look like this. And what if, amongst all this noise and all this other astrophysical signals, there's somebody trying to say hello? What if we miss it? We can't miss it. Artificial intelligence, so this is basically how I feel about the problem, right? It's beautiful, it's exciting, there's a potential for incredible discoveries, but at the same time, it's an overwhelming amount of data. And this is why we need artificial intelligence. So machine learning, which if you don't know, is a branch of artificial intelligence, and it is everywhere. I guarantee that you've encountered at least one machine learning algorithm this morning already. I got a few examples from my own favorite tools. So for instance, Netflix likes to try to tell me what I should watch next. I really like in YouTube Music, I can say, hey, I like this song, play me more songs like that. That's all machine learning. My favorite is I can ask Google Photos to find me pictures of my cat. It can't tell the difference between my two cats, but that's okay. Most people can't either. But 10 years ago, this was impossible. This was really one of the most impossible problems in computer science, and now it's trivial. And of course, we can't talk about AI without talking about large language models. So I'm pretty sure everybody's encountered ChatGPT. There's a screenshot. Uh-oh. Clicker doesn't seem to be clicking. Anyway, what you would see is a screenshot of being a bit annoyed at ChatGPT. It was trying to help me code and not doing a very good job at it. But really, you know, all jokes aside, large language models have absolutely revolutionized our, the way that we work with all kinds of different tools. Let's see, there we go. Brilliant. And of course, pretty much every field in science has started to embrace AI and started to need it, especially as the data sets get larger. And this conference, we have these 3 different strands, but there is actually another common thread, which is AI. So for instance, I found a very nice example from microbiology using unsupervised learning, so this is without labeled data, to automatically group together different microbes based on their proteins. And of course, Perseverance is a lovely example of using citizen science-assisted AI to choose which rock samples to take next. And there are many, many other examples within robotics of using AI. So to go back to what we're really here for, what we actually want to do is anomaly detection. So we want to look for the unknown unknowns, the signals that we're not expecting. You can use machine learning for this. The way the machine learning algorithms work is by looking at your data, trying to group together the things that are kind of normal, and look for things that are weird. I'm pretty new to the field of the search for intelligence out there, but as I understand, traditionally you would think about, okay, what does technosignature possibly look like, and then go look for it. This is a different approach. We're now piggybacking off of large surveys and trying to solve the needle in a haystack problem, trying to look in an unbiased way for anything interesting, and hoping that one of those might be evidence for intelligence. Oh, this is, okay, there we go. Okay, so a couple of years ago, we tried to attempt to solve this problem with my collaborator, Bruce Bassett, who's actually over there. We designed a framework called Astronomy. So this is a general purpose anomaly detection framework for astronomical data. And what's really important is actually this loop over here, because machine learning algorithms on their own are not actually enough to solve this problem, because a lot of anomalies are not actually interesting. So you need a little bit of human in the loop to actually improve the algorithm and find the things that we really care about. The other step that's important is this innocuous-looking box here called feature extraction. This is a way of taking complicated high-dimensional data like images or time series data and simplifying it down into a representative set of numbers for the algorithm to deal with. Traditionally, this has been the bottleneck, the hardest thing to solve, and what's really given us another leap forward in this field has been deep learning, like with so many other fields. Deep learning is yet another sub-branch of machine learning, and this is an example of a very complicated-looking convolutional neural network that will solve a problem like find me pictures of my cat. However, what people don't realize, or what many people don't realize, is that 90% of this algorithm is doing feature extraction. It's trying to learn a representation of something like an image or a time series. Only the last little bit is actually doing the classification. So what many of us in the field are starting to do is chop off this last layer and use this machinery as a feature extractor. So one of the pioneers of this was Mike Walmsley, who's an Oxford alumnus, actually. And so we did very successful anomaly detection with one of these deep neural networks. And this work's been extended by a student of mine, Koketso, using self-supervised learning, which you're about to hear a lot about, to automatically group together similar galaxies. Of course, we work in the time domain, and I'm sure Dan, who's one of our excellent speakers coming up, is going to mention this work led by a very bright high school student doing a similar thing, train deep learning neural networks, using them as feature extractors and doing anomaly detection. And of course, I would have to mention Alex Anderson, who's run a really cool citizen science project with Meerkat data. So this is a telescope from South Africa with radio time series data. And we've been using Astronomy to actually find radio transients. So these are many, many different fields, but all underpinned by the same kinds of approaches for anomaly detection. I want to give a very short shout out to my group. We call ourselves the Computational Astrophysics and Machine Intelligence Lab. We just made it up. The reason I just want to highlight this is many of them are here. So if you want to talk to people about anomaly detection in images, you can talk to Verlon, Koketso, and Margarita, who are all here. If you want to talk about anomaly detection for time series data, try reach out to Bertie and Hanwoo. Please, this is a discuss conference, so please get those discussions going. I want to finish with just one highlight. I want to say that not only can machine learning detect scientifically interesting sources, it has. So here's some examples of some really cool looking optical galaxies that Verlon found in 4 million decals sources. And then on this side is my very favorite, which is a weird object that I discovered with Astronomy and Meerkat data. We think it could be the remnant of a binary supermassive black hole merger. We're not sure. We called it Sauron, which made all the media and the YouTubers get excited. I found out if you want to be famous, just give your discoveries silly names. But that's not the point. The point is that we've already shown that machine learning can make discoveries. So this really could be the tool to make the first technosignature detection. I'm going to finish off, I asked ChatGPT to help me finish off with a bit of a zinger using sci-fi puns. It was terrible, but it did come up with one that I liked. In space, no one can hear you scream, but together, our collective voices can reach the stars. Thank you very much, and let's enjoy the very first Strand. It is my absolute pleasure to introduce the first speaker of this session, which is Alexis Boukouvalas. He has a background in computational biology at Manchester, followed by a pretty impressive series of AI-related positions, if you read his bio. His current position is Research Engineer Team Lead at Google DeepMind, and he's going to kick us off with what looks like an amazing overview of some very interesting AI applications in science. Thank you very much, Alexis. Do you want to use the clicker?
Yes, thank you very much.
Thank you so much. Welcome, Alexis. Thank you.
I don't know where to look. Okay. Thanks, everybody, and I appreciate the invitation. Okay. So hopefully you can all hear me. I have way too much stuff here. Oops. Yeah, I have too much stuff in here. So please have a look also. I'll kind of go through quickly a lot of things. I hope you find them interesting. Please come talk to me. I really look forward to discuss in this conference. Right, so what's Google DeepMind's mission? As you can see, it's building AI responsibly to benefit humanity, right? And I'll just give you the first section here. It's just some of the things that have happened in the company, right? A big part of a lot of people in Google DeepMind's focus is on science and the intersection of science and AI. And why is that such an exciting and interesting space is because we see a lot of data becoming increasingly available, and this is across science, right? So you have a picture here of basically the CERN collider there. We have, in biology, it's just unbelievable, an unbelievable explosion of data availability. as Vishal just showed, right, in astronomy, right, you have a lot of things. Fusion is more and more experimental results are becoming available, and weather, right? So these are just some examples. And basically how Google DeepMind works is we are a fairly small team, right? To give you an idea, basically the science team in Google DeepMind is about 100 people. So we try to identify root node problems, right? Problems where we think we can have the maximum impact and help the most people to make progress, right? So this is kind of a very, this side, a very famous strand of work, right? So you care about drug discovery. You really want to, cure disease, right? How do you, like synthetic biology, there's a lot of, advances you could do here. There's a common thread, like protein folding and actually also understanding DNA here, right? So these are basically the problems that are being attacked by the science team to enable everything that kind of stems from it. And what I'll be talking most of the time here is about what I'm particularly excited about. My recent work is on geospatial intelligence, really understanding what's happening on Earth, the planet's surface. And I will actually start by talking about specific why this is useful, right? So solar potential, there's a big drive to change energy generation, so we use solar power. So we can leverage understanding the geospatial context to make a lot of progress here. Just understanding and making sustainability impact, right? So thinking about deforestation, sustainable supply chains, all these things, the root node problem is understanding what's happening on the surface of the Earth. And just as another big thing there is agriculture, right? There's huge applications. All right, so before I go into that, just very briefly, what's been happening. This is a little bit delayed. All right. So AlphaFold, I won't talk about AlphaFold, but people, I suspect, already know a lot about it, but it's predicting the 3D structure of proteins, right? So this was a very successful large-scale program that's still going on, and a lot of people are already using the outputs here. But going beyond that and really understanding what's going on at the DNA level, this is another example actually of what I think is a common thread in AI for science, which Vishal also highlighted, right? You actually have a lot of data, but typically you don't have a lot of labels, right? And this is very much true in biology, right? So if I make a mutation in a particular piece of DNA, right? Is this going to lead to disease or not? Actually, we don't know most of the effect of most mutations, right? So this is an area where this AI revolution can really help. And there's been some recent work, I'm just highlighting it here, about understanding the effects in kind of proteins. So this is the coding region of DNA, and also non-coding, which is basically regulation. So there's a lot of work there, lots of potential applications, drug discovery, etc. There's also a lot of work on fusion and understanding how to control plasma. This is a collaboration with EPFL, and it was a publication also. Please, have a look and talk to me if you're interested. There's also just thinking about mathematics and doing automatic proofs. For example, understanding, taking part of competition. There's a lot of work in this area, so please, have a look. And also things, I already mentioned weather. So currently the state-of-the-art weather prediction model is a pure machine learning model, which is called GraphCast. GNOME there, which the logo seems a bit messed up, is basically designing new materials, right? So there's also been a lot of progress there. Alpha geometry, talking about solving geometry problems, so people are attacking this. And fan search. So fan search is very interesting also because it's a way of using essentially deep reinforcement learning to design new algorithms. And this has proven successful, for example, right, to design new sorting algorithms or new matrix multiplication algorithms that are faster than anything any human has designed. So this is very exciting. And one thing also, because Vishal already mentioned LLMs, so I would be remiss not to talk about LLMs also. And I was thinking specifically for science, right? There is a lot of laborious, like grant work that happens because data very oftentimes is very messy. So a lot of, and I spend a lot of time, right, just putting things together, sorting out metadata, all that stuff. I'm just highlighting for all of you out there that big LLMs like ChatGPT or Gemini, right, are already very good at helping in this area. So think about like having an assistant next to you that is your automatic data scientist that helps you understand data, do quality control, put things in the same format, etc. And also to mine the scientific literature, right? So this is the example here, right? I'm looking at a particular gene here. Please tell me all the research papers that say anything about this gene or related genes, this kind of work. So this already works. All right. So after this kind of whistle tour, I want to talk about geospatial intelligence because that's what I work on actually, and also what I think would be the most also interest in this setting. Right? And I'll start with 2 case studies. The first one about solar potential. Right? So there is actually already in Google available. It's a service which assesses solar potential. And the whole idea is you have a house and you want to put solar panels on it, right? But you want to say, is this, when will I benefit from this, right? I will pay X for this. Now, tell me, based on the orientation of my roof and where my house is and all the kind of historical kind of weather, like how much, when will I pay off? When will I start making money, right? So to do this effectively requires remote sensing, right? Requires remote sensing expertise. And specifically what you need to do is you need to build these digital surface maps, right? This is currently done with aerial imagery, so high resolution aerial imagery. And that map on the top shows you, we don't actually have high resolution aerial imagery for a lot of places. And the current product out there relies on having this. Once you have this high resolution imagery, the whole ball game basically is to identify the houses, right? Segment the roofs and find the orientation of the roofs. So you can say specifically, you can make an accurate calculation of solar potential and how much power you're going to get, right? But there is this problem about availability of high resolution aerial imagery. You also have low quality, like low resolution, much more widely. You also have remote sensing, like Sentinel-2 optical imagery, right? It's available everywhere. So what people have been doing, teams in Google basically, right, is you take a lot of different types of imagery, you feed them into basically your large-scale neural network, and you get out basically a segmentation problem, which identifying the houses and the roofs, right? And the orientation here. So this is the surface model. And this goes in and gives you basically your answer. So the whole solar calculation is actually quite involved. It involves an economics model as well. You push all of these through, and then you get an answer that's hopefully quite useful. This is available. You can actually already use it. It's not available globally, right? And these folks are the people who actually did the work. But the idea is to actually, the next step in this work is to use remote sensing and have global coverage. So anybody anywhere on Earth could do this, right? And this has high sustainability impact. But this is like one specific example, right? I want to talk about another case study here, right? Which is dynamic world. This is also out there. You can use it. This is a global land cover map, right? So this is quite a large model, right? It's been trained using more than 24,000 Sentinel-2 images. It's high resolution, so you have 10-meter resolution, right? It's constantly being updated as new acquisitions, new imagery is obtained, right? It's free, open source, etc., right? And it's basically available in Earth Engine, so you can easily use it, right? And the idea is you can help decision makers, right? Like state government, national governments, NGOs, conservation NGOs, etc., to figure out what's going on, right, in their area of interest and track change in time. Now, what is this model, right? This is a like classical supervised AI model, and these are the classes, right? So it's identifying where there is water, where there is flooded vegetation, where there is a built-up area, where crops, where you have trees, grass, shrub, snow and ice, right? And that's it. This is a fixed set of categories, right? And then you crack the handle and you make this work. And then you can basically use this to do classification of near real-time images, right? You can also, the model quantifies its uncertainty. So quite often you will see for this particular case, sometimes it really gets confused, for example, between grass and shrub because they look quite similar. So, but you know, you can look at the probabilities, and then based on these, you can build derivative map products, right? So specifically things that you're particularly interested in. For example, if you're monitoring deforestation, you really care about forests, right? So forest versus non-forest. Now, how does this actually work, right? And this is a significant effort that you know, a team in Google worked on for you know, more than a year, where you basically collect a lot of data, right? You build a significantly large model. You collect annotations, so actually hire people to annotate where it's water, where it's crops, where it's et cetera, right? So this is what's happening here. And it's a very big exercise in building up the training data that you require to build such a model, right? And then what you have is, once you are satisfied, you validated the model, you assessed it's good enough, then you can run it all the time on any new image, and it will do this segmentation. Now, this is the training data set. It covers all of the Earth. It doesn't cover, for example, Greenland, because there's mostly ice. Nothing that interesting, but I guess that's changing. This is not such a trivial problem, right? Because when you're looking at optical imagery, the thing you will already notice is you have to worry about clouds, right? You can't see through clouds in the optical spectrum, right? So, and this is an example of a problem that anybody dealing with optical remote sensing data has again and again and again, and people are solving it again and again and again. This is an example of wasted effort, right? Or even worse, not having basically the best results you could have for your particular application. Right? You cannot use this image for training data. It's all cloudy. Right? You can actually have another model to identify where the clouds are and just remove them and just mask that out and then use the rest of the image. So people, this is kind of one approach. And once you solved all these problems, basically the whole infrastructure problem, and the whole kind of how to deal with clouds, data quality control, you know, Earth is a sphere, so you have to worry about UTM projections, all these complexities. You've done all of this, and now the idea is every time we get a new image from Sentinel-2, you know, we immediately run this algorithm, and basically from this is the start date of when we have data, 2015, for Sentinel-2, and to basically up to like 2 to 5 days ago, you have an updated run of the model, which basically tells you what's going on in this area, right? So this is very exciting, but both of these examples that I showed you are, I guess, fairly large, dedicated teams that solved this particular problem, right? Land use and how it's evolving in time, and like solar potential, right? Can we help anybody who wants to basically have more responsible decision-making and leverage and get insights of this mountain of data that we have from remote sensing, but to do it much more easily? And this is the pitch, this is the idea behind building a foundation model on remote sensing. Now, this is also a brief overview of machine learning for remote sensing data. right? The classical approach, the traditional ML approach, is to basically, what Michel talked about, right? Talk about feature engineering, do a lot of that, you know, like this takes a lot of intuition, a lot of trial and error, right? Because these images are very high dimensional, right? So you really need to do that before you apply your classical machine learning model, something like a random forest, for example, right? Or linear regression. The nice thing is these are very easy, fast to train models, right? You don't need that much data, assuming you do your feature extraction well, right? But this feature engineering is a very laborious, error-prone process, right? So, and such simple models have proven in the past not to be as accurate and as scalable as deep learning approaches. Now, deep learning, right? So this has dramatically improved accuracy for a lot of different problems with remote sensing. I just showed you some examples, right? You don't need to do feature engineering, exactly what Michel said, right? Because that's part of the model, right? But you need a lot of data. You need a lot of label data, and you need significant compute. So you need to be well-funded to do this. Right. Can we do better than this deep learning approach? And the answer is to look at a foundational model approach, right? And for foundation models, what is going on? And the whole idea is this self-supervised learning that also Michel described, right? So you just look at the images. You don't look at anything else, right? And then you crack the handle, and I'll explain how this works, right? And then you can basically either fine-tune the model on the set of labels that you have, or actually something called low-shot learning, where you actually don't need any labels at all, right? If this works, and you know, we believe it does, basically you don't need to do feature engineering. It is highly accurate, so it keeps basically the advantages of deep learning. But you no longer need, you know, huge amounts of label data. And the really nice thing is this kind of trunk that you build, the foundation model, you can use it on many, many tasks, right? So you don't have to keep reinventing the wheel. You basically can start already from a quite advanced point. Okay, so how this works in practice, right? You collect a large unlabeled data set. Now, in Earth Engine, we have more than 25 petabytes of remote sensing data, right? This is all of Sentinel-2, for example. You pre-train this large single model, right? These models have typically billions of parameters, and you'll use the self-supervised technique that I'll talk about. And then you either fine-tune or you do this low-shot training. Right. Okay, I'll keep it short. The analogy to think about is actually large language models, right? So if we think about language for a second and not remote sensing, right? You try to do this next token prediction, right? Large language models operate on the same principle, self-supervised, right? And basically, you mask out a bit of text, and you ask the model to try to fill it in. And you basically do exactly the same thing with images and remote sensing images, right? Okay, I'll skip that. So basically, you take an image, you basically start masking out, and you ask the model to fill in, right? And this builds an intrinsic understanding in the model of what is in these images, basically, right? You do need a lot of data, but image data, right? There's no labels at this point. And like a typical architecture that you will see of these models, this is basically very similar to large language models, is you basically have, you take all of the images across, right? You work on this patch basis, and the encoder essentially produces this low-dimensional representation, right? So you basically go through a bottleneck, and then you blow it up again, right? And you reconstruct the images, and that is your objective, right? Your objective is to minimize the reconstruction error. You can add a few other things as well to make sure, for example, you have temporal consistency, etc. Okay, I think I'm out of time, but hopefully you got an idea, because once you've built this foundation model, then you can just use it directly on basically the set of labels that we have. So for example, we're talking about forest or non-forest, and then very quickly have a model that basically is able to do this classification. Okay, please have a look at the slides. the one point that this is saying, this type of approach is already working on images. So there is a flamingo model here. So we are already seeing very positive results in remote sensing. And I will stop with this slide. But essentially, why remote sensing is so interesting and so exciting is, although I showed you a lot of optical imagery, there's actually a lot of different types of imagery, right? So we have radar, we have LiDAR, we have all kinds of things. And it's really an ideal domain for an AI approach, right? It's also the temporal aspect is hugely important and valuable because it allows you to understand what's changing. And we can also leverage things with outside imagery with imagery, things like text understanding or seismographer data or magnetic data that the next speaker will talk about. So it's a very kind of exciting space to work in. And I'll stop at that. Yeah, thank you very much.
Thank you so much, Alexis. I'll just remind the audience that we will take questions right at the very end. So if you've got burning questions, make sure you write them down for the discussion session. And I'd like to go straight into our next speaker, Regu Angappan. So Regu did his PhD in planetary science at Johns Hopkins, where he still holds a visiting scientist position. But he's a postdoctoral scientist at SandboxAQ, and I'm very excited to see how he's going to show how AI and quantum physics can combine to help us navigate the world. Thank you, Regu.
Thank you, organizers. Thanks, Michelle, for the introduction. Before I get started with my talk, I wanted to introduce myself so that you understand where I'm coming from on what I'm talking about. And I'm a postdoctoral scientist, so I'm always looking for new collaborations, new opportunities, new mentors, and new mentees. So if any of this resonates with you, please do reach out. So I'm a planetary physicist by training. I'm also an educator, and my research interests are in fluid dynamics, magnetohydrodynamics, mathematical modeling, things like that. But I'm also interested in pedagogical approaches, science education, arts and science, and what I like to call be a Jedi, giving a sense of belonging in the sciences, making it accessible, just, equitable, diverse, and inclusive. And I do all of this applying a modus operandi of empathy, creativity, novel and conventional approaches, and hopefully you'll see a little bit of that in the talk that's to come. So back to our topic, it said understanding and navigating our magnetic world with AQ. What is AQ? It is the combination, it's a powerful combination, a union of artificial intelligence and quantum physics-based innovation. So it combines the power of both. That's what AQ stands for. Why AQ? What's so special about it? So the quantum physics aspect gives us the accurate and sensitive observations, and AI brings efficient and effective data processing to those observations. So that's the idea behind AQ. And that's what SandboxAQ does. SandboxAQ, we focus on 4 main AQ solutions. So we have cybersecurity, so quantum cryptography, AI and quantum sensing, which I'll talk more about, and AI simulation, so doing quantum calculations and computing to determine new material, drug discovery, and so on. We'll focus on AI and quantum sensing today. So why quantum sensors? What does quantum sensing enable? Quantum sensors beat current limits. There's no drift in quantum sensors over time. And they're much more accurate. And so they're very precise devices to measure various things, and today I'll be talking about magnetic field sensors in particular. Now you combine all that very sensitive observation with the power of AI to be able to tease out different signals, and you can make some really cool discoveries. At SandboxAQ specifically, we use magnetic quantum sensors for two different things. So there's biomagnetic sensing. You've all probably heard of echocardiograms. There's a magnetocardiogram, which can detect electrical signals from the heart in the neurons, and non-invasively be able to tell you when something is starting to go wrong. And there's geophysical sensing, so you sense the magnetic fields from the Earth system, which I'll talk a lot more about today. That's my focus. So I wanted to give everyone an overview of our magnetic world and what is it that these sensors are picking up. Oh, there was supposed to be a movie here. I'm not sure if the movie is going to play. But if you saw the movie, we'll just go on to the next slide. The magnetic field of the Earth is predominantly generated in Earth's core, in the liquid outer core. So the mechanical motion, the churning of a liquid iron ocean 3,000 kilometers beneath our feet, that mechanical energy is turned into magnetic energy in a dynamo process that creates the magnetic field of the Earth that we can detect with compasses. We call the North Pole, South Pole. But it's not just that. Rocks that form in that magnetic field retain a component of that magnetic field when they lock that in as they're forming or as they get set. And that is a different signature because these rocks are forming over time and the magnetic field is changing over time. So there are two components already. But we really like this component in particular because you're not just able to navigate between north and south, but it's almost like you have a fingerprint. So if you know where you are on this map, you can use this magnetic field signature to get around and navigate the world with. So it's a new form of map. So we really like this field. But that's not the only magnetic field either. You see a picture of a solar flare. So the solar wind carries magnetic field from the sun. That magnetic field interacts with Earth's magnetic field. When two magnetic fields interact, they create current systems, and those current systems in turn create more magnetic fields. So it's starting to get very complex. And I'll walk through some of these different current systems that are dominant. So you have the magnetopause currents. That's what we call the magnetosphere. Magnetotail currents, and Birkeland currents. Birkeland currents are very interesting because that is where open energetic particles go along the magnetic field lines of the Earth, and they interact with the atmosphere to cause auroras. And there is a ring current system, but we're not quite done yet. This is a closed loop, so the Birkeland currents and the ring currents have to connect somehow, and they connect in our ionosphere through a number of different current systems. Now, why did I put this slide up and talk you through all these different current systems? All these current systems create magnetic fields. So if we're sensing magnetic field around Earth, we are picking up all of this, and on top of that, any electrical currents that we produce in our system itself, we're sensitive to that as well. So it's a problem of superposed signals that are time varying. This is going to be another strand, perhaps, of talks that are to come. And the scale of it all. So the crustal field that I said is a good map that we can navigate by is about 300 nanoteslas, whereas the Earth's core field, that's the dynamo that's producing the main magnetic field of the Earth, is 5×10⁴ nanoteslas. And all in all here, we have 12 orders of magnitude covered from the human heart, which produces a signal of 0.05 nanoteslas, all the way to an MRI machine. And so if you have a sensor that is sensitive enough to pick all magnetic field signals, it's picking up all of this. So why do we need an alternative navigation technique that's based on Earth's magnetic field? GPS is what we tend to use nowadays, but GPS is not foolproof. It can be jammed, it can be spoofed, and in current geopolitical conditions, it happens quite a lot. So if you are flying and your true location is along that line, and GPS goes out, currently we depend on inertial systems, INS, and that tends to drift over time. So over a certain time period, you'll find yourself quite off from where your true location is. But with this magnetic navigation capacity, we can anchor that drift. So it's not necessarily only to function independently of GPS and inertial navigation systems, but it is also to anchor and give a truth value. And you can't jam or spoof these signals. So, and it can't be changed by atmospheric conditions. So it's unjammable, but we also want to produce a diversity of sensors so that we can navigate robustly and effectively and safely. So wanted to give you a quick rundown of different types of quantum magnetometers. And their main advantage, as I said, is it's long-term stable. They're passive sensors, so they're jam resistant. And what we really like is the sensitivity. It's picking up the whole breadth, that full scale. So how do we process all that signal then? If we're picking up everything, what do we use to process it? And that's where AI and ML come in. So to demonstrate that, I wanted to start off with MagNav challenge. So the US Air Force and MIT did a collaboration where they wanted to pursue this specific challenge, to be able to remove all that is noise and just find the magnetic signal to navigate with. And they flew a Cessna flight, 1 hour flight time, 200 kilometers, and they had a number of quantum magnetometers on the flight. It's an open data set. There is a GitHub page. They even have a Julia code available. So anyone who wants to take a gander at this, feel free to. And you can still give in submissions for this, I believe. And they found that they did improve accuracy over INS. And a lot of the efforts that have come in for this use classical machine learning and deep learning. So this is, me and Alexis did not talk about this beforehand. We have very similar slides here. So I won't go into the details of this, but essentially the question is, can we do better than classical machine learning techniques, which used MLPs, multi-layer perceptrons, or deep learning, the LSTMs, long short-term memories? Turns out we can do better, and there's a paper that was led by Favor Nerys, who is a Sandbox resident, intern, and also a PhD student at Stanford. So she looked at liquid time constant networks, which was developed at MIT. How does this work? It uses ODE solvers, it's very high dimension, and it does sequential tasks. The difference between what you saw earlier and this is it models complex time-varying signals. Temporal dependencies are accurately understood and represented. And the way they do that is, or the inspiration for doing this comes from studying worms for the researchers, which is why they have temporal dependencies. And the benefit is it's more generalizable, it's faster, and you can do it potentially in real time, which is what we would need if we're navigating with these signals. So I want you to focus on the two numbers highlighted here. I'm showing RMSE, so you want it to be close to 0 as possible. The error should be low. And the previous models are quoted up there, and the model that does the liquid time constants closed form performs best. And compared to classical models, we see a 58 to 64% reduction in error when we apply this technique. And what does that translate to in terms of magnetic field signal? So if I have a truth field signal that is plotted over there as my flight is going across, and I have a time signal, time series of it, this is what the predicted signal ended up being. So it looks almost similar to the truth signal. So we got very high accuracy with this technique. That was with the MagNav challenge. But we continue to fly our own boxes, and these are some of our partners in that effort. So we have a number of boxes. We're collecting data all over the globe. So can we do even better with all of this data? The short answer is yes. And to know how, you have to stay tuned. I'll be presenting a talk at the American Geophysical Union meeting that goes into a lot more details on this. And there'll be another talk at NeurIPS, both in December. Or you can talk to me after this. Future outlooks with AQ. How does AQ transform the science? That is Strand 1, right? So we're collecting, imagine a world where we're collecting data on all the flights that we all flew in from. Perhaps some of you took trains and other things, but imagine data collection from all of those. As we fly continuously and get this data that is very sensitive, we're going to be able to identify changes that are naturally occurring in the system itself as well. And soon we'll be able to monitor its changing core and external field better than ever before. And there are some precedents to this. So I, for my PhD, did this as my project, where I took the Iridium satellite constellation data, 66 commercial satellites, and took the magnetic data that they had to build a magnetic model of the Earth. Our state-of-the-art before then was about 6 months. You can build a snapshot of Earth's magnetic field. We got that down to 2 hours. So I can monitor Earth's field every 2 hours and see changes that's occurring in that. And the change pattern that was dominant, that was fascinating to me, was you could see a global wave pattern move across the planet in 14 months. And it directly tied to a wobble of the Earth. So there are lots of physical insights from that wave that we can then get. We can learn about the core flow dynamics, the flow in the core. You understand the forces. So that's field of force. You understand core magnetic field strength. We know the strength of the magnetic field at the surface, but we don't know the strength of the magnetic field inside the planet. There's a component of the field that doesn't come up. So we can guesstimate that. And we start understanding the different excitation modes for these types of waves that we observe. And it's almost like an MRI machine. You have the field inside, and we have sensors on the outside, and we get to scan everything in between. So if we can do all of that with just 66 satellites and a grad student, imagine what we can do with all the flights and AI. We can also do better in characterizing external fields. So we know that solar storms happen, and we need to be resilient to that. There's supposed to be a movie there showing Mercury being blasted by external field. So we were able to take messenger data, find residuals in that data, and simulate that. And messenger was not at the planet for very long. So imagine what we can do with a lot more data. So here are some potential possibilities to come. We would be able to predict changes to Earth's core field, which is of interest to a lot of folks. We will be able to predict external field changes and when solar storms might occur. We will answer open questions in fluid dynamics and magnetohydrodynamics. And we'll close the gap in understanding whether you need planetary magnetic fields for habitability and life. So I've tried my best to tie my talk to all the other strands, and I've labeled them here. But all of this wasn't done by just me, so I wanted to give a shout out to the whole team at AQNav. And here are some QR codes for the different references that I shared. So if anyone wants to take a picture, you can of this. And thank you. And to students in the audience, do check out our residency programs. It's a fabulous opportunity. Thank you.
Well done. Thank you. Great, thanks, Regu. All right, so our last talk before coffee is going to be Ashley Villar. So Ashley's got a PhD from Harvard, and she did a stint at Columbia and Penn State and has settled back in Harvard as assistant professor. I asked Ashley to give a little bit more background of machine learning in astronomy specifically, but I'm pretty excited to hear how she's going to tell us how to talk to our data and have it talk back. So thank you very much, Ashley. Better now? Okay. So what is so exciting about this field is that it really also does span orders of magnitude in observable space. By that I mean the timescale which is the last duration and the luminosity that we see.
And for historic reasons, that has this bizarre number called a magnitude. And you can ask me about that at coffee if you're not an astronomer. But there's also a whole zoo of physics underlying those explosions that we see. It can be the accretion of matter onto a supermassive black hole. It can be the collision of extremely dense stars. All of this is happening, and it's happening unlabeled in the sky. We just see something. And our goal is to kind of piece together this zoo and tell the story of how stars live and die. You're going to hear a lot for the next few talks about this upcoming observatory called the Vera-C-Rubin Observatory that's being built right now in Chile. That's going to begin a 10-year survey, or basically a movie of the slowest movie ever, of the southern sky over 10 years. I'll stand right here. In which we will have an unprecedentedly deep and high cadence visualization, and we should see millions of things happening in the night sky. In particular, my group thinks a lot about the explosions of stars. We call those supernovae, and I abbreviate that as SME, apologies. But I really want to emphasize that this is such an exciting time for astronomy right now because it really breaks exponential growth of discovery rates that we've been seeing for decades. So back in the 80s, before I was born, we would discover about 10 supernovae per year. Vera-Rubin's going to discover 1 million per year, so thousands every single night. What's exciting about this is that there's potential discovery space to find unknowns. We will be seeing these millions, we'll see thousands per night, and in real time, we make decisions of, okay, what is the most important thing that has gone off in the night sky tonight that is worthwhile to study in more detail? That's a very, very, very small fraction that we can actually spend real time on, and that's limited by resources that we have. It's really time expensive to get a spectrum of what's happening, but also it's expensive to get a graduate student to help study these events. And so we really are limited to less than 1% of everything we see. What I find so exciting is that the unprecedented discovery rates, in theory, lets us discover what has not been seen before. If we discover 1 million explosions every year, there's a chance that we can find a 1 in a million level of phenomenon. Even if that phenomenon is something that's not expected in this physical landscape I presented for you. And of course, in this group, that phenomenon might be from other intellectual life. Okay, so that's the idea, is that we have this kind of observational space that we're thinking about. We see all these time series, and we have to try to figure out how in the world do we look for new things if we don't have a physical model. I'm rephrasing what has been said to you, but in the words I think you'll see again and again. The way we do this typically is that we look at these light curves, light over time, and we extract features from it. As a physicist, those features can be engineered but very easy to understand. Again, like how long is it lasting and how bright does it get? And what I can do is I can then take those like messy, irregularly sampled, different size data sets of light curves, and I turn them all into the same size vectors, and I make scatter plots like this. Obviously, I'm not literally doing this, but you know, I make a small dimensional vector space, and I call that space a feature space, or I can call it a latent space if those features aren't directly observable. And then it's super easy to find weirdos. It's that guy. It's the guy that's not in the high density region where I see lots of other phenomena. What makes this a little challenging is, well, one, someone mentioned this, feature engineering is way harder than I'm giving credit to it. But also, part of this is because there's no like physical model to rule them all. I really can't just say, all of this is being driven by the explosions of stars, and I can write down the exact differential equation and just pull out the energetics of that. I can't, because there's so much that's happening, and by definition, I don't know the physics of the unknown I'm looking for. And that's one reason why we're turning to these data-driven methods, is that we want to extract these features that can be nonlinear, complex, but that I don't have some great idea as a physicist for what it is I'm looking for. I'm still making those same feature or latent spaces, it just now I've changed the axes. The way that we do this, in my cartoon form, has already been said to you, and I said it in passing. I take some higher dimensional version of my data that is many, many points of my light curve, and for every one of those different light curves, the explosions I see in the night sky, I project all of them into a low dimensional space. That projection I'm finding is really hard. It is not, and when I say that, I'm not literally doing linear algebra typically. I'm typically doing some form of a neural network, some deep learning model. Okay. When I train these neural networks, the only thing it really knows about the system is what I tell it to optimize. I tell it, here's your objective in life. Maximize or minimize this objective. We've heard this term, self-supervised or unsupervised. That means I'm not telling it, your objective is to tell me the labels of all these interesting physics. Your objective is not to tell me where the weirdos are. We're going to play a clever game where we say, no, your objective is to just learn about yourself. And one common way we do this is that we say, to do this projection, let's play a trick. You're going to start with this high dimensional space, project into that lower dimensional latent space, and then so that I can give you an actual objective in life, unproject. Go back to the original space. And then my goal is going to be, can you reconstruct yourself? Can you reconstruct yourself, but with this really important bottleneck that is this low dimensional latent space in the middle? And this common setup you've actually already seen. It's called an autoencoder, and you'll see it again and again, where there is this idea of doing the original projection, the encoder, and then going back to the original data, that's just a trick to help us actually train this neural net to learn about itself. But at the end of the day, we're going to throw away the decoder, and we're just going to be left with this wonderful low-dimensional visualization of the data itself. And we can use that to look for weirdos. And then really the game is that simple. Now that we're in this low-dimensional space, how do I actually find anomalies? For example, this cow, which is a cow for an actual reason, but you can ask me at coffee. And I could look for things that are in a low-density region of the space. And one way that I think you'll see in this, because we use it a lot in astronomy, is something like an isolation forest. Really, I look at these spaces like the scatter plot. I randomly put down a cut in this space, and I just ask a question. Hey, are you really hard to isolate? Like, does it take many, many cuts of my space? Or is it really easy to isolate you? If it's easy to isolate you like this cow, you must be super weird, because that was way too easy. And if you are really difficult to isolate, well, you must be really normal. You're just in the middle of the pack. So things like this let us find those low-density regions without actually having to do the much, much harder task of estimating density in a moderate dimensional space. Okay. I flew through that hoping that I saved time. Perfect. So now some fun things. That was the basic idea that has been shown to you and will be shown again and again, because it really is the language we use to talk about this. We use representation learning. We're building these latent spaces that represent the data. And we build them in a way that we can find interesting, complex, nonlinear features that still really do capture the fundamental summary statistics that we want. There's tons of really fun open questions that we're now working hard on. For example, in this latent space, as a physicist, I may or may not want my latent space to actually have physical meaning to it, or at least obey some physical laws I know should be true. I'm just trying to remind myself, oh great, I did do this. So to do that, one way that we can try to enforce physical laws is that we can change that neural net's objective in life. Instead of just recreating that original time series that you had, which is pretty straightforward, what if you also did a few things? What if I do have some labels? Like I know that these guys are explosions and these guys are supermassive black holes. Can you try to cluster these together? And I can even do this without labels, and that's this idea of contrastive learning, that I can try to build in natural clustering to groups I know should exist. Or can I just directly actually input known symmetries that I have in physics? So for example, I actually know exactly how time series should behave as a function of distance from like myself to the object, not distance in this space, but distance away from the Earth. I know that if you are very, very far away, you look much redder, and you have a very dilated time series, because time appears to be moving more slowly. Why don't I just directly build that invariance into the objective that my neural net has? So this is the way it's forward, and we're thinking a lot about how to do this. Let's see what I want to say. How to do this in a way that actually regularizes the space so that when we actually look for new anomalies, we know that they are of physical interest and not necessarily, like Michelle pointed out, a defect of the instrument that we happen to be using. Okay, the other thing that has been mentioned as well, I think by Alexis, about that we're interested in is the fact that we actually have lots of different types of data. I talked all about these time series we have, but that's not all we have. We typically have other pieces of information that have varying levels of richness, that is how much information they contain, and how readily available they are. So I have lots of time series. I have a lot more just images of galaxies. And it turns out most of these explosions in the night sky happen in galaxies other than our own. And the type of galaxy that you come from tells me a lot about what type of explosion you are. So we can use this data as well to understand what sort of weirdos there might be. And then much harder to get, because it's very expensive, we can get spectroscopy. We can really actually have a very detailed understanding of exactly what elements were synthesized in an explosion or pre-existed in that explosion. What we're thinking about now are these multimodal style of foundation models. That is to say that I know that this spectrum is the same comes from the same object as this light curve. A different, much more terrestrial way of saying this. I know that this picture of my poodle at home matches my natural language description of my adorable little poodle at home. And there's a way I can actually tell my neural net, hey, in that latent space you built up, these two vectors are the same object. Point them to the same vector. That is what the direction we're going in this kind of contrastive learning way of building in one latent space that represents all of these different modalities of data by explicitly telling it how to cross-link that data together. One way that we've done this recently with something called the Young Supernova Experiment is to build an anomaly detection pipeline. So this is great work done by Patrick Aleo at UIUC. To build an anomaly detection pipeline that actually does explicitly put together time series that's coming in from something called the Zwicky Transient Facility. So those are just explosions every night we see. And then pictures of the galaxies those explosions come from. And what's fun about this, actually, I'll go one more, then go back, is that we can actually use this joint embedding space to very explicitly look for different types of anomalies that we've already found. What do I mean by that? In this example, I'm showing you a light curve, and so sorry, I have to explain this for a second. In the actual colored points, so not the ones with the low opacity, that is one light curve of a supernova. On the right-hand side, these are pictures. The upper left is a picture of his home, his galaxy he came from. What you can now do by building this embedding space is ask the question, I found this guy, here's his light curve, here's his home, find me the closest neighbors. What else in my data set actually looks like this? And that's what else is being shown. Now in the light opacity points, these are his nearest neighbors also being plotted, and his same neighbors, their hosts are being plotted here. And you can see, loosely, they all are these kind of 1As from these beautiful spiral galaxies for the most part. What's exciting is you can do the same thing once you find one candidate anomaly you're interested in, and you can search in galaxy space, you can search in light curve space, or you can search in the joint space. We're thinking a lot about how to put the human in the loop, because obviously we need a lot of domain knowledge to actually do something with this data. One way that we do is this LACE pipeline gives us Slack updates 9 a.m. Eastern every morning. It's very fun to then go through and upvote or downvote whether or not we think this is an interesting anomaly, and then from there trigger our various follow-up campaigns. So then the last thing, so it actually is very brief, I'll just say, the last thing we're thinking a lot about is using large language models efficiently, and the way I like to think about this is talking to our data. So right now, the way that we have lots of data. We have very large databases. They're not nearly as large as many other sciences, but pretty large databases that we query with SQL queries that are customized to whatever science that we want. And there's a lot of work that goes into, poor graduate students typically do, to really think about how do I isolate this class of physics I care about. One thing I think is so interesting, though, is that large language models offer a really different way of approaching this problem in representation learning, so that weird nonlinear representation of our data offers an interesting way to explore that might be hard to talk about in just plain SQL queries. So I apologize, I changed this. This was a movie, but you can ask me about it. I think it won't play here. So the way I like to think about this, though, is that we have this system now. In the back end, we have these large databases that less and less have a clear column header. I'm not just looking at duration. I'm not just looking at how bright the thing was. I'm looking at weird feature 1. That is a good summary statistic, but hard to physically define. In the front end, what we're working on in this beautiful video are chatbots that actually directly talk to that database. And you can ask it questions like, have we found any type 1a supernovae tonight? Oh, okay, what was the closest one we found? And what we're working towards, pie in the sky, is asking more abstract questions. Hey, this one's weird. It seems like it dimmed but then re-brightened, suggesting a second energy engine. Can you help me find more of those? Which I can't show you here. But I really do think that this is a very promising way forward, and it really, in a way, makes it more equitable to talk about the data. there's no longer this lead up to skill set that isn't exactly the most helpful thing as an astronomer to have. Instead, I can just use my natural language and expertise with these chatbots to help me directly talk to my data and have it talk back to me. Okay, so I will just end there, and people can go to coffee soon, I think.
I'll take both. Brilliant. Thank you so much, Ashley. Okay, so we're running a little bit late, but the coffee break's already very short. So I think let's keep a 20-minute coffee break, and we're going to come back at 10:50. So just one final round of applause for all of our fantastic speakers. Thank you. Okay, let's get started. Okay, if everybody could please sit down and stop discussing. Okay, so I think just while the last few people are filtering in and finishing their breakthrough discussions, I'm going to just start the next session so we don't get too far behind. I'm delighted to introduce Paul Nathan, who's got a very interesting biography. 25 years in finance, and then finally saw the light and came back. And is now a PhD student at my alma mater at University College London. Has apparently written several novels, which is kind of cool. His talk, if you read the abstract, it's got a lot of sci-fi sounding terms like dimensionality and manifolds. But I think it's going to be really interesting and very foundational, and I think by the end of it, you're going to have a really pretty good idea of the kind of concepts that we've been trying to convey with anomaly detection. So please, Paul, take it away.
Thank you very much. Perfect. Hopefully you can hear me okay. Thanks so much, Michelle, and it's great to be here. And thanks also to the amazing speakers this morning, especially Ashley, who I think has managed to lay down a good common vocabulary for a lot of the stuff that we do in anomaly detection. Welcome to my talk, Finding Pegasus. Now, with a room full of astronomers, you'd probably be forgiven for thinking that this is going to be a talk about this wonderful constellation, but actually it's about this little guy here. So what a winged horse has to do with science and discovery, and how Pegasus is kind of helping me personally try to enhance unsupervised anomaly detection. Well, hopefully that will become clear in the next 15 minutes. My name is Paul Nathan, as Michelle said, and I'm from University College London's Centre for Data Intensive Science, where we're using AI and machine learning to try and answer some of the big questions in astronomy and also in particle physics. Like a lot of the speakers this morning, I'm an anomaly hunter, so I'm scouring the universe for the unusual, trying to understand it better, and also trying to find that perhaps that elusive something that might push forward the boundaries of science. Now, to do that, the haystack of data that I'm sort of trawling through are astronomical spectra. So for those who are not quite so familiar with astronomical spectra, they're snapshots of light from distant objects like stars, quasars, and galaxies. And the light is split into its constituent colors, and those colors are characteristic of the underlying astrophysics and astrochemistry of the object being observed. It also holds sort of really important information about the object's distance from us and also their age. Now, I'm lucky enough to be part of a collaboration, an international collaboration called DESI, or the Dark Energy Spectroscopic Instrument, and already halfway through its initial sort of 5-year term, it's been starting to answer some of the sort of big questions around the universe's structure, history, and also its future. It's being run out of the Kitt Peak National Observatory in Arizona, and its mission is to gather 40 million of these astronomical spectra. And although that's still like an order of magnitude below some of the things that Michelle was talking about before, it's an order of magnitude above what we've got in terms of astronomical spectra at the moment. So I've got this big haystack of astronomical spectra to look through. That's my role, I guess, within the collaboration, to try and look through for the weird spectra. And the tool that I'm going to be using to try and identify these spectra is unsupervised anomaly detection. Now, again, we've had a good intro to this already, so all I'll say is that the unsupervised bit means that we don't have to label the data first. And so that's an extraordinarily powerful way of dealing with data, because it means we can let the machine learning algorithm or the computer essentially find structure on its own within the data set. And the anomaly detection is kind of as it sounds. I'm looking for weird stuff, I'm looking for sort of unusual things, isolated things, outliers. So they may be rare objects, they may be predicted phenomena, or they may be those elusive unknown unknowns that, say, Dame Jocelyn found in her work. The anomaly detection, we've already seen a couple of examples on the screen. So in 2 dimensions and possibly even 3 dimensions, it sort of doesn't look too hard, right? You're looking for these outlier points, and it's relatively easy to see visually where those are. The problem is that we're not usually working these days in 2 or 3 dimensions. Again, has been sort of mentioned before. We're actually working in much higher dimensionality than that. So these are some examples of some DESI spectra from the Dark Energy Spectroscopic Instrument. These are all captured in 7,800 different wavelength intervals. So essentially, this data is 7,800 dimensions. And so the problem is that the tool that I'm using, unsupervised anomaly detection, doesn't really handle high dimension that well. There was a very nice paper recently, relatively recently, by Han et al., who looked at a bunch of widely used anomaly detection or outlier detection techniques, of which a good chunk of them were unsupervised. And they found that none of them, first of all, was statistically better than the others when they tested them across a whole bunch of different data sets, which is kind of what you'd expect from something called the no free lunch theorem in machine learning. But also, crucially, none of them performed particularly well with high dimensional data. So why is high dimensional data even a problem? Well, the raw data representation is often high D because of how the data is collected, rather than reflecting any underlying physics. So I've already said, like, DESI spectra in like sort of 7,800 wavelength bins, so 7,800 dimensions, but images of galaxies are often much more higher dimension than that, maybe captured in tens of thousands or even millions of pixels. And this unusual, unnatural, high-dimensional representation lends us no physical intuition. It's hard or impossible to work with computationally, and means we're afflicted by what's called the curse of dimensionality. In high dimension, data becomes sparse as distance between the points increases, and points are found increasingly towards the boundary of the space. And weirdly, the distribution of those points becomes much more tightly spread. So the concept of nearest neighbors, which is fundamental to many anomaly detection techniques, starts to fall apart. So dimensionality reduction should be beneficial, and Ashley talked about that as well. But how do we do it, and is it actually a meaningful thing to do? Well, dimensionality reduction relies on something called the manifold hypothesis, and I appreciate it's still before 11 o'clock, and I was told once, but I should never mention manifold before 11 o'clock, but here we go. It's the manifold hypothesis that most real-world, high-dimensional data sets actually reside to a much closer, lower-dimensional manifold. We can just think, for the purpose of this, as a manifold as just being like a lower-dimensional surface. Now, that actually seems to be quite valid for astronomical spectra, which is my domain. There's some very good research by Yip and Portillo et al., who showed that you could compress astronomical spectra down from their 7,800 native dimensionality down to, say, 6 dimensions or 10 dimensions. And the reason that works so well is that actually the data contained in those spectra is very highly correlated. So that's great. So we can do it. How do we do it? Well, we can find that low dimension manifold, and again, we touched on a couple of these points already, using a linear projection method, using something called principal component analysis, which probably a lot of you are familiar with already, or a nonlinear manifold learning method, something like TSNE, or we could use UMAP, which again, we've seen already today, and some other methods, maybe a deep learning method like an autoencoder, which Ashley talked about. But the manifold we find will be different depending on the model we use, and that's a very kind of key point. Linear methods will find a hyperplane or a combination of hyperplanes. Nonlinear methods can find more complex-shaped manifolds. So that kind of got us thinking, well, maybe we could reframe the anomaly detection problem from the perspective of this manifold. All right, so how would this work? Okay, Well, there are two main ways of identifying outliers anyway, right? So one, and again, luckily, we've already talked about this, is to look for points which are isolated or extreme in the distribution because of their distance from neighboring points, or because they're in areas of relative underdensity of points. And in high dimensionality, we've already seen that, it's problematic, so we usually transform to a lower dimension, and we look for extreme and isolated points on the low D manifold itself. So an example of a technique that does that is local outlier factor. Now we're going to call those points and those techniques on manifold. And then the other way is to construct a low dimensional manifold, which well represents the bulk of the data set, and then points which are far from this representation are assumed to be outliers. So that could be using PCA or autoencoder reconstruction loss, and probably not very originally, we're going to call those techniques or anomalies off manifold. All right, so all very well. Okay, the manifold is model dependent, we've already said that, therefore the anomalies detected will also be model dependent. And this is a key point. For a given manifold, on-manifold and off-manifold anomalies are going to be complementary, okay? And they're likely to be quite different. So this thinking would apply if we explicitly combine complementary on- and off-manifold methods, we're likely to consistently discover more anomalies. And the other thing is, if we've constructed the manifold well, then the on-manifold outliers ought to represent extremes in our current thinking, and the off-manifold outliers ought to be where we find new and rare physics. All right, so all very well, and all, let's face it, a little bit nerdy and theoretical. We're doing anomaly detection, so I want to show you some real data, but my real data is 7,800 dimensions. I don't think we're quite ready for that yet, so that will come in about sort of 3 or 4 minutes. But first off, I thought I've devised a little illustration which takes a 3-dimensional data set and then compresses it down to 2. And we actually start in 2 dimensions. And I think that's, hopefully it'll be a little bit memorable, and we can go with that. We can start in 2 dimensions, and our data set for, again, a room full of astronomers is horses, okay? I quite like horses, so, and we're going to plot height and weight of horses. So this is an idealized set of horse data. We'd expect it to look something like this if we plotted height and weight. There's reasonable correlation between height and weight for horses, right? But we're doing anomaly detection. We need some anomalies. We need some outliers. So we can have these 2 points here. So enter my 2 friends. On the left is Eohippus, which was a horse precursor. It was about 20 centimeters high. And on the right is a visualization of Samson, who was 2.2 meters high to the shoulder, and apparently the largest horse that ever lived. I think that's still a slightly exaggerated picture, but you kind of get the idea. All right, so that's our horse data set, 2 dimensions. But we want to add 3, okay? We're not going to hold back, we're going to add 3. And this, our 3rd dimension that we're going to add is numbers of pairs of wings. Okay, most of the data here is going to be unaffected by that, as you'd probably expect. But we're going to have 1 point, and that point is, of course, going to be Pegasus, right? Pegasus flies to the rescue, right? Okay, so now we've got our 3-dimensional data set. Remember, we're doing anomaly detection. Okay, but we're going to pretend that we can't cope with 3 dimensions. So normally we're in something like 7,800 dimensions. We need to squish it down to maybe 6. We're in 3. We're saying we can't deal with that. So we're going to do some dimensionality reduction. We're going to use PCA to find a lower dimensional manifold. Now, the lower dimensional manifold that PCA is going to find is pretty much just going to be this height-weight plane. PCA works by finding essentially the plane or the hyperplane which best fits the data. Here, it's clearly going to be this, right? It fits most of the data very well. Okay, now we're going to project our points onto that lower dimensional manifold. Let me just take it one back. Most of these points are already sitting pretty much on the manifold. Pegasus gets projected down there into the middle. Now, this is a sort of an important point. Pegasus is average height, average weight, and its wings don't weigh anything because its wings are magical, right? I mean, it's not going to weigh anything, right? But I guess the important thing is there that if this feature that we're modeling with this extra dimension isn't well correlated with the other features, the observable features, the normally observable features, then it could be that when we do dimensionality reduction, interesting points can get lost in the middle of other points. All right, okay. Let's do some anomaly detection, right? So first of all, we're going to do on-manifold anomaly detection. We're going to use local outlier factor, right? Hopefully we know how this works now. We're going to look for points which are in areas of underdensity or isolated points. So we're going to find Eohippus, we're going to find Samson really easily, right? Because they're out on their own. But we're not going to find Samson, we're not going to find Pegasus, because Pegasus is lost in the middle of the other dimension. So local outlier factor will find us a couple of like extreme points, but it won't find us Pegasus. Now, if we used our other method, which is off-manifold anomaly detection, here we're using reconstruction error. So we're looking for points which are poorly reconstructed or poorly represented by the low-dimensional plane, clearly we'll find Pegasus, because it's very poorly represented by the two-dimensional plane, but we probably won't find Erebus and Samson, because they're actually sitting on that plane. So if we sort of summarize, we can see we've got some on-manifold anomalies, we've got some off-manifold anomalies for this manifold, right? If we'd created a different manifold, we might have a different representation, but for this manifold, this is what we're seeing. If we could combine both of those sets of anomalies, we'll end up with a superset of anomalies which might help us to find all three of these anomalies. And they're all interesting points, right? We'd be interested in finding all these points. All right, okay. So that's 2 or 3 dimensions, right? We're going to get a little bit hairy now. We're going to go up to 7,800 dimensions. Okay, so this is using real DESI data. It's just a sort of, like, I guess, a toy data set, about 50 to 60,000 spectra, split 60% stars, 40% galaxies. What I've done is I've taken the raw dimensionality, 7,800 dimensionality. I've squished that down to 6 dimensions using PCA and an autoencoder, so I've done it in 2 different ways. And then I've visualized those 6 dimensions, because we can't really see 6 dimensions, right? So we still have to squish those down further into 2 dimensions using this manifold learning technique, TSNE, but we could have used UMAP or whatever. All right, now this is what these manifolds look like when we squish them down in 2 dimensions. So the first thing to note, which is maybe an obvious point, is that they look a bit different, right? And this makes the point that the manifold that we generate is going to be model dependent. The second thing and it's not just a rotational thing, they are actually a bit different. Second thing to note, maybe just in sort of like parentheses, is that you can see that the stars which are in red and the blue and the galaxies which are in blue are kind of sort of separated within the distribution. And that's why, that's the other reason why people like unsupervised dimensionality reduction, because it gives you a bit of classification for free. All right, we're doing anomaly detection. So now we're going to take one of those manifolds, we can take the PCA manifold, and we are going to look for anomalies both on and off that manifold. We're going to identify, for the purposes of this, it's just a toy example, we're going to identify outliers as just like the 1% of points which are like most poorly reconstructed using PCA, or which have the highest local outlier factor rating. Right, so first of all, this time we're going to start off manifold using our PCA reconstruction loss. So these are like our Pegasus points. So the bright blue dots on there are the points which, using PCA reconstruction loss, we identify as the most anomalous points. If we look on manifold, using local outlier factor, so for these are the points which are the most in the areas of lowest density and which are the most isolated points, we find these yellow points. So the sort of the obvious thing, or the punchline of this is that they're not the same. Okay? The similarity score between these is only a couple of %. So if we combine both sets of anomalies, so complementary on and off manifold method, we'll end up with a superset of anomalies, which gives us more potential interesting things to look at. And we see exactly the same thing with a different manifold which we've constructed from the autoencoder. Again, the on-manifold anomalies and the off-manifold anomalies are different. If we combine them, we get a bigger superset. Now, this is obviously only a starting point. Once you've got this superset of anomalies, you need something like maybe Astronomy, that Michelle and Bruce worked on to curate those anomalies and actually then end up eventually getting an expert in the loop to visually inspect them. But what it does do is it gives you a bigger set of anomalies and of potential sort of weirdos that you can look for. All right, so quick summary and takeaways. Unsupervised anomaly detection can struggle with high-dimensional data. Hence, researchers usually choose to work in lower dimension, and this creates a manifold which is model-dependent, hence the anomalies detected will also be model-dependent. And we've reframed the problem from the perspective of this manifold, dividing unsupervised anomaly detection techniques, anomalies into on and off manifolds. For a given manifold, combining complementary on and off manifold techniques should widen the number of anomalies that we find in high-dimensional data. If the manifold is well constructed, off manifold is where we might hope to find new science. So many researchers are currently just intuitively combining different anomaly detection techniques, but we hope by viewing the problem explicitly from the perspective of the manifold, it will inform their choices and enhance anomaly detection. It's very much live research, so I'm going to actually apply this to a big sort of DESI data set, hopefully later on in the summer or the autumn. And the idea also is that, and I think this is one of the things with anomaly detection generally, that these techniques are portable to different domains as well. So we could easily use this in medicine, we could use it in financial fraud detection, whatever. And we've got a paper coming out later on in the autumn. So I'll just leave you with a thank you slide. Oh, I think I've missed somebody off. There we go. And just to say, yeah, thank you so much. And I hope if it's inspired any of you to do some anomaly detection, then the more people we've got looking for things, the more chance we've got of finding some interesting stuff. So thank you very much.
Amazing. Thank you so much, Paul, for finding Pegasus. The next speaker I'm delighted to introduce is Daniel Muthukrishna, who's originally from Down Under, from Australia. Did his PhD at Cambridge and his postdoc at MIT. We've been working together for many years on anomaly detection for optical time series data. And he's going to give a very technical and very serious professional talk, as you can tell from the title, From Squiggles to Signals. Thanks, Dan. Take it away.
Thanks, Michelle, and thanks for having me here today. It's great to be back in the UK, in Oxford. So, as Michelle said, I'm Daniel Muthukrishna. I'm a postdoc at MIT, and I work a lot on astrophysics and time series data and seeing how we can apply machine learning to this. And I guess the ultimate anomaly, as Michelle's mentioned, would be the SETI signal. All right, so astronomy's reached this pretty incredible time, as we've heard, right, where we have more data available to us now than ever before. And upcoming surveys, such as this Rubin Observatory, are really going to change the game a little bit. It's going to observe over 1 million alerts every single night, right? An order of magnitude more than any survey to date. And I think as such, new and novel approaches are necessary to be able to process and classify and find anomalies in this data set. So one issue we have here is that some of the greatest discoveries in astronomy have largely happened serendipitously, have happened by accident, right? We've heard already from Jocelyn Bell, and when she discovered the first pulsar, at least I read this on the internet, I'll have to confirm with Jocelyn later, she described it as an unclassifiable squiggle, right? And that really was an anomaly, right? She ended up creating an entirely new field of astronomy where you have these rotating neutron stars that create this lighthouse effect. And at the time, I was speaking to Chris Lintott yesterday, he mentioned that they originally thought this might have been the first techno-signature, and Jocelyn was quite upset by this because it meant she had to rewrite her PhD. But in fact, more and more in astronomy, we've had discoveries that have happened largely by accident, right? From the first exoplanet discovery, right, which was 51 Pegasi b, discovered by a PhD student at the time, T.D.K. Lowe's, no one expected hot Jupiters to exist, right? No one thought that a Jupiter-sized planet close to its star would be something that was common. And yet now we find that that is the most commonly found exoplanet in the universe. The first gravitational lensing event, right, where we have identical spectra observed in the night sky, right, confirming Einstein's theories of gravity, also by accident. Fast radio bursts, again, once thought to be alien origin, happened by accident, right? It was a very, very sharp signal in a data set that really did appear as an anomaly. And so the question is, if so much of astronomy, so much of the greatest discoveries have happened largely serendipitously by accident, what are we going to do in this new era, right? So here's an animation I always like to show, which personally I'm interested in supernova, and it shows you every single supernova we've ever discovered, plotted against the night sky, since the first observation in the year 1054, when Chinese astronomers looked up and saw a new star appear in the night sky, up until about 2018. Right? And it's about 13,000 events. And this might sound like a lot, right? But it pales in comparison to what we're about to find, right? LSST is going to observe over 10 million transient alerts per night. And hopefully start beginning observations next year. But astronomical searchers have so far largely relied on human eyes to identify what's interesting and what's not interesting. And so how do we find the needles in the haystack? How do we find what's interesting and what's not from this massive wealth of data? Okay, if there was a wow signal there, would we really have a human writing this, or would we have to have a computer to write on the side of this that they've found something amazing? So we do need to automate serendipity. And so we've seen a version of this plot already, but this shows us some of the known transient universe. That's the time domain, time-changing universe. And I plot brightness on this axis versus time scale on this axis. And up until about the end of the last century, mostly what we knew about was supernova, right? We have type 1a supernovae and core collapse supernovae. But since then, and since we've started exploring and looking more at the night sky and observing with new surveys, we've found more events. we found 1 kilonova. Only one event has ever been discovered in 2017, and potentially more soon, right? It's a very rare and novel event. We got novae, we got intermediate luminosity red transients, calcium-rich transients, tidal disruption events, which are stars being ripped apart by black holes, superluminous supernovae, 0.1A supernovae, which are still hypothetical events, and gamma-ray bursts, these relativistic explosions. And all of this is to say that the more that we've looked, the more that we've found. Right? The universe is very rich for discovery. And these are just 2 parameters I'm plotting here, brightness versus timescale. If you consider wavelength and other parameters even more than this, we should expect that there's a lot of unexplored parameter space out there. And for the first time, we have surveys exploring completely new areas of this space. Right? LSST will observe a much brighter much brighter parameter space, and surveys like the Transiting Exoplanet Survey Satellite are observing much shorter timescales. Okay, so we've had this discussion already, and it does lead to a lot of debate on what actually are anomalies. I would say known knowns are the things that we already understand, right? These are not anomalies. But what are anomalies, I think, should be both the rare objects, the things that, that we know about, they exist, and these known unknowns, things like kilonova, where we know only one of them, they're very rare, and these unknown unknowns, things that we don't even know to exist. And the way we can test our algorithms is with these rare objects, and hopefully by applying it to these rare objects, we can find completely unknown unknowns. All right, so how do we do anomaly detection? Let's get into some of the details and some of the machine learning. Okay, so the classical approach is you do some sort of clustering algorithm, potentially the most intuitive, right? You take your data, somehow parameterize it, and you look for the high density region. Anything that's further away from this high density region, for example, these points on these red points, right, they're outliers. And effectively, anomaly detection is just a process of doing outlier detection. Okay? Another approach, which we've heard a little bit about, is isolation forests. And this is, if you've heard of decision trees, it's basically applying decision trees to your data. And if you're not familiar with it, it's basically a game of 20 questions, right? You ask a bunch of questions, for example, was there calcium in this line, or was there not? What was the flux at a particular wavelength? Keep going down this tree until you can isolate each object. If it was really easy to isolate, that's probably an anomaly, right? There was very few parameters that kind of separated it. And if it was difficult to isolate, it's probably an inlier. Okay. So what we can do is we can then apply these clustering algorithms to our data, and we can often do this with, to get some sort of classification process out of this as well. And here's an example where we've applied it to some known transient or variable star events. So for anomaly detection, I think there are really 2 steps. And so I mentioned the second step here, which is this outlier detection. We can either do clustering or we can do isolation forests. But I think the much harder step is step 1, doing the feature learning. How do we find a feature space or a latent space or an embedded space? I'm going to use these terms synonymously, right? And what I mean by a latent space is it's some space that represents your data. So you do some sort of representation learning and you learn some sort of lower dimensional space of your data. And the question is, how do we find a latent space that is useful for anomaly detection and useful for downstream tasks? So typically, we might do some sort of feature extraction, handcrafted feature extraction. We pick out features that we think, as humans, are relevant because we're experts in this field, and we look at, okay, well, we think maybe the rise time of a supernova is important. Maybe the standard deviation is important. Maybe the mean is important. Maybe the color at a particular wavelength is important. And so we pass in all of these things that we think are relevant, and we chuck it into some algorithm like a random forest. This is not bad, but you're highly constrained by your feature set, as we heard from Alexis earlier today, right? If your feature set is biased, isn't a good representation of your data, you're not going to have a good result, right? So what can we do differently? Perhaps we can do something more general. Perhaps we can build some sort of generalized model and learn features from the data directly with the neural network. So what I'm going to try and show today is we're going to try and build some sort of foundation model, a multimodal foundation model that can try and learn some representation of the data, right? And so the analog I'm going to pass in, which is more familiar to you, is probably like ChatGPT, right? ChatGPT can predict the next word in a sentence very, very effectively using a transformer architecture. And we can do the same thing with light curves, right? We can predict the next flux in a time series. And so our time series are effectively the language, and our fluxes or our brightnesses are effectively the words. So this is effectively what we can do, is given some partial data in the gray region here, we can then predict the rest of the light curve. And this is very similar to how a transformer works when you're interacting with one of these LLMs, is you pass in some amount of input text and it can predict future text. Yeah? And so we can do that for a time series as well, where here we've got our data in the error bars and our mean predictions in the solid lines and our posterior predictions in the baseline. Okay, so we can encode the light curves with a transformer. Maybe we can also encode some of the other physics, right? Some of the other things we understand, right? So we have a lot of systematic errors in our data. One of these errors is these telescope systematics. Here I'm showing these scattered light bubbles we get caused by light entering the telescope that we don't really want to be there, right? And they're very difficult to remove because we don't have good analytical models for them. And in the same way that DALL-E can generate images really, really nicely with the diffusion model, we can generate these scattered light images as well and generate some of these systematics. The third mode I want to talk about is images and spectra. Right? So we have our spectra, which we heard in the last talk, and we have our images. Maybe we can just have a convolutional neural network that can represent these architectures. Pretty standard approaches. Convolutional neural networks have shown a lot of success in image classification in general and image generation. So we have our three modes, and what we're going to do is we're going to pass in our three modes into some sort of joint embedded space or joint latent space. So we have our light curves, which are encoded with a transformer, our systematics encoded with some sort of other model, like a diffusion model, and our images encoded with a CNN. And what we want is we want to have some joint space that learns a representation of all of our modes of data, right? And the trick to this is we're going to do something called contrastive learning. And there's no good machine learning talk that doesn't show a picture of a cat. So here's a picture of a cat. And the idea is that we want to have similar objects, so things that are both cats, or in our case, both the same type of supernova or both the same type of object, to have a high similarity score. And so we're going to raise that up. And things that are different, like a cat and a dog, to have a low similarity score. We're going to push them away in this latent space. And the point here is we want to structure our latent space such that it learns to encode similar types of objects closer in that latent space. And this works really, really similar to a really nice paper that was recently released by OpenAI called CLIP, which is this contrastive learning approach. And the idea is that you feed in textual data and you pass in some sort of show me a picture of a cat, and it will produce a picture of a cat and vice versa, right? And it has this joint encoding where you encode both the text and the image data into this space, right? We want to do something very, very similar. We replace text with light curves. And we have our light curves encoded in one model and our images and spectra encoded in the other model, right? And now we can go back and forth between these things, and we have a joint learned representation of both of these modes of data. Great. Okay, so ultimately, once we've done this, right, we have some sort of embedded space that represents our data, and I'm plotting this embedded space in 2 dimensions here with a manifold embedding technique called UMAP. And we have our 2 dimensions that represent all of our data. And these are all of our known classes, and in this plot over here, we show our rare classes, our anomalous classes. Right? And so what we want to do, you can see already that our anomalous classes do kind of separate away because they weren't learned about during the training phase. And what we can then do is we can pass in this feature learning approach. We're passing that feature learning approach into some sort of isolation forest like so. And then we can get our isolation forest to spit out anomaly scores for us as well. Yeah. Here we can see that the common types of supernova here have much lower anomaly scores than the rarer types of supernova over here. Okay, so the red. And so that's ultimately it, right? We can do this. We have these 2 steps. We have some sort of feature learning that represents our data, and then we can do some sort of anomaly detection. So I'll conclude here and say that a lot of discovery in astronomy has been driven by serendipity, and a key goal for us is to automate this serendipity. We need to learn some sort of feature space that is useful for anomaly detection, and one really nice way to do that is to encode all of the data that we have available into some joint space and let a neural network learn this joint space really, really well and structure it in a way that puts similar types of objects together and hopefully anomalous types of objects separately. So Thank you.
Fantastic. Thanks so much, Dan. And we're actually starting to make up some time, so thank you. Our next speaker is Guillermo Cabrera-Vives. So he's an associate professor at the Universidad de Concepción in Chile. He's the principal investigator for ALERCE, which I'm going to let him tell you all about, but it's a very exciting project. And we're really getting to the point where we need to figure out how to go from pixels, from these alerts, to actually finding anomalies. And Guillermo is going to give us a lot more of those details. So thank you very much.
Thank you. Thank you, Michelle, for the introduction. So, there you go. So imagine you're an astronomer in the future, and what you want to do is you're going to wake up in the morning, you're going to grab a cup of coffee or tea, depending on where in the world you are, and you're going to open your laptop and start interacting with the system, right? And the system is going to tell you, last night we observed through this telescope and that other telescope this potentially important astronomical source, right? So for example, we found a couple hundreds or thousands of supernovae, exploding stars, and we found another couple of thousands of variable stars and AGNs and different types of sources. But I also found something last night that you may be interested in. And this is an anomaly. This is something that I don't know exactly what it is. I got data from this particular telescope, this particular database, and I think that this is an anomaly. So the system tells you this, and then it tells you, you know what? You have follow-up time for tonight. Do you want to follow it up? And you check all the data and say, sure, that's what I want to do. Just do it, right? This is what we're aiming at. So some of the tools I just described already exist. Some of them, they don't, okay? And today I'm going to talk about ALERCE. ALERCE is one of the brokers for the LSST, one of the official brokers for the LSST, which you all heard a bit about it. And we're aiming at building this during the next couple of years. So first, I want to talk about alert streams. So most likely you heard about the light, I know you heard about the light curves and all this, but I want to tell you how these are created. So we have something, a telescope, like the LSST, which has these wide field images, right? So what they do is that they have what's called a template image, and the template image is like a historical image of the sky. And then tonight, we observe, and we get what's called the science image, okay? And what we do is that the LSST, well, there's a huge process around this, but it aligns the images with sophisticated algorithms, and then it subtracts them, right? So if something new appears in the sky, it would look something like this, right? So like a point, okay? And so when the LSST finds something like this, it's gonna emit an alert, okay? So if you think about it, during one night, you can have one alert at a position in the sky, and then 2 or 3 nights after that, you may have another alert, and then 2 or 3 nights in the future, you have another one, and so on and so forth. And then you start creating a set of image stamps. This is what they're called, image stamps, okay? And then you can get the photometry, the flux, the brightness of each of these sources, and start putting them in time. So this plot shows the brightness of the source in time. And then for the first night, you have that. For the second night, you have that, and so on and so forth. And this is what it's called a light curve, all right? So we have image stamps, we have light curves, and in principle, they look something like this. This is a real light curve from CDF, okay? And this is a particular supernova. So if you notice, on this plot, I'm only showing alerts, but we don't only have alerts. We can also build a light curve for all sources in the sky. And we can also, and this is what's called the data releases. So you'll have the light curve for all the sources in the sky, or at least the ones that vary. And the other thing that you can do is, if you get an alert tonight, then, there you go. So then, if you get an alert tonight, then you can go back to the images in the past and get the fluxes that were on that position of the sky in the past, okay? So that's what we call force photometry. So we already have 3 types of light curves, right? Alerts, data releases, and force photometry. So Alerce is currently working on CDF data. So we're connected to the CDF data stream, and every night we process CDF. And we're getting around 1 terabyte of data per night, and it's around 1 billion of objects in total, but we're getting around 100,000 to 1 million alerts per night, depending on the night and depending on a lot of things. When the LSST starts operating, this will be 1 or 2 orders of magnitude bigger in data size, in number of alerts. We all talked about this, but 10 million alerts per night, so that's a lot of things. And we need to classify all that and get all the important stuff out of that alert stream. So that's when the brokers come in. So what are the brokers? So in the future, maybe not that far in the future, we have the survey telescopes, right? And the survey telescopes will communicate their alert stream, all the alerts they found every night, to the community brokers. The community brokers, so there are 7 of them that are officially brokers for the LSST, and the community brokers will connect to the downstream brokers, so these are specified brokers for specific scientific cases, but also directly to follow-up resources or to the users community. Okay? And what most likely is going to happen is that after getting all this data processed, we will want to go back and get more data for particular sources. The brokers have different products and services that they're developing. I'm going to talk particularly about 3 of them right now. So it's about classification, calculating features, and of course outliers and anomalies. So just to let you know, there are 7 official brokers for the Vera-Rubin Observatory. There are 3 in the US, 3 in Europe, and 1 in Chile. Alerce is the one that's built in Chile, and it's one that is based on a lot of machine learning models behind the scenes. So now I want to talk about the models. What type of models we have? First, we have what we call the stamp-based classifier. This is like a really fast classifier. So when we get an alert, we get the stamp images, and we classify them really quick, okay? And it's basically a convolutional neural network behind the scenes. And what we do is that we build what's called the supernova hunter. So every morning, you can connect to the supernova hunter, and you can see all the transients that were classified by Alerce last night. Okay, so that's one of the use cases that we already have running. So thanks to the supernova hunter, we've been submitting detections of supernovae to TNS every night, or every morning actually, because the astronomers wake up in the morning and they make sure that everything is correct. And we are the 3rd group around the world that posts more supernova in the sky after, to TNS, after pan-stars and CDF. We also have our light curve classifier. So the model I showed before only classifies into 5 classes. One of them is supernova, the other one is asteroids, AGNs, and other 2 classes. But we also have like a classifier that works on a more detailed taxonomy, and that's what we call the light curve classifier. So how it works, it's basically we have light curves, as I explained before, and we calculate a whole bunch of features from the light curves. And we calculate around 185 features from the light curve. And we have 2 models. One of them is a balanced hierarchical random forest. This is like a standard classical machine learning model. But we also have a time series plus tabular transformer. This is a more sophisticated deep learning model. And those 2 models are already producing classifications. And well, the balanced hierarchical random forest code name is Handsome Squidward. This was an idea from the engineer team. I don't know why they choose that. And the second one, the paper, is called AT-AT, but the engineering team called it Mbappé. Don't ask me, ask them why they did this, all right? That's their code name. And we also have an anomaly detector. So how does this work? It's very similar to what Dan exposed before. So basically, we have the data. We put all the data into a neural network that finds a latent space where the different classes are clustered together. And then when we find, when we look for an anomaly, we see how far away from those clusters these objects are. Okay? And through our anomaly detector on the first run, which was working on alert data, what we did is we found a lot of TDEs and microlensing events. Okay, so those were anomalies at that time, but they are not anomalies anymore, because now they are part of our taxonomy, and on the new model that should be put into production this week, those are going to be part of the taxonomy. But we also find stuff that is weird, that we don't know what it is. So the brokers are built to enable new discoveries, all right? This is super important for us. We need the people to use it. We need science to come out of them. Right now, Alerce, there are around 130 refereed papers that use Alerce. There is around 180 papers in total, adding up those that haven't been refereed. That was up to the last time we counted, which I think it was like 1 or 2 months ago. And I want to point at one particular paper that I think is super interesting. And this was led by Paula Sanchez-Saez. And what happened is that she found this particular galaxy that for 2 decades showed no optical variation. And suddenly, on December 2019, Alerce classified it as an AGN. Okay, so something happened there, right? So it was not varying, and suddenly it started varying, okay? So what they did, they started looking at archival data, and they also did perform follow-up observations of this particular object. And what they found is that there is something weird, of course, because something changed. And the hypothesis they had is that this could be a newborn AGN, or it could be an exotic TDE or something different, okay? So this is the kind of science that I expect to be happening during the next couple of years. You find something weird, something that was not discovered before, and then you say, what can I do about it? Let's go and look for more data on the archives, right? Let's go and do follow-up observations on this. We have also released all the features that we calculated up to May 3rd of 2024, so you can all go and get them. There are around 174 features, and we have used this to look into the feature space for stuff, right? You can go and download it. It's a Parquet file. And what we did, well, we started with one of these, right? So it's a microlensing event. And we said this was one that was discovered by our anomaly detector. And then we found on the feature space a lot of these microlensing events, all right? And that way, what you can do is you can grab all this and put them back into your training set and build models. This is another thing that was curious that we found. We don't know exactly what it is, but we found a bunch of them. A hypothesis is that it's a supernova with circumstellar interaction. So, user stories. This is what computer engineers usually like. Any computer engineer in the room? Can you raise your hand? None? Okay, one. All right, so first, quasi-real-time supernova detection. So CDF is feeding data into Alerce, all right? And you have a human that goes and interacts with the system and asks, what supernova were detected last night, all right? And Alerce responds to that, and then the humans say, okay, I shall report them to TSN, all right? So then you go through Alerce and into the database of TSN, and you submit a new set of supernova, all right? This already exists. This is the supernova hunter I showed before. Another option. So I am the human, and then I want to find a particular class of objects. Okay, so I want to find AGNs. Then I go to Alexis, and Alexis gives them back to me, and then I find something that's interesting, and I say, oh, this one's interesting. Then I will go into the data and try, into the archive data, and try to get more data out of it. Or I can perform follow-up observations, okay? And this already exists thanks to handsome Squidward and Angappan. Right? Another one, so historical anomaly detection. I'm the user and I say, what anomalous sources are in the database of Alexis? Okay, so I can interact with Alexis and I say, oh, this one's interesting, so then I can go to archival data or for follow-up to perform follow-up observations, and that already exists thanks to the models we already deployed. So that's fine. Now I'm going to talk about similarity search. So what sources are similar to this, all right? And I have a whole bunch of sources, and I want to find similar sources to this. I go to Alexis, to the database of Alexis, and then I grab the data, and I can perform follow-up again or go to archival data. That also exists because the feature data set is public. Great. Okay, so now we're going a bit more into the future. So we're going to think about multi-survey, okay? Quasi-real-time anomaly detection. So in this scenario, what we have is Alexis being fed by multiple surveys, okay? So as you can see here, we're thinking about optical surveys, but you can also have gravitational waves or whatever type of survey you can find around, right? And then the user comes, and now Alexis tells the user, last night I found this rare object. You may want to check it out, okay? And then the user says, whoa, many thanks. And now I go to the archival data, I perform follow-up observations, and I'm super happy, and I find something weird, okay? Let's say now, we're in the future, a bit further into the future, and Alexis says, last night I found this rare object. Data says this is interesting because, right? And it gives you an explanation on why that is interesting. And usually, in order for that to happen, you will need Alexis to have models that are fed by multi-surveys, but also that are fed through archival data. And now we're talking about multi-model models inside Alexis. Before we were also talking about that, but that's fine. And then I say, really? Many thanks. And I go and perform follow-up observations. And now this is like the far into the future. We say, we want to do semi-automatic follow-up. So Alexis says, last night I found this rare object that we need to follow up immediately. Given that you have allocated time, should I run the follow-up campaign? And you say, let me check first before running anything. And then you say, okay, go for it. And then Alexis performs the follow-up observation. Or maybe a tool, maybe not Alexis, because most likely that's going to have to be connected to the TOMS. So to summarize, what we need is the systems that have to be built and that have to be connected within each other. In particular, we're one of the brokers. There are other brokers. And we're exploring a diversity of use cases. And we need all the brokers to prepare for the LSST, but also to be interoperable with all the data systems that we have. Before leaving, I just wanted to point out that, oh, that slide is not here. Okay, it's not here, but I'm going to tell you about it. So in December, we're holding the Astroinformatics Conference in Puerto Natales. It's one of the most beautiful places in the world, according to me. It's really amazing, and all of you are really invited to come. We have a very limited number of places because the place is very small, but it's really, really nice. So thank you.
Thanks so much, Guillermo. For our final talk of this strand, I'm delighted to introduce Vishal Gajjar, who is a staff astronomer at the SETI Institute, a visiting researcher with Breakthrough Listen at UC Berkeley, and a project scientist for Breakthrough Listen's international collaboratory facilities. So Vishal is going to basically take everything that we've just heard, put it all together, and bring it back to the reason that we're here, which is the hunt for technosignatures. Take it away, Vishal.
Thank you, Michelle, and thank you for the organizer for inviting me to speak on this topic that is sort of so close to my heart. Yes, so I am an outlier. I am not an AI researcher per se. I am a radio astronomer. So we do work during the day and night. So we don't have to wake up in the morning to look at what is there in the sky. We do that during the daytime as well. What I'm going to talk to you about today is that so far what all you have heard is different techniques that people are using in astronomy to really push the field of astronomy. But I'm going to focus more in terms of like what AI is going to do in terms of finding extraterrestrial intelligence. So for this audience, I definitely don't need to introduce or justify why that's important. So far, what we have learned is that any time we look at the sky or any star you look, it's likely to have exoplanet around it. So exoplanets are probably almost everywhere. So why is that a constraint? Why is the life not likely to be there as well? So obviously, this brings us to the question, like, are we really alone in the universe? And the likely answer is probably not. But to answer that question, it's a very complicated it's a very complicated question, and you need to understand each and every strand of this complicated mystery to really unravel, to answer this question, are we really alone in the universe? So what I'm going to do throughout the rest of my talk today, I'm going to break it down into multiple strands, and I'm going to explore each one of them with you. First, I will tell you outline of different ways by which we can find intelligent life. We're going to talk about different techniques that people are currently exploring. And then in the end, I'm going to talk about AI and upcoming facilities. So the talk title might seem like this YouTube video that you might click, but you have to wait till the end to get to the right thing. So I will come to AI towards the end. So my goal is that by the end of the day, if you get to learn answer of these three questions, I will be happy. That what exactly this basically summarizes everything that what we are trying to do. All right, so before I move forward, I just like to define this term which I'm going to use throughout the rest of my talk called technosignature. You all have probably heard about the word called biosignature. A technosignature is an extension of biosignature. So what is a technosignature? So technosignature is a direct or indirect evidence of past or present technology that has been developed by extraterrestrial intelligence. So this actually is a very broad definition, and you can cover a lot of different kinds of stuff under the same umbrella. So I'm going to give you a couple of examples, but because of the limited time, I will not be able to explore all of them. But just for the sake of argument, I'm going to give you examples of different kind of technosignatures. One of them is what we call physical artifacts, obviously very speculative, but Oumuamua is a really good example. And there has already been work happening in that area of detecting a similar kind of objects like Oumuamua using the Villar Rubin Observatory. In fact, there was a paper that came out earlier this year by an incoming graduate student here in Oxford, Rogers et al., which actually outlines an anomaly detection algorithm, how we can detect similar types of objects using the Rubin telescope. There are other kinds of technosignature as well. For example, exoengineering. We are talking about extremely advanced civilization, extremely advanced life, which can basically wants to harness all the energy output of their star. So what do? They can build what we call a Dyson sphere around their star, and you can detect it. You can detect a waste heat that is coming out from the Dyson sphere. So there are surveys that's already ongoing to detect it. In fact, you might have heard about these recent discoveries about some of the objects that discovered with the, that are potential candidates for Dyson spheres. So that work is already ongoing. That is, again, a potential technosignature. Atmospheric pollutant. We use a lot of technology. We use a lot of, some of these chemicals that are there in our atmosphere are not biological. And if you do detect them, that's an evidence of technology. Obviously, I wouldn't say they are intelligent if they are polluting their atmosphere, but it could be a phase in their evolution, right, like we do, but like we had, where we actually had a lot of these chemicals in our atmosphere, but you can detect it. So the best thing is that with the modern day technology, it is possible now, at least within a certain light year distance, that you can detect these technosignatures. But the last thing, which I think what I'm going to talk for the rest of my talk is electromagnetic waves. So how do we detect electromagnetic waves as a possible sign of extraterrestrial intelligence? There are various different types of technosignature in electromagnetic waves. I will not go in all of them. I give you an example of two case studies. One is a signal that is highly concentrated in frequency. This could be in radio or in optical. So if you put a lot of energy, concentrate all that into only few frequency channels, that's a very good sign of it being artificial, because so far we don't know any natural process to produce a signal like that. The other is the opposite extreme, that you put a lot of energy in time, like nanosecond. So nanosecond optical flashes or nanosecond radio pulses, for example, are also potential technosignatures. So I guess this probably might have given you a good idea about different kinds of things that we call a technosignature. Now I'm going to talk about different search strategy. What are the search technique we use to search for these different technosignature, especially in the electromagnetic spectrum that I just talked about. All right, so where do we actually conduct our searches? So a large amount of the searches are being led by Breakthrough Listen program, and we actually search almost everything that can be potential target. We are looking at our nearest million stars. We are looking at our entire galactic plane. We are especially interested in the galactic center, which is where I personally am very much involved. We are also looking at so many of nearby galaxies as well, and most importantly, we are looking at anomalies in astronomy. This is sort of continuing to the discussion that we were having since morning, and these anomalous objects are going to go up when the Vera Rubin is going to start feeding us more anomalies. So we do have a program to follow up all these exotica as well. And what do we use to observe them? Almost everything. So we use almost 24 radio observatories and optical observatories all across the world to actually conduct the searches. Many of these observatory people who are leading work on this are all in the attendance, so please reach out to them to know more about what exactly the activities are going on there. I may not be able to go to each and every one of them, but I'll give you some of the examples. So let's start with the highest end of the electromagnetic spectrum. So this is the entire, just an example of electromagnetic spectrum that is sort of penetrates our atmosphere. And we talk about the ground-based facilities that can actually see this part of the electromagnetic spectrum. First is the optical band, and then you have a radio band. And we have a number of sort of observing facilities that are actually actively searching at both these bands. So I'm going to talk first about the optical band. So at optical, we have a number of observatories. I'm going to give you an example of one of them is the Veritas telescope. These are 12-meter 4 antennas, which are spread, I think, around 100-meter separation or from each other in Arizona. What they do is that they are actually specially designed to detect gamma rays. So they are not directly detecting gamma rays, obviously, as you can see, they are in the ground. But what they do, what happens is that when gamma ray passes through the upper atmosphere, it interacts and produces the shower of photon. And that shower of photon is what these telescopes are capable of detecting. In fact, there's an animation there which actually shows you that how the entire shower happens. But the most important part is that it is actually looking at the sky in a nanosecond time scale. So it's actually taking images at around in a nanosecond scale. And this is a very interesting way of searching for extraterrestrial intelligence, because I mentioned earlier that nanosecond laser pulses or optical pulses are potential technosignatures. So we can use the same telescope that is designed to detect gamma rays to detect technosignature. So the idea is still same, but there will be small differences. For example, if the gamma ray interacts in the upper atmosphere, because it is localized event in that particular direction, when it reaches to these different detector, you can triangulate the position. They will come out at a different part in their CCD images. But a plane wave coming from a far away distance a laser source, for example, coming from far distance, will appear at the same location at all the detector. And this way, you can basically disentangle what is produced by natural phenomena and what is basically produced by extraterrestrial intelligence. So this is one effort that's ongoing to search for these extremely narrow optical flashes. Okay, so moving on from optical to radio, and obviously I cannot start my talk without radio without mentioning the amount of interference that we have to deal with. Very nice place to put a radio telescope all across mobile phone tower. It's just a sort of, I mean, it's the image created by DALL-E or ChatGPT, so obviously not an ideal place you want to do your radio astronomy from. But the idea is that radio sky is polluted. We do get a lot of interference from almost everything. You have mobile phone tower, you have electronics that we are using ourselves, aeroplanes, helicopter, everything generates radio waves, and we have to kind of disentangle these radio waves that are produced by our own technology if you want to detect radio waves that are produced by extraterrestrial technologies. So how do we do that? So I'm going to give you an example of a couple of ways by which we try and separate out things that are produced by our technology with what is extraterrestrial. If you are using a single dish, like for example, this is the Green Bank telescope in West Virginia, the way we try and do it is that we move the antenna, which is what we call positional switching. So we move antenna up and down to different parts of the sky. Interference, since it's not coming from that particular part of the sky, it's coming from everywhere else, it will not disappear when you look away. So you have to do this multiple times, and then you will be able to rule out what's actually coming from the sky, that particular one point, versus what's being produced by all the local sources. We have a number of radio telescopes that's currently operational. Just give you an example of 2 single dish telescopes. This is the Green Bank telescope mentioned earlier. Dr. Steve Croft actually leads the program on there. And we have a radio telescope in Sardinia, Italy, which collaborates with us quite extensively to search for technosignature at radio frequencies. We have 3 students who are in the attendance, so please feel free to reach out to them. We have Francesca, Simon, and Andrea. So both of these telescopes are capable of observing all the way up to like 100 gigahertz. So that's a huge range of frequency coverage that we are getting from both these instruments. But they are single dishes, so there are some limitations about the interference rejection that we are able to get. And for that, we have to go to interferometers. I'm going to go to talk about that. So let's go slightly lower in frequency. For frequency, we have 2 ways by which you can basically, in fact, high frequency also has multiple beams, but what we have been doing so far is that we have been using some of the instrument which has these multi-beam capacity. So what this means is that it is simultaneously looking at multiple parts of the sky. So you don't necessarily need to do on and off. You are actually simultaneously observing multiple parts of the sky at the same time, which allows you to disentangle what is coming from terrestrial sources versus what extraterrestrial. For example, we use the telescope, which is one of the world's largest single-dish telescope, FAST in China, which is equipped with 19 beam receiver, which means that it is actually looking at 19 different parts of the sky at the same time. We also have interferometer. Interferometers are magical. You can basically digitally beamform as many beams as your digital backend can support. So for example, with the Meerkat telescope, we've been creating 64 beams. With the VLA and Cosmic program, we've been creating 6 beams. And with the ATA, we are also creating 4 or more beams. And in fact, if you are more interested in talking to about interferometers, you can talk to Daniel, Chenova, or Vial, who leads the program on all of our interferometers. So interferometers are a fascinating way by which we can disentangle sources of interference versus what is basically produced by extraterrestrial. Okay, going to the extremely low frequency, we have a telescope in the Netherlands, and which is the core station called LOFAR. What we are using is the international stations of LOFAR. One is located in Ireland, and one is located in Sweden. This program is led by Professor Evans Keen, who is also in the attendance. So please reach out to him. What we are doing is that because this is an extremely low frequency array, it is actually able to see a large area of the sky at the same time. So what we are doing is that we are using multiple antennas and pointing toward the same part of the sky. And then we are trying to see whether the sources or the signal that we are detecting is coincidental on both the stations or not. So if the signal is truly coming from the sky, it should be there for both the stations. But if it is sort of terrestrial, it may be localized to one of the two antennas. And this way you can disentangle different sources of interference. All right, so lastly, I just want to talk more about, so as you can imagine, interference is the biggest challenge in radio SETI or radio technosignature searches. And this is where AI is helping us. So I'm giving you an example of a couple of ways in which we are using or utilizing AI to really eliminate false positives that have been generated by interferences. So I'm going to give you an example of a telescope in Australia. The program over there is led by, used to be led by Danny Price, is currently led by Joe Bright. What we are doing is that this is a 64-meter single-dish antenna. It actually had a multi-beam receiver on it. So it had a 13-beam receiver, and we actually surveyed the entire galactic plane twice. So we surveyed the entire galactic plane and carried out roughly around more than 1,000 hours of observation. And we searched the entire data set for that. So it covered billions of stars. So we covered billions of stars, and we searched for this one particular signal, which I mentioned earlier, the narrowband signal. We found more than 300 million hits. Now, this is a massive number, right? Nobody, you cannot hire that many number of undergrads to look through 300 million hits. So you have to come up with a better way of eliminating them. Even if, so as I mentioned, even if we are using multiple beams, there are still interferences that kind of goes into our data stream. And to eliminate that, we are using AI to basically help us sort through false positive. One of the ways which we are doing is that we have designed a signal-based classifier in which we have artificially injected signal into our data, and we have trained the classifier to identify it. Once the classifier is identified, we have also trained the classifier to identify if the signal that it is detected is same in all the beams. Because think about this, if you have interference, that interference is likely to be same in all the beams. But if it is coming from the sky, it will be very different for one particular beam with respect to every other beam. So you can do this kind of comparison, and in fact, that has allowed us to reduce the number by 99.8% from our earlier detection. So this has drastically helped us in terms of eliminating a huge amount of false positive that we were getting before, and it's kind of it has brought the number down to something that is humanly possible to inspect. The project is currently led by our graduate student, Karen Perez, who is also in the attendance, so please reach out to her if you have questions about this. The other thing which I'm quite excited also, which is the future ways by which we are looking towards, is the completely an AI-based signal searches. So in the previous search, what we did is that we used the traditional technique to detect the signal first, and then we use AI to verify whether the signal is true or not. But what we want to do is that we want to basically eliminate and make everything streamlined just using AI. And for that, we have developed this technique. The paper was led by Peter Ma and Cherry. Cherry is also in the audience, so reach out to her if you have questions about this. So what we did, so I mentioned this earlier, that for single dish, what we were doing is that we were observing a star, doing on and off observation. So if you have a narrowband signal that is present during both on and off, when you look at that signal in the consecutive sequence, you will see the signal being present all the time. And that you can see on the top sort of left plot. You see this narrow signal that is present in all the panels, which is what we call RFI. So what we did is that we trained the network to classify different kinds of signal that are only possible to present in the on, but not in the off. Traditionally, what you do is that you train a model and you use for classification, but there is a black box problem. We don't understand that what exactly it got trained on. So in order to eliminate that black box problem, we actually helped use an autoencoder. So what autoencoder did is that it provided us a latent space which is sort of a reduced dimensionality and made these things much more simpler. We use this thing called beta variational autoencoder, which actually was trained to create latent space features which are most distinct from each other. In a simple term, this means that when you're looking at images as humans are, you can see things which are clearly distinct from each other. This is what the model was trained on. And if you use the combination of autoencoder along with the traditional sort of training model, it gave us really excellent result. And we were able to kind of do the entire search based on the AI technique, and we actually found some interesting signals. And this was published in Nature Astronomy last year. So finally, I just want to wrap up with what we have achieved by conducting all these searches so far. And I want to present it with this particular graph. So what I'm showing you here, the x-axis is the output power of different kinds of transmitter. And you can see an example, like for example, this is the output power of Earth. Like if our entire civilization, this is what the power consumption that we have. This is the output power of Arecibo telescope planetary radar. This is the output power of, for example, all the mobile phone towers that we have on Earth. And this is the output power of like a Voyager spacecraft, for example, which is there in the, currently going in the interstellar space. If you combine all of these together, these are the kind of limit that we have achieved so far. So combining all the surveys that has been happened so far in this area, these are the kind of limits that we have achieved. So we have eliminated a huge amount of parameter space. So obviously, there is a very less, like I forgot to mention, what is the y-axis? That's the transmitter rate or the occurrence rate. So how many number of transmitters are there per star? So if you survey 1 billion stars and you don't find a transmitter, that means that the transmitter rate is somewhere around 10 to the power minus 9. This is in a log scale. So we eliminated a lot of parameter space. And with the new and upcoming facility, we are just going to push the boundary more further down. We are hoping that if the transmitters are there, if the signals are truly exist, maybe they are weak. That's what the current kind of understanding is, that they are not very bright. They has to be extremely weak. So the future facility like SK and NGVLA will probably help us push this limit down further. And if we are going to explore them, then we have to discover a whole new way of doing our searches. So traditional way doesn't work, and we have to come up with a better way in which our entire search needs to be sort of AI-enabled technosignatures. We have to have AI-enabled search techniques, as well as we have to have the entire search being conducted by AI in real time. So we have Luigi Cruz also, who is in the audience, and there are current effort that's going on at the Allen Telescope Array in California, where we are trying to do the searches in real time using AI models. So ultimately, hopefully, in future, we'll be able to combine these strengths together and form a strong bond, which will help us answer this question, like can AI help us find extraterrestrial intelligence? And I'd like to end with a very maybe controversial point, but my thought is that yes, only AI will help us find extraterrestrial intelligence. Thank you very much.
Thank you to all of our speakers in this session. I think let's just give them one more round of applause. They were really fantastic. So we are just a couple of minutes behind schedule, but we are going to stay on time, so lunch will just be slightly shorter than on the program, but we're going to be back here at 1 o'clock sharp for the discussion, so think up your questions. It's going to be really fantastic. Thank you so much.
slides up. If
Honestly, I don't know if
there's a relevant question, I might have an extra slide in my
I feel
deck.
like I was the best thing,
But they may not
ever.
be.
I kind of wish I didn't because like now I know how good it is.
Yeah, now I'm looking at the price every time.
Yeah.
Like, what?
Like, we even built up those airline miles, you know.
Okay guys, so we first have a little quiz with the audience that I'll just run, and then I'll be asking questions.
We're working on it.
Thanks. And then we'll go to the audience, and I'll probably come back around.
Okay, heard a sudden hush. We must be time to start. Thanks everybody for coming back. I hope you had a great lunch. So we now have this very cool discussion session. So this is after all Breakthrough Discuss. And we're going to kick off with asking you some questions. So we have a fun little interactive poll, some questions contributed by a few of us. And so if you scan that QR code, I see a lot of people are already in with cute little animal faces. So if you scan the QR code, or if you go onto Kahoot, you can put in the PIN. And let's see, we've got about 45 people on. So let's give it one more second. Okay, Dylan, I think we can go to the first question if the instructions stay on the slides. No, they don't. Okay. All right, we're going to go for it anyway with whoever we've got online. All right, so the first question, if AI or ET is discovered, is it going to be running Linux, Windows, Apple, or Android? Let's see what the votes come in. Oh, there we go. If you missed it, the instructions are at the bottom. So if you go to Kahoot, kahoot.it, you can put in the PIN and instructions at the bottom. We've already got 55 answers. I use Linux, by the way. All you Apple users. I don't know if that makes me an alien. Probably makes me an anomaly. None of the above. Yeah, I mean, probably. I mean, we can barely get our own systems to talk to each other. Imagine trying to talk to aliens. Okay. Can we skip to the reveal of the answers? Or we just wait 5 seconds? Let's see. Dun-dun-dun. Ah!
Linux.
Are you saying I'm an alien? Brilliant. Okay, here's the next question, slightly more serious. Is artificial general intelligence possible? So if you don't know what this term means, it means an AI that is as intelligent or more intelligent than a human. And I've specifically made this not a nuanced question. You have to either say yes or no. I mean, hint, it is probably a bit more nuanced than yes or no. Is there some fundamental reason that it would be impossible to have truly genuine, general intelligence that's artificial? Fifteen more seconds. We've got, I think everybody's answered, so we could, I don't know if we can skip. It's, okay. 4, 3, 2, 1, let's see. Interesting. Pretty divided. Most people say yes, but a very substantial fraction say no. We could never have truth. That's probably mostly people who've interacted a lot with ChatGPT. Tried to get it to write code for them. All right, last question. When we detect the very first technosignature, will its origin be artificial or biological?
What does that mean?
What I mean is, will we be talking to biological organisms like ourselves, or will we be talking to an entire race of intelligent robots that have superseded their biological origins? If you answered no to the first question, I'm pretty sure you can't put artificial in this one. Okay, 15 more seconds. I think everybody has probably answered. After this, I'm going to ask some of the panelists what they think. Wow, that's quite a split. 50-50. Very interesting. Okay, that's the end of our audience quiz. Thank you all very much for participating. I'm going to open the discussion by asking our panelists whether they think the first technosignature will be biological or artificial. Yeah, thanks, Dylan. We can take it off if possible. And I think leading on to this, is artificial general intelligence possible? And I think the first person I'm going to ask their opinion is Guillermo. What do you think?
Okay, so first, thinking about the signature that we're going to get out from space, if it's going to be artificial or biological. First, I don't think I mean, it could be artificial, but not necessarily general artificial intelligence, in the sense that to have something like general artificial intelligence, we're assuming that there's something like a human in another planet, right? And that general artificial intelligence should be able to do everything that we as humans do, right? So maybe it's more into your field, but maybe we can have other type of life that it's not similar to humans. Can that be possible?
Yeah, what do you think, Vishal?
So I think if you ask me this question the other way, like whether we will detect biosignature first or technosignature, I think this can be answered in a slightly better way. I feel that we will detect technosignature first for following reasons. First of all, technosignatures are going to be longer lasting than biosignature. They are going to be much more common, and they're going to be much more spread out than biosignature. Biosignature will be limited to a planet, while technosignature don't necessarily need to be sort of associated with a planet. It could be anywhere. So extending on that, if you ask this question whether the technosignature we will detect will have origin from biology or from artificial intelligence, I would have to go with the artificial intelligence.
Interesting. Anyone else have any thoughts on it? Yeah, go ahead, Paul.
Maybe, since we're choosing which question to answer, I'm going to answer the question around the general intelligence. And it seems that human intelligence is such a multi-faceted, multi-kind of featured thing. And if we were plotting human intelligence from all those different facets that are encompassed by human intelligence, it would be quite a complicated, multi-dimensional map. So it definitely feels possible that general intelligence, computer general intelligence, could fit in somewhere within that map.
Is there anyone on the panel who fundamentally believes it's impossible to develop artificial general intelligence? All right, there we have it. Problem solved.
But that doesn't mean that we all agree that it's possible to create it.
Okay.
I think these are the questions for the computer science people. They may be able to answer this in a better way.
Yeah. Yeah, I mean, you have to ask yourself, if there is a fundamental reason why this is impossible, why? What is it about the human brain that could not possibly be replicated? I think it doesn't necessarily mean the direction we're currently going with AI is necessarily going to lead to AGI. Maybe we need something very different. But personally, I don't think there's a reason that it would be. There's no way we could replicate a brain or some more advanced version of it. Okay. Let me ground us back into maybe a slightly more familiar territory as scientists. Most of our machine learning methodology is developed in industry, but there are certain aspects of that are pretty unique to astronomy or other types of sciences. Specifically, we have to deal with low signal to noise, and we have to deal with uncertainties, which are maybe not necessarily problems that industry faces canonically in developing machine learning algorithms. So what should we be doing to adapt our machine learning algorithms to handle these? And I'd like to punt this one to Ashley.
I guess can I clarify the question? Is the question, how do you think we should best think about
is uncertain.
Yeah, what needs to be adapted from kind of the standard, if anything, from standard machine learning algorithms for the types of data that we have to deal with, which are generally noisy. We often worry about uncertainties and need to quantify uncertainties.
Yeah, definitely. I think I'm going to not really answer your question, but I will say some thoughts that are related.
That is your right.
The first is that I think one thing, so culturally speaking, in astronomy, we live in what we call this Bayesian world, which is just to say, like, we actually try to input, we try to quantify our prior information, our scientific knowledge, and our physical laws into what we're doing. And behind the scenes, like, we do that across every subdomain of astrophysics, and that has been true in machine learning, or it's moving towards that in machine learning. We very much would like to quantify this notion of, is this a calibrated statistic coming out? I said this is an anomaly with some, like, weird metric I've measured. What does that actually mean? How do I know whether or not I need to spend my time on it tonight? And a way to think about that is, what's the probability I can find something exciting? That's really, really difficult, and it actually doesn't quite mesh well with this very Bayesian framework that we've set up, and it also doesn't mesh well with typically out-of-the-box algorithms. Don't account for these types of uncertainties because they're not so important when you're in this really data-rich environment. And all that being said, too, I brought up Bayesian because we explicitly, like I said, put in our biases, our known physics. That's something we want as astronomers. If you're looking for the unknown unknowns, sometimes that's not what you want. You might actually be preventing yourself from finding this by incorporating those uncertainties. The last thing I want to just mention is where it also does become important for us, but then has much larger implications, is because we're doing anomaly detection, we actually care a lot about, like, the tail ends of distributions. And that is exactly where these algorithms fail. There's many really upsetting examples of this across the board where you try to get information from an algorithm and you end up basically getting out the mean of that algorithm. A really, like, famous example from quite a few years ago is reconstructing faces and putting in a picture of someone who's clearly Obama and then getting out a picture who's clearly a white man. And, like, you know, that has a lot of implications. For us, mathematically, and looking for new phenomena, the implication is just that we often default to the first order moment, or, like, the mean of our distribution. That's not what we want in this case. And so there's a lot we have to think very carefully about as domain scientists.
Oh, thanks, Ashley. Dan, do you have any thoughts on this? I know you've thought quite a lot about these topics.
I think as scientists, if you want to build trust in your models, you have to have really good uncertainties. You know, people won't believe your models. If you don't have reliable, robust uncertainties at the end of it, then that feels almost unscientific. And so I think this is particularly true for science models, which is very different to the problems you face in industry, where when you take a picture of a cat, you don't really care about the uncertainty of every pixel in that cat. But when you take a picture of a galaxy, you certainly do. Or you have a spectrum, you certainly do care about the uncertainties of each of these things. And so you want to be able to quantify this, and you want to be able to make sure that those uncertainties are robust and can be flowed down to downstream tasks. And so having a distribution that represents every prediction, I think is really, really important. But then you've got the trap of, if your distribution is, you know, you assume it to be Gaussian, and it's not Gaussian, or it's not normal, a bell curve, for those not too familiar with that term, then you'll have the problem that, you know, if you're looking for the tails of the distribution or things that are further out, you might not be able to model those things as well as you might otherwise. So it's a double-edged sword that we need uncertainties for people to trust us, but sometimes those uncertainties and those distributions aren't well described.
We don't want to over-specify the model. A kind of follow-on question from this is, are there any other aspects or problems that are unique in astronomy or related fields compared to other fields that use AI? Yeah, Guillermo, if you want to go.
So following up on the previous question and related to this one, I think that one thing that happens in astronomy is that we don't get access to the real thing, to the ground truth. For example, if I'm classifying between cats and dogs, I can grab a dog and pet him or whatever. I know this is a dog, right? I can sequence its gene. I can do stuff, right? In astronomy, the things are too far away, right? So I won't be able to get access to the thing, to the object of study. I cannot get access to the galaxy itself, to the star itself. And that means that all the models that we create are biased because of that, because we don't have the ground truth. I remember in a paper we wrote a couple of years ago, we found a spheroid galaxy, an elliptical galaxy, that it was kind of weird, but we looked at the data from SDSS, and it was clearly a spheroid galaxy. But then we got to HST, and we could see the spiral arms, right? So because of the quality of the data, we weren't, as humans, being able to classify it correctly. And this was, we found it in Galaxy Zoo, and 100% of the people said this was an elliptical galaxy. Everyone said it.
Interesting. Does anyone else have thoughts to add? Problems that astronomy faces that are quite unique? Paul, do you have some ideas?
I really like that point, Guillermo. And I was going to say that at a cosmology level, it's even worse, the situation, because there's only one universe. So we're reliant on the data, observations of that single universe, and a whole bunch of simulations, essentially. So yeah, I can completely agree with you.
So a follow-on question, especially talking about uncertainties. There's a famous, of course, Carl Sagan quote that extraordinary claims require extraordinary evidence. I wonder how many times people in the SETI community hear this quote. But it's true. And more broadly, not just the detection of a technosignature, which would require an extraordinary amount of evidence, but just in anomaly detection, when we actually make these kinds of discoveries, naturally scientists are skeptical. So what kind of evidence would it take to convince the community that we have actually detected a technosignature, or very similarly, we've detected some completely new class of object? How do we actually support our claims made by, when these discoveries are made by machine learning? Let me start with Vishal.
Yeah, so in the technosignature community, although it's a bit controversial, but they have devised a metric called a Rio scale. Now, Rio scale is a sort of a quantifying way of identifying or putting quantity on any detection that you make. And there are various uncertainty in there, obviously, because you don't know a lot about your detection, and those factors really can put your Rio scale from anywhere from, so the Rio scale goes from like 0 to 10. 0 means it's totally uninteresting, 10 means that a UFO landing on like a White House lawn. You can think of that way, right? It's like a direct evidence that you can verify. It's up to that level. So it has a long range, right? So when we make or when we potentially will make a technosignature detection, it will be somewhere in the middle, obviously. So in order to quantify that, it's going to be very challenging. I can tell you example from like radio technosignature searches. It's a long process that will happen if we ever make a detection. It needs to be followed up by multiple observatories. Signal needs to be present all the time. If it's intermittent, like a transient, then we will have no way of verifying. Like, for example, like wow signal. Wow signal was just detected once, although we detect similar signals all the time, but it never seemed to repeat, right? So we have no way of verifying it. So there are certain criteria. This is an example, but like certain criteria that it needs to sort of go through in order for us to say with confidence that it is real.
Anyone have something to add? Dan, do you have thoughts?
I think I think Madhu might be more familiar with this, but it's in the biosignature, when you do detect a telltale signal of a chemical, it's hard to get people to trust you that this is the smoking gun, right? Even if there is no other way you know that this is produced on Earth other than artificially, it might not be enough. And this is why I feel technosignatures might be a better approach, because as long as you get some repeating signal that, if an alien started shooting Morse code at us, I feel like that would be that'd be a pretty good
If an alien started saying, hey, we use Linux, that would be pretty good, pretty strong evidence. All right. Any other thoughts on that? I definitely have other questions, but I feel like this might be a good moment to open up to the floor and just allow any questions from the audience, either for specific speakers, in which case maybe direct your question, or to the entire panel. And I think we're going to throw cubes at you. So, you might want to duck. Thanks, Rod. Any questions? All right, who's got the first question? Let's do the one in front. Yeah.
Cash the box. My question is for Paul. Since I was surprised by the manifold approach, as an observer, so someone who tries to have the best possible data, the spectrum taken in matrix in order to have the best possible quality of the data, I was surprised when you said that you have somehow to downgrade the data to do the manifold, to select outliers and whatever. And so I wonder why we do such an effort, technological, data analysis, whatever, to get multidimensional data that if they are not used or useful.
So that's a great question. And maybe there was a point that I didn't stress highly enough, maybe towards the beginning of the talk, that one of the things, I guess, that's driving this sort of approach is the sheer volume of data we've got. So it's an oft-used phrase, we're living in a golden age of astronomical spectra and astronomical data. But I've got a lot of collaborators within DESI who are perhaps, say, experts in tidal disruption events, I think those were mentioned a couple of times, or quasars, borderline quasars, who go through and they actually look at each and every spectrum. And they, as you say, I mean, that's the kind of the ideal, that you've got time to look at each spectrum, you've got your full, the full sort of experience that you've got as an astronomer in that subject matter area. And so you're not losing any information, you're looking at all the data. The problem comes when, as I say, we've got 40 million spectra in DESI, and then we're going to have orders of magnitude more than that in some of the other observation types that we've got. And there, you simply can't use visual inspection for that whole data set. And so you've got to have some way of getting to what you think will be, and curating what you think will be an interesting subset, and then eventually getting a human in the loop, doing some visual inspection on that. So that's what some of these dimensionality reduction techniques try and do, some of the unsupervised methods try and do. They try and just give you that set or that short list of data that we think, those are probably good ones to look at. But what people then look at is they look at the full, they'll look at the full spectrum. And then, with techniques like Astronomy, which are so good at then curating those maybe 1,000 spectra that you've got, if you tell it that you're really interested in black holes or tidal disruption events, it will try and you show it what those look like, it will say, okay, and so why don't you particularly focus on these top 50? So your point is really, really well made. If you had all the time in the world with lots and lots of people, yeah, you'd look at the data in its full glory.
Thanks for the great answer, Paul. Next question. There's one over there. Just before you ask it, the question after this, I would love to come from a student or postdoc. So young people in the room start thinking of questions. Go ahead.
Okay. Yeah, so we heard a lot about anomaly detection, but not a lot about exoplanets. With exoplanets, our problem is not so much excessive masses of data, but we have a time series for each planet. We have a time series of spectra combined from the star and the planet, and we're trying to infer from that fairly high-dimensional structure, the 2D, 3D, and maybe even 3D chemical composition and temperature structure. The workhorse for a long time has been Monte Carlo Markov chain and Bayesian inference, but I have to believe that modern machine learning techniques could help our retrieval. And I was wondering if there are any thoughts about how machine learning could help us get beyond Monte Carlo Markov chain.
Great question. Anyone want to tackle exoplanets?
I mean, from the technosignature side of things, I can mention that if you want to look for anomalies in exoplanet searches, there is also a case for technosignature. For example, incomplete Dyson sphere are a good example of producing anomalous light curves. This has been observed. I mean, we have one case where we thought it is a megastructure like the Tabby star. And similar searches are ongoing. There are a couple of papers where people have actually used anomaly detection techniques in order to look at all the light curves of TESS data, all the light curves of the Kepler data. And they have in fact trained the model based on completely non-spherical objects passing in front of the star. So what kind of light curve, what kind of dips those objects will create, and you can train a model from that as well. So yes, that work is sort of ongoing for technosignature side of things.
Dan, do you want to say something?
Yeah. So I mean, back to the question of whether MCMC, the Markov chain Monte Carlo, is there anything after that? One problem with these retrieval methods is that it's highly dependent on the chemicals that you input at the start. So you have to predefine what chemicals you believe are in the spectrum, and then your MCMC will go through and search that parameter space. And so it feels like, you know, if there was a technosignature there, or if there was some other chemical or some sort of unknown phenomena going on, it would be much harder to find that using standard approaches. And so we have a lot of machine learning techniques, such as simulation-based inference, that can search a lot larger parameter space a lot faster, and it might enable you to actually input various different parameters in there, or various different molecules in there that can search this at least a lot faster. And the benefit of being faster is that you can search a wider parameter space.
Thanks, Anne. Okay, where's my question from a junior person? Got one there. I've got lots, great.
How do we navigate situations where one research field's desire to apply AI to their work might hamper the goals of other fields? As an example of this, it seems in order to improve multimodal foundation models in geospatial intelligence, we may need larger amounts of higher quality data, which might involve launching more satellites into space. However, as we heard from Vishal, this could lead to more radio interference, which could make it more challenging to search for technosignatures using AI.
If you want to make an astronomer cry, remind us about all the satellite constellations that we have to figure out how to deal with. Great question. Who wants to tackle this? Everyone's like, nope, not me. Ashley, what are your thoughts?
Okay. Sorry. No, I mean, I think it's really challenging as a deep philosophical question. A different way of saying this is a lot of these very large models, honestly not astronomy, we're not the big offender here, but they take up a lot of energy. And what cost is that to us? I don't know. It's challenging to say, and it really isn't a great answer. There's no one decision of what is the most worthwhile scientific question out there to be asking.
Anyone want to add? You look like you want to add something.
Well, again, yeah, brilliant question. That was a very good answer, I thought. I guess as these issues become more in the mainstream, and as you say, especially in terms of the resource, or the consumption in lots of different ways of these different models and these different fields becomes more important, then I guess naturally, like it or not, they'll probably be of more interest to maybe governmental organizations who tend to dictate and how priorities and resources are balanced against each other. So,
I agree with that. I definitely think that there can be an issue of policymakers not necessarily talking to each other. So satellites are a good example. The US government and countries around the world are putting in something like $1 billion into the Vera C. Rubin Observatory, and many science cases are very heavily impacted by the satellites that are also allowed to launch by the same organization. So there is definitely a level of policy that discussions that maybe aren't happening. Great. Okay, where's my next question? There we go.
So for everybody who's not neck deep in AI at the moment, you'd be forgiven for thinking that after the discussions here, that there's a lot of time series models out there. And I see some smiles up there because, yeah, there are not. Really, when you're talking about foundation models, there's large language models, we have large video models, we have large audio models. So maybe, Alexis, this might be a question for you as well, is where are the large time series models? Are they coming? Are people working on them? And then, finally, for those of you who are in the research community, are you actively collaborating on creating some of these models? At MIT, obviously, you've put one together as a kind of a foundation model. So are you looking to expand that, involve other people to collaborate, create, I would say not sell, because you're all in the open source community. But is there any talk about doing that so that we can actually advance time series foundation models?
Great question. Alexis, do you want to comment of why there aren't any time series foundation models? Do you want to grab?
Hello. Yeah, it's a good question. I guess the one thing in terms of time series that comes to mind to me is audio. People are actively working a lot on very large models for audio understanding, generation, music generation. So these things are happening. So in terms of open source, like I'm not sure. What I can tell you, like me personally, for the work around sustainability and these models, we do hope, and a lot of these models are open source. So for example, the largest weather model, GraphCast, is open source. So specifically things around sustainability conservation, at least for Google, and I think a lot of other, like Meta and stuff, they do try to open source these models. But it's still hard to, even if you open source the model, it may be very difficult for somebody else to reproduce those results. It's very expensive to do that.
Does anyone want to comment? Yeah, Ashley, you want to? Collaborating on foundation models as well.
Oh, no, I don't believe in time series foundation models.
You don't, wow, a controversial statement. Right, let's go. Why don't you believe in time series foundation models?
I think time series are particularly challenging in a way that images truly aren't. I think audio is a good example of like, yeah, that's fair. There's a sense in which, oh, so sorry. There's a sense to me in which audio, very similar to images, it's almost like conditioned or has this very strong prior in its structure. The way I'm speaking has a very cadence that you're used to. I don't do things like suddenly have chaotic behavior, and I mean that mathematically chaotic. I'm coming from a stochastic process. And that's true in time series. There's so much interesting behavior, and then in the astro world, it's multivariate, meaning there's different signals coming in, but the signals are correlated with each other, and also they're not coming in at an even time. I get them randomly. There's so much more going on, to me, than in images. And so that's why, partially, I think we're so far off from a foundational time series model that I don't believe in it right now. I think it's not the direction to be thinking about.
Okay, who wants to fight back on that? Everyone, everyone! Go ahead, Guillermo.
Okay, so I kind of agree, but not completely. All right?
No, you're supposed to have a fight.
So you're right. If you think about a time series foundation model, like a general time series foundation model, it's going to be really hard, but you can still build it, right? I mean, if you had the data and you want your model to follow the distribution of the data, then you may get it, which is what we do with language, right? We're following the distribution of the data that comes into the model. In the case of astronomy, we built a foundation model, which is Astronomy, but it's limited, again, to the distribution of the data that was built on, right? So that means that, for example, if you switch the cadence, the model changes completely, right? So then you have to think about how you encode the time into the time series model. And that makes a huge difference, right? And, but again, once you switch that, even if you do that, the model will still follow the data, the distribution of the data you're feeding into it. But if we grab all the data from all the time series that we have in the world, we could build a time series model, right?
But that exists, and it's very bad. Like time GPT exists, and it's really bad. Gaussian processes can easily outperform a lot of their baseline metrics.
Right, but that's because the distribution is too complex, right?
Yes.
Right, but if, sorry, I was thinking about light curves, sorry.
Okay, that's fair.
So in terms of light curves, I think it's not that complex.
But what makes foundation models really good is massive compute. And I don't know if there's many companies out there, even DeepMind or OpenAI, who are putting that much effort into massive compute for time series data. And the ones that probably are would be the hedge funds. But we don't know what's going on inside there. Maybe you do.
He's like, I'm out of that world.
And so I don't think it's impossible. I think it's just we haven't put enough effort into it. And I think astronomical time series are particularly challenging because we have a lot of missing data gaps. We have multi-channels that have partial observations in each of them. So it's a much tougher problem for our data set. But things like audio, yes, they're stochastic, but they do have or like stock markets, they do have long duration trends. And if you go to the right frequency, the right range, then yeah, you totally get trends. On short timescales, for sure, but that's also true with images.
Yeah, but I mean, I think to follow on with Ashley's point, that one of the complexities of this problem is the sheer range of timescales we're interested in that something could be anomalous on, right? It's everything from milliseconds to years. And that is not really an issue we have with images, right? We don't have fractal images where you can be interested in these 2 pixels as well as the whole thing. There is hierarchy, but it's nowhere near the level with time series. So it is a very challenging problem.
But does it always have to be one-dimensional? When you are, for example, looking at the time series data, there are other metric or other streams of data that you can also correlate with that and try and make your prediction better. Supposed to kind of do it that way.
You're talking about like combining image data and spectra. Yeah, these are the multimodal kind of foundation models.
Data as well, like, yeah.
When that's available, which is not often. Great question. Sparked a lot of discussion. Next question, yes.
My question is for Guillermo. You introduce alerts as a very flexible system, and I remember your slide about the classification of AGN, buzzwords, something like that. My question is about, because we have more than 10,000 unclassified exoplanets. Well, the question is, could your alerts used to try to classify exoplanet, because usually we have 3, maximum 4 parameters, no more, excluding the black dot of the planet, of course. Could your system be useful for such research or not?
So I would say the system as is right now, it's not built for that, all right? But all the techniques behind the system itself, they can be applied to planets or to whatever data stream you have. At some point, we talked in the team about building a version of Alersi for planets, for exoplanets. But we decided not to follow that route because it was a lot of work, right, to build the whole system. Now, the algorithms are not that hard to build, but the problem that's really challenging is starting from the algorithm that you created for the paper, putting that into production so that it works on a real alert stream. That's a lot of work. That's a lot of work. It usually takes us around 3 months since we get the model, between 3 and 6 months since we get the model, until we put it into production and we do all the sanity checks on what the system is doing. So building a system for something different, like the whole system, would be really challenging. Building the model should not be that hard.
Okay.
Vishal, let's just do one more.
I think we're actually going to have to close the panel. Okay. I'm sorry, everybody. We're actually already eating into coffee time. But I want to ask one final question of our panel before we close, which is basically, what is the future? What are the techniques that you're the most excited about? Where is the field going? I'm not going to ask each and every one of you. I'm going to ask the one who looks the most excited to answer the question, which is, I don't know, who's the most excited? I think it looks like Paul.
Oh, okay. I was trying not to catch your eye, actually. My approximation, my first approximation to excitement. Where's it going? Well, I think maybe looping back to the first question, or one of the first things we talked about in terms of general intelligence. There's so much that we've seen in astronomy, I guess, from everybody's interest in ChatGPT and large language models. Even if we're not necessarily specifically using large language models in astronomy, we're using a lot of the tech from it. So the attention mechanism and transformers and so on are being used in it. So I guess that's the way things seem to be going, you know, to try and push towards general intelligence, whether it, you know, is possible or not. I mean, I guess we think it is, but well, whatever. But, you know, so I reckon there'll probably be a lot of collateral developments that will come from that we will be using. Again, whether we're using general intelligence or not specifically, I reckon there'll be a lot of spin-offs that we will be using in our day-to-day work.
That's great. Anyone else have something to add? Vishal, what are your thoughts?
I mean, I can't really comment much about like how the AI is going to, like what new techniques are going to come in AI, but I can comment from this side of like techno-signature field. And I can say that is sort of mind-boggling the way we are able to conduct the searches right now and what future holds for us in the next 5 to 10 years. The new facility is going to generate data. I mean, you talk about terabytes a night. We are already generating several hundreds of terabytes in an hour, in fact, at radio facilities, right? So that's an enormous amount of data that comes in. And we definitely need something that can work in real time to make inferences and basically allow us to do this processing much more faster, because we talked about this Bayesian approach, right? We don't know the probability of life. We don't know whether the evidence we will get will suggest there is life. But the middle probability in the Bayesian thing is that how well you understand your experiment so that anytime you make a detection, you can say with certainty whether that detection is real or not. And that will depend on making more observations by collecting more data, and that is only possible through AI.
So AI meets giant surveys, and it's never been a better time to start looking for techno-signatures. So with that, I'd like to thank all of our speakers again for a very interesting panel. And thank you very much to the audience for all of your participation, and please enjoy our 20-minute coffee break. I think so.
Okay, right. One, two, three, four. One, yeah.
I still don't have a mic. I can't be heard.
I showed up and we're like, do we have it?
I don't have a mic.
Oh, you don't?
I have a mic. It's not
Your
working.
mom?
Yeah, I'm speaking, but I hear nothing. I'm speaking, but I hear nothing. I'm speaking. Okay, you know what? It needs to be further up. Thank you. All right. But we have her back? Okay. Okay, darling. Thank you. All right. Showtime. All right, folks, if you could settle down. We're about to overcome several technical difficulties, and now we have, and we will start our session. Session number 2, strand number 2. And this has to do with life as we know it on Earth and beyond. And we've accumulated a wonderful potpourri of speakers to really cover at least the corners of the breadth of this enormous field. Without further ado, since we had a few technical difficulties, I want to introduce our first speaker. Dr. Bethany Theiling is a friend and colleague of mine, also works at NASA Goddard, and she is working on how to use AI for astrobiological purposes on real missions. And those of us in astrobiology, that's one of our prime targets is how do we have assistance to go to other planets? Bethany's area of focus, of course, is the outer icy bodies and the potential for life there. So Bethany, if you're on, let me turn it over to you.
All right, thanks, Benny. And I think if you all can do it, then it won't back into my ear. That'd be great. All right, hopefully that works. Yeah, thank you so much. First of all, I wanted to thank you. Thanks to the IT group and the AV group for setting this up, and I really appreciated that this was a challenge. So I really appreciate you guys working with me so that I can actually present today. And thanks to the organizers for inviting me. I'm very, very sad that I wasn't able to physically be there, but I'm really excited to be able to present this work to you all. This is pretty much hot off the presses. We've been doing this for a few years kind of in quiet while we got this going. And so I'm gonna basically kind of guide you all through the process that we've taken to kind of get here. And really the goal here is that we're trying to develop actually one of the panelists in the previous panel was discussing this. There's a lot of this like model development, but then how do we use those models? And so basically we're trying to create the framework that would enable people to use whatever bespoke model you have through an artificial intelligence framework. And particularly we're trying to do this on board. So again, my name is Bethany Theiling. I'm a research scientist at NASA Goddard Space Flight Center. And I'm here right outside of Washington, D.C. It's just after 10 a.m. Let me get my timer going just so that I can have a sanity check here. All right. So the agenda for today, I've got a lot to go over. So I kind of want you to see where I'm going. So why do we want this at all is the first thing. I'll kind of talk about the case study that we used for this, and as Penny mentioned, my primary focus is on icy ocean worlds, such as Europa and Enceladus. Then I'll go into the demonstration. So this is it's a pre-recorded demonstration of how the AI works, but I'll walk you through it. We did this because it would just take a lot of time, and I don't have too much time to share with you. And then I'll talk briefly about how you could implement this into your workflow and your mission. And then what are we working on now and future plans. So why do we want to onboard AI for ocean worlds and astrobiology specifically? So this morning, sorry, I guess for you guys it's this afternoon by this point, we've been talking, and I heard a lot of great talks this morning about how you can use this for data-rich experiences. Well, for planetary science in general, and certainly for the astrobiology community, we don't have a lot of data to work with. And so there's a few challenges that we need to kind of overcome. And so hopefully you guys can see this thing at the top here. So we have the challenges for outer solar system missions, which are the ones that I'm really focused on, have to do a lot with latency. How do we talk to our spacecraft? And so, this is just a model of the solar system. You didn't notice I left Pluto off of this. You're here, at least I think that's where everybody is today. I don't know where everybody else is joining us. And so I think about a lot about the moons of Jupiter and Saturn. And so even to get to Jupiter, it takes just the speed of light. It'll take you about 35 minutes to send a message to Jupiter. If we get to Saturn, it's getting around 1.2 hours. And of course, this gets worse and worse as you go into the outer solar system. The real challenge here is not just that delay, but then you have to, on top of that, think about where's the position of the spacecraft relative to Earth, or relative to some sort of relay station. We don't have a lot of those assets out in the solar system. NASA is trying those sorts of things out. But this is a real challenge. So, and I'm just giving I'm going to pick on Europa a little bit because I know a lot about Europa. But for the flyby mission that's coming up, the Europa Clipper mission that's going to launch in October, I'm so excited. It's about 8 hours to have a message that comes one way. And this is a flyby mission. Now, if you were to land on the surface of Europa, it could be upwards of 43 hours, depending on where the position of the moon is relative to Jupiter and Earth. And of course the sun, so it could be on the other side, actually. So this is a huge challenge. So if you think about, it takes a long time to get out there, it takes a long time to communicate, we don't have the ability to sort of redirect in real time. And you add to that the challenges, and I think many of our scientific colleagues that I'm sure are in the room or online, we have this challenge of when we get the data back, it takes a while to think about that data, to process it, and to actually consider what it means. But if we're thinking about an astrobiological detection, a life detection, the real challenge to me, and the thing that I would not want to miss out on, is what if we saw something that could be life, and that was our only opportunity? Just because that's how luck works sometimes. And I think one of the talks this morning was talking about, or this afternoon was talking about this like we learn a lot of things that we didn't know before. And so we want to make sure that we take advantage of being out there. And that's really where AI can help. So, and I'm going to focus kind of on the icy ocean worlds and biosignatures here. So I want to give you this view, and maybe some of you have seen these pictures of the surface of Europa. Maybe you haven't. Maybe this is the first time you've ever seen this. But one of the things I think about, and I'm going to use hopefully you guys can see my cursor, these bands here, these cracks in the surface, and this section over here is called chaos terrain. So these are overturned blocks, and these are actually like flexure points that we think actually opened up. Some of these are actually subducting, similar to Earth's tectonic plates. And so this is an actively tectonic system. It's ice, so it's all ice. This is not rock. But we've never observed this happening in the solar system. And so we've taken pictures of it, and we have evidence that it does happen. But what if we could be there? What if we could respond in real time? So if you start to see a flexure of that icy crust, in any direction using one of your instruments, even a magnetometer, as one of the participants put up this morning. What if you could respond to that? The other thing is that, especially in Europa, we don't know if there are active plumes. There's a lot of work that suggests that there could be plumes, but other people do not agree. This is actually some recent detections by JWST. This is the James Webb Space Telescope. This is not a plume, but it is carbon dioxide ice that's on the surface of Europa. So this kind of lends credence to this idea that maybe there are like volatiles that are being ejected into space, similar to Enceladus. So how could you react to that in real time? I think you'd have to have AI. And then, of course, the most exciting one, I think, to many people is could you react to a potential biosignature? So if you saw something that was interesting, and this goes into the anomaly detection, it's been a lot of the conversation today, could you respond to it? And then I like to put this up here because sometimes we don't know what we don't know until we're presented with something new. And so I call this opportunistic science. So how would we be able to, again, respond to something that maybe we didn't know that we wanted to look for? We can plan all we want, but there's so many things that we learn once we're actually out there. So we actually worked on this case study. So basically, we built a lot of machine learning models, many kinds of machine learning models, and then I really started to push on this idea of, could we do something with them? Like, how do we get these on board? How do we do this? Can it be more than a tool for a scientist on the ground? Could it actually fly? And I've talked a lot about Europa already, so Europa's up here. And Enceladus is down here. We decided to focus on Enceladus because a lot of the mission priorities upcoming are on Enceladus. And I'm going to give a brief introduction to Enceladus. I don't want to steal Chris Glein's thunder. He's giving a talk next. He will talk probably a lot more about Enceladus. But this is a beautiful picture of the surface of Enceladus. So this is near the South Pole, and you can see that it's ejecting these particles out into space. So it's a lot of water. It's mostly water. Carbon dioxide, there's salt actually. So the composition so far seems to be very much like Earth's ocean. So it has sodium chloride and sodium bicarbonate. There's things like gases like methane and hydrogen, which is very exciting. I'm sure Chris is going to talk about it. Organics, which is also super exciting because organics, of course, are the building blocks of life, at least here on Earth. And then things like silica, which maybe Chris will talk about. That gives us evidence for hydrothermal processes happening at the seafloor. And just to give you a sense of scale here, because I think it's really important, Enceladus's plumes are enormous. And you can see here's Enceladus. This is actually a Cassini giving a long gaze backward. This is its last picture of Enceladus before it dove into Saturn. And you can see the plumes are ejecting upwards of 200 kilometers out to space. They're huge. And then Old Faithful, so this is one of the Earth's largest geyser. It's in Yellowstone National Park in the United States. And so you can see it's, maybe 0.6 kilometers. So these bars here, so this is just a scale. This is Enceladus's plume, and here's this teeny little dot, which is actually too big still to indicate the size difference in these things. So these are enormous. And we had the good fortune of being able to fly through them with the Cassini spacecraft. Cassini also was able to take a lot of data here. So you got these like warm bands. I'm going to say warm in quotes because, and I put these temperature estimates at the bottom here. So, negative 135 degrees Fahrenheit is probably the warmest, but this is the surface. This is not underneath the ice. And then about negative 330 degrees Fahrenheit out here, and you have Kelvin here as well. This image over here on the right-hand side is actually, these are the unique detections of plume activity, the unique sources of plume activity. As of 2008, there's been many, many of these. This was just a helpful diagram. And so from all this, we've been able to come up with this profile, this model of what the interior of Enceladus should look like. And you can see it has this ice shell. It's about 5 kilometers thick, give or take. There's a lot of work on estimating this, and people sort of range or vary on how they think, how the thickness of these. There's also these, what we think, and I think Chris will probably talk a little bit more about this, but we have evidence to support the idea that there are these rock-water interactions at the seafloor, and these are called white smokers, and that's based on the chemistry that we see in the plume. So this is just an example of these white smokers that we have here on Earth. And you can see it's a very, very deep ocean. So it's 65 kilometers thick, the ocean. That's very, very deep. And of course, we have these cracks that kind of go through the surface and be ejected here. Now, a lot of the work, again, that Chris Glein has done and his colleagues, they've suggested that there's enough chemical energy to support microbial life, which makes this a really exciting target. And this is one of the reasons why we decided to focus on it. So a lot of the work that I do and the group that I'm in here at NASA Goddard is in developing mass spectrometers for spaceflight. So I'm going to give you just a brief overview of how a mass spectrometer works so that at least you have a sense of like what kind of data I'm looking at. So the sample enters here. It actually gets, in whatever form, we usually try to make sure that it's a gas by the time it enters a mass spectrometer. They don't like water. They don't like salt either, turns out, which is going to be challenging later on. But basically, that gas enters into an ionization source. It ionizes, so it basically gets energetic, like it's an energetic particle or group of particles. Those particles are now accelerated. They interact with a magnet, and when they interact with that magnet, they actually get bent, and they separate out based on their weight. And so things that are very, very heavy can't get deflected as much, and so they are detected here, and these lighter mass ions get deflected a lot, and so they tend to be diverted a lot. So that's the basic idea of a mass spectrometer. I'm going to show you all, so these are, hopefully they will play. Go. It may not be working. That's too bad. So basically what I'm trying to show you guys here is these mass spectra that should be here. So you'll have the mass over charge on this axis and then the intensity on this y-axis here. I'm not entirely sure why they weren't showing. Everything worked up until apparently right now. But what you should be able to see is that there are these pretty distinct peaks here in each of these. And what I was hoping to show you is that these are very, very, very different, but also very simple, because these are one molecule, one kind of molecule. And so that tends to be pretty easy. And there's very easily, we can create machine learning models or even statistical models that show you the differences between those two things. We don't need a lot of intelligence for that. Now, things get more challenging when you have salt in it. And like I said, mass spectrometers don't really like salt. So here's the kind of spectra that you might see. And I really wanted you to see the simple spectra so that you could see what we start out with and then what we actually end up with. So this is just a solution that has sodium chloride, just like other solutions, in it. You can see that it tends to ionize in really weird ways. And then if you add organics into it, it gets really complicated. So this is the perfect kind of problem. Could we identify, so basically my group initially started several years ago working on, could we extract information from these really complicated spectra that could help us identify not only life versus non-life, but also just the chemistry of an ocean. So that's kind of what we worked on. So I'm just going to show you, like, this is the low-hanging fruit kind of work that we were like, we should start here, and then we've gotten a lot more complicated. So just to show you that kind of spectra again, this is a really simple version of it. So one of the things that would be super simple to implement, you don't need a machine learning model for this, would be things like the limit of detection or limit of quantification. And so could you actually say, all right, well, this is where I know that my instrument is actually making a detection and not just, noise. And now you have a feature, so maybe it's something interesting, or even you could set your threshold upwards to a novelty or an anomaly, as we heard earlier. Or is it something I've never ever seen before? So it could be that too. So basically, I'm so upset that none of my animations are shown. This is really, really upsetting, actually. Mostly because you won't be able to actually see anything work in real time. Let me just see if I can have it work here. Yes, it would be great. Cannot play media. Okay. Oh, that is really too bad. Okay. Well, we'll work with it anyway. So what you should be able to see is that there are 8 spacecraft that are orbiting Enceladus. And I want to be very clear, this is not a mission concept. So we wanted to come up with a very, very complicated scenario that would basically be impossible to work with. And so we had 8 small sats that were orbiting around Enceladus. I have it rotated so you can see the South Pole where those really cool cracks are that have the geysers. And so one of the things that we wanted is these cones here should be showing you that there are these, that at least you could view the South Pole even if you couldn't fly over it. So it's not a stable orbit to actually fly over the South Pole. And again, this would be a really great animation if it was actually working. I think Zoom doesn't like this for some reason. So here, what we decided to do, what we also really realized that we needed to do is model the communication pathways. Because if you're going to have an intelligent constellation that can respond to something in real time, then you need to figure out, well, when and how can the spacecraft communicate with each other? And so what you would be able to see if this was able to work is that you would see that those spacecraft are orbiting, and then how their communication pathways can change. So who can talk to who at any one moment. A lot of the data that we used are based on laboratory simulations. So the idea is that we know if there's these rock-water interactions with the seafloor, you should have these gases that are kind of moving through the system. We can measure them here very easily using those mass spectrometers. And so this is what those experiments look like. I made fake seawater. Sometimes I put microbes in them. And then we measured the CO2 that interacted with those microbes, or just the seawater. And we were able to create a lot of machine learning models. And again, I'm really sad that you guys can't see this. Basically, there's this console. I'm not sure how I'm going to deal with the next slide, but there's this console that we developed that it's using a platform called Redis. And so we have 3 consoles. So you have Spacecraft 2, we were just focusing on a smaller demonstration for you all. So Spacecraft 2, Spacecraft 1 is in here in the middle, and then the mothership. In this particular case, we decided to have some sort of like data relay system that can communicate back and forth. If this was able to work, then what you would see is that this is actually working in real time. And so this spacecraft was preparing to take a measurement. It started that measurement, and it's then communicating that back and forth between these. This is the one that's truly upsetting because it's really exciting to show all of you. But basically, if this was able to play, you'd see that we have, I think at this point, we have upwards of 30 machine learning models that have been inputted into this system. All of those models have to collaborate to come up with basically an opinion about what they think the data is. And so they're seeing this analysis in real time. They're able to talk about, like, basically communicate amongst themselves, all of those particular machine learning models, and then the consensus approach, or the majority agreement would be, hey, we think we found this, what should we do now? And so again, I'm very sorry to say that you guys can't see this. Just gonna see if there's any way that this will play. Let's just see. Oh, so upsetting. Okay, it just won't play at all. Okay. Yeah, but the exciting part about this is that we've actually demonstrated that using randomly generated, basically randomly called data from our data flow, so you can actually look and see, it seems to think that there's a particular probability that this is a biosignature, and because it was a pretty high probability, it was asking for follow-on analyses. And those follow-on analyses were then communicated to the mothership and back and forth between a couple of spacecraft. They came to a decision that they actually had the onboard resources and the time necessary to do that, and they redirected the spacecraft so that, or they repointed the spacecraft so that it could actually take a new measurement. And so this is the kind of technology that would really enable new missions. So I'll end with, I know I'm running out of time here, or out of time, so I'll end with, we built this as an entire system so that it should take in information about the spacecraft, about fault detection, about its navigation and guidance. It should be able to transfer systems, knowledge across systems. It should be able to manage its mission constraints, so you can hard code those things in. We're also building it so that these are modules, so that you could basically say, I don't have the onboard computing resources to do all of this, but I would like data prioritization, and that would be something that would be really helpful for my particular mission, or I would like the intelligent sensing and response. And so that's really how we're trying to work that through. So what are we working on now? Super quick. We're trying to make really more complicated decision-making, deploy it with hardware, and then conduct field tests. And so these are actually, these 2 guys over here on the right are my 2 summer interns. This is my graduate student, Lily, and then one of the CS professors at the University of Tulsa I work with. And they actually were doing this summer, so we're actually trying to build machine learning models out in the field in real time, which is really cool. And then hopefully we'll deploy in space very, very soon. So with that, thank you very much. And again, apologies that you all couldn't see all of those amazing videos. And I'm happy to stick around and answer some questions.
Thanks, Bethany. I'm going to cut our introductions brutally short, so if I can get Chris to come up here since we started about 15 minutes late. This is my friend and co-chair, Chris Glein, who is at Southwest Research Institute. He is a fan of the icy bodies. He was on the Cassini mission. He's on the upcoming Europa Clipper. And take it away, my friend. 18 minutes.
Thanks, Betty. I'm actually a fan of exploring outer space, not just icy bodies. All right, let's proceed, if this will work. Oh, there we go. Okay. Yeah, so today I'm going to talk about Saturn's moon Enceladus. I was really pleased to see that Bethany gave you all a sneak peek, and we'll really dive into Enceladus for this talk, and I'll discuss its importance in the search for life. But before getting there, maybe it goes without saying at a breakthrough meeting, we might want to ask ourselves, why is the search for life important? And I really think about this in two different ways. You know, there's kind of like the scientific answer to this question. We want to push the envelope of knowledge and ask ourselves, what is the role of life in the universe, or is life an inevitable outcome of the laws of chemistry and physics, where through science, we've learned to replace many of our origin stories with this new understanding of cosmic evolution, where you go, from the Big Bang, galaxies, stars, planets, and so forth. But as of right now, we only know on our planet that all of these processes have eventually culminated in life. And we like to know, is this common or maybe not? And then the second reason is more of the human side of things, or how we feel when we search for life. We feel excitement. We feel like we want to do something great. We heard this morning that we could be the first generation that's on the precipice of answering this question of whether or not we are alone in the universe. And what a gift for posterity that would be if we could answer that question. And then for me personally, there's just like the cool factor, right? So we are blessed to be given this opportunity to ask the big questions and to seek out life. And I'm a sci-fi geek here, so I really like that what I can do for my day job involves merging what we think could be possible with actual experiments to test what's possible. So space exploration has given us an embarrassment of riches. And many of you have probably heard of the candidates where we might go to look for life. These are kind of like the big five, where we have 4 objects in the solar system and then huge numbers of exoplanets to study. In today's talk, I love all planets and moons, so I'm not going to put down any planets or moons. I'm going to focus on Saturn's moon Enceladus for 2 reasons. One, it has this amazing story to tell us for astrobiology. And the second reason why I'm interested in Enceladus is it's kind of like an underdog. So I'm an American, I like sports, right? And so we're always rooting for the underdog. Who's going to beat the New England Patriots, that kind of thing. And Enceladus is kind of like the underdog in our exploration to search for life, where all these other objects got all these great missions, either already studying them or we're planning to send missions. But Enceladus so far has flown under the radar. So I'm going to let you in on a secret of what we can do. First, I'll tell you a little bit more about Enceladus. I know Bethany mentioned it. It's a small icy moon of Saturn. It's one of Saturn's 7 major moons. I love that I'm giving this talk in the UK, because this graphic is finally very relevant. This is actually 2 scale shown here, so it's a very tiny moon. Europa, you've probably heard of Europa, Jupiter's moon, is roughly the size of our moon. These are the big moons. Enceladus is just a baby. It's tiny, right? But it packs a punch, and we'll get into that in a little bit. It's a cold moon. It orbits Saturn. It's 1 billion miles from the sun. It's very cold on the surface, near the temperature of liquid nitrogen. And it's also the most reflective object we know of in the solar system. It's covered by very clean water ice. I guess we can just stare at Enceladus for a little longer. Oh, and that just took the complete wind out of my joke here. So Enceladus should not be confused by things that might sound like Enceladus. That was a fail, by the way. So you probably heard, hopefully, or if not, you're in for a real treat here. We had this mission called Cassini-Huygens. It was a joint collaboration between NASA and the European Space Agency, and it discovered some really fantastic things in the Saturn system. I would argue that the biggest discovery, the most intriguing and surprising thing we found was that this little moon of Saturn is erupting a plume into space. And Bethany showed you, you can see the plume going out 200 kilometers. It actually goes out a couple thousand kilometers into space. You can really see it from the James Webb Space Telescope. This plume is massive because the gravity is so feeble on Enceladus. And what's really significant about this feature is by finding it, we've learned that Enceladus is the smallest geologically active body in the solar system. For all intents and purposes, this body should not be active. It should just be a frozen ice cube, but it's not. And we've learned, we did a number of flybys with Cassini. The last one was in 2015. We flew the spacecraft actually through the plume. And we had different kinds of instruments collecting data, and some of the instruments, known as mass spectrometers, which could measure the chemistry of the plumes, revealed that the plumes taste salty. So, there's frozen ice particles, and those particles actually contain salts in them. And from that discovery, we were then able to piece together what we think is going on. And the punchline here is we think that the source of the plume is a global ocean of liquid water, thought to be about 40 kilometers deep. So it's about 10 times deeper than Earth's oceans are on average. Very spectacular. Maybe we just have operator error here. Oh, there we go, okay. So finding all this water created a lot of excitement among the scientific community because on Earth, wherever we find liquid water, we find life. And so the natural question is, could Enceladus be alive? And to get to the bottom of that question, what we tend to how we tend to organize our thoughts is around this question of habitability. And what habitability is it's the ability of this environment to support life, to provide the essential ingredients that life would need to sustain itself. And in really general terms, you can boil that down into liquid water, and we found that on Enceladus. It has an ocean, right? And then there's these other two requirements, a source of energy that life can use to power itself, and then the key building blocks like organic molecules and other key nutrients. And I'm going to spend some time now going into these questions we had about whether Enceladus could provide these things. We designed a flyby. This is just near the end of the Cassini mission, late in 2015. We flew through the plume, and we were surprised to find a very large abundance of hydrogen, H2 molecules, in the plume. So you can see, the flyby happened very quickly. Within about 30 seconds is when we collected all our data. So the spacecraft was screaming through the plume. And then right near closest approach, we detected a massive spike in the signal corresponding to H2. We estimate it's about 1% hydrogen in the plume. For those of you who are astronomers, maybe this isn't so interesting because H2 is the most abundant molecule in the universe. But on a small moon, it matters to find hydrogen because the gravity is too low. Enceladus cannot hang on to H2, so it must be actively produced in the interior. And we scratched our heads for a while to try to understand what could explain this. And this is the mechanism that we landed upon, shown in this graphic here, where I mentioned it's covered by bright ice on the surface. We have plume erupting. There's a deep ocean there. And then we were able to use the chemistry of this plume to peer down into this dark hidden world down there. And we think the chemistry is telling us that there is hydrothermal activity at the seafloor. This very small moon. We think the water is reacting with hot rock. I won't bore you to death with all the geochemistry, but through water rock reactions, hydrogen can be produced. And eventually supplied to the ocean, and we see it coming out from the plume. So we think that this moon has hydrothermal systems. And probably the bigger implication of this finding was, again, from our knowledge on Earth, we've learned that when we visit these hydrothermal systems, we're astounded to find that life is actually teeming outside of hydrothermal vents. And the reason for that is because molecules like hydrogen are able to act as fuel sources to power their metabolisms and provide sources of energy in the absence of sunlight. So you can see this is a really great example. This is an image near a hydrothermal system in the Caribbean Ocean where microbes feed on the hydrogen and then shrimp and other animals feed on the microbes, and you have a full-blown ecosystem. Could it be on Enceladus? So this is the only boring part of the presentation, hopefully. I'm going to just give you a little bit of an introduction to how geochemists think about these kinds of measurements, because we can actually dig a lot deeper than just saying hydrothermal vents. We're able to quantify how much energy is available in this mixture of molecules. And we do this using this variable called the chemical affinity for this reaction up here, where CO2 reacts with hydrogen to make methane. It's known as methanogenesis. It's a very important microbial metabolism. And we can actually use the data from Cassini to figure out, is the system close to equilibrium, which is not too interesting because that would correspond to death, or could there be a source of energy that could be exploited? Here's how much energy microbes need on the Earth. They need 10 to 20 kilojoules to keep on trucking. And here's what we learned when we pieced together all the data from Cassini. We're able to then pinpoint roughly how much energy might be available in this system, and it's shown by this cyan region right there. And notice, this is above that, right, coming from a scientist. We can easily see that. And what that means is that the energy supply is greater than the demands of life as we know it. So we would conclude that this environment is energetically habitable. And a good way to think of how much energy is available is I calculate, this is a very difficult calculation, it's the equivalent of about 300 cheese pizzas every hour that is coming out of the plume. Not too bad. So we think there's a source of energy. And then the last topic I want to touch upon is the essential elements. This is our most recent story. It's published last year. The question of phosphorus. Phosphorus, and this will be a great lead into Jane's talk, it's really important for life on Earth. And as far as we can tell, no other element can replace its role in biology. It serves a number of roles. Probably the one we're most familiar with is it's a building block for our bones. But within the biochemistry of our cells and for microorganisms, phosphorus is super important in allowing energy to be transferred between different molecules. A classic example is known as adenosine triphosphate, ATP. So it's important. It might also be a biosignature. And in Earth systems, like our ecosystems, phosphorus is often a limiting element that restricts microbial growth. And on Earth, normally phosphorus is rare. It puts a lid on microbial activity. And people originally thought that, by analogy, maybe phosphorus should be rare in other oceans, right? We weren't quite sure a couple years ago because we know that the chemistry of Enceladus' ocean is actually a little bit different from Earth's ocean. So rather than just say it should be like Earth, we thought we should make some models to try to understand what might be possible. And it's summarized by these figures shown here, where this was published a few years ago now, where we made predictions based on the geochemistry that we know of Enceladus' ocean, how much phosphorus we might expect based on water-rock reactions at the seafloor. And that's represented by these bands shown here. So this is the predicted concentrations of phosphorus. And here's Earth for reference. And one thing that really surprised us was, for most cases, it seems like the predicted levels are either comparable or even much larger than what we find in Earth's oceans. So this created some encouragement for us to, again, dig a little deeper. So what we did is we then started working with some colleagues in Germany. They did some great work analyzing a huge number of data from the Cassini mission, and we focused on Saturn's E-rings. This is a ghostly ring around Saturn. And it's important because it's coincident with the orbit of Enceladus. And we now know that the plume actually supplies the E-ring. So the E-ring is composed of lots of plume particles that have escaped from Enceladus and they've been trapped in orbit around Saturn. So in a way, if we sample the E-ring, we're able to sample what originally came out of Enceladus's ocean. It's a frozen reservoir of ocean water. And the team in Germany, led by Frank Postberg, they analyzed thousands of particles in the E-ring that were sampled by Cassini, and they found the needle in the haystack. This is an example of one of the spectra that were collected. This is a mass spectrum showing the masses of different species detected in the plume ice grains, and roughly they're abundant shown on the vertical axis, and you can see I've already simplified this by outlining this box shown here. These are new species that were seen for the first time, sodium phosphate species in the E-ring ice grains, showing that phosphate species are abundant in the plume. So that seemed to suggest that maybe we're on the right track with this model, and this is an environment that is rich in phosphorus. In fact, this is the first detection of phosphorus in an extraterrestrial ocean. And I got to tell you a little bit more about the chemistry, because I love chemistry. You might wonder, why is phosphorus so abundant in this ocean when our oceans don't have too much phosphorus? It's a great question, and here's how we can simplify it. It all boils down to the beautiful coupling of chemical equilibria between bicarbonate, which is one example of baking soda, calcium ions, and phosphorus. It turns out that if you have a soda ocean, like we think Enceladus does, what that tends to do is it drives down the concentration of calcium by a lot. And when that happens, phosphate minerals like apatite are much more soluble, and they naturally produce large abundances of phosphorus dissolved in the water. And if you don't believe models, you can actually go out in the field and confirm this for yourself. This is one example. It's of a soda lake. It's called Last Chance Lake in British Columbia in Canada, and it's the most phosphorus-rich body of water that's known on Earth. And people have made measurements, and you can see this is just one summary figure showing that as you have more carbonate, more soda dissolved in the water, phosphorus really shoots up. And there's where Enceladus falls on this kind of plot. So it's like a soda-rich body of water, soda ocean meeting these soda lakes. So we think, based on what Cassini showed us, that Enceladus has an extant liquid water ocean that is seemingly habitable. We found everything that life as we know it would need. The only thing that we're not quite so sure about is sulfur, and that's still work in progress. And I think we're just about out of time, but on my last slide here, this is a call to action for this community and others who might be watching online who are interested. Just to summarize, we have a body in our solar system beyond the Earth with abundant liquid water and other evidence for extant habitability. And not only that, but it's actually an accessible body of water. We can go there, we can land on the surface, we can fly through the plume, and we can sample material that came from this ocean. So it offers us a very unique opportunity in our solar system to look for evidence of life. The unfortunate thing about it is, like I said, Enceladus is our unsung hero. We don't currently have any concrete plans to get back there yet. Nothing has been funded. And this is a great opportunity for a grassroots effort to start building, to try to get to the bottom of this age-old question, is biology unique to Earth, or is it an inevitable outcome of the laws of chemistry and physics acting on matter in complex planetary environments? And with that, I think I'll be kicked off the stage. Thanks. Here's this.
Yeah, you hand it over. Jane, here's the clicky. Our next speaker is Professor Jane Graves. She is at the University of Cardiff in Wales, which is a lovely place. And she's going to talk about all sorts of interesting gases that you can see with radio telescopy and focus on Venus. And she's also a navigational artist, as am I. And so she has maybe a surprise for us. So take it away,
if
Jane.
we have time at the end. Okay, I just need the slide up the front, please. Okay, my job to do this. Got it. Finally. Okay, so we're moving on to Venus and some of my team's new observations today, and the exciting possibility, we're looking at some molecules that relate to life that is there today, microscopic sized life in the clouds. Okay, we've heard wonderful things about spacecraft. I love spacecraft. But I trained as essentially a radio astronomer. I work at wavelengths from a millimeter up to a few centimeters. So why would you want to use these? Well, I think this diagram shows very nicely. It's a theoretical calculation of the habitat size on several bodies of the solar system. And you can see there's a lot of these. And so you can't necessarily urgently send a spacecraft to each of these, as we just heard for Enceladus. So sometimes I think what motivates us is urgency. I just want the answer now, right? Like now. Also, we might have a new idea. We might think of a completely different body. We might decide there are fire-breathing dragons on Io. We want to turn a telescope on that and find your dragons, okay? And our telescopes on Earth are very adaptable. So maybe you think of a biosignature that involves something that changes very fast, or that's polarized, or that's some kind of wavelengths you never normally think about. We have telescopes to do that. I just wanted to show you some of my favorite, most beautiful telescopes. So this is the ALMA network of telescopes on a very high plateau in Chile. Let me see if I can do the pointer. To give you an idea of scale, here are some regular-sized trucks. Here's one of the two giant transporters on which they physically move the telescopes around to reconfigure for different kinds of observations. You've seen this already this morning. This is the wonderful 100-meter diameter Green Bank telescope in West Virginia, apparently one of the world's largest moving structures that humanity has ever made. And here's one of my favorites. This is the 30-meter diameter IRAM telescope in the south of Spain. And that's what we used for one of our first astrobiological projects. Okay. So this is Enceladus, but the data we got is the spectrum you're looking at there. You're going to see quite a lot of these in the talk. So what you're looking at, if you're not familiar, you're going from short wavelengths to long wavelengths as you go left to right. This kind of stuff here, this is just random noise. What you're looking for is either an emission line going up or an absorption line going down at a very, very specific wavelength. We have very high precision in that. We're talking about like, a part in a million or something. And molecules undergo quantum transitions between different states at these very precisely defined wavelengths. So we could look and say, we want to look for methanol, which is what we did. So these methanogens can not only make methane, they can also make methanol, the carbon molecule shown there. And so we found some. You can see it in the spectrum. And this is a case study of how to be careful with your astrobiology. So we looked at it and we decided there's no way this is a biosignature. Firstly, the scale of it shown by the blue cloud in the artist's impression, it's much bigger than the moon. And then we found there's more methanol in there than in relative abundance to everything else than Cassini sniffed out actually at the vents. So that doesn't work. The life forms are not outside the moon. So what we're seeing is some really weird chemistry in Saturn's plasma environment. Also, we realized Enceladus, like the man said, is really small. It's too small. So we thought we'd go to our neighbor planet next door. This was a few years later. And this was based on the 1960s idea that as the surface of Venus appears to have turned into some sort of scorching hell, owing to a runaway greenhouse effect, making it much too hot for any biological functions, that pre-existing life of a microscopic nature could have adapted to float in the high clouds instead of being on the surface. So the clouds are pretty hostile. They're very acidic. But this isn't a completely crazy idea because planet Earth has a limited aerial biosphere. It's relatively very small compared to the abundance of life elsewhere on Earth, but these micron-sized creatures do float up there. And it's an open question if it's a very active environment or they're just kind of there and a bit more dormant. But, it's a possibility. I should also stress that we don't know if conditions on early Venus were ever right for life to get started. So if we think of Earth and Venus as two similar planets made by smashing the rocks together till you've got one very hot rock, path to the Earth in the lower right went fine, but Venus must have taken some different path, and we don't know quite where it turned off. So if there were early oceans, life might have had a few hundreds of millions of years, or even a little bit longer, to get going. Could have been oceans and land masses. On the other hand, if the water was kind of never really built in or was lost very, very early, there could never have been enough water for life to develop. But it's still worth us taking a look. What my team is trying to do is what exoplanet astronomers would call a gold standard search. So finding two gases that could plausibly be biosignatures. So something that has some biological function. Okay, and you ideally don't want your biosignature gas to be made easily by something else, so not by volcanoes or sunlight changing the molecules in the atmosphere. So if you're an extraterrestrial scientist at this equivalent conference somewhere out there in the universe, you're saying methane and oxygen, these are great. I'm going to look for those on this Earth planet we've just discovered. And they would be products of living things because they disappear quickly if life stops making them. So Venus has the advantage over doing extraterrestrial studies that it's really close. It's our neighbor planet. And so we can look for gases at very, very small relative abundances. And so we can look for ones that are very distinct. As we heard, phosphine, pH3, is very distinct of life, and so in fact is ammonia, NH3. What we're looking for is a classic out of equilibrium situation. So life is an out of equilibrium process. And a redox disequilibrium is when you have molecules dominated by oxygen, such as the sulfuric acid. You see the formula there, it's mostly oxygen atoms, and we know that's there. Also there with reduced gases, which are mainly dominated by hydrogen, and that balance doesn't stay unless something is making it. So we set out to look for phosphine. We're very privileged to have used the telescope on the sacred mountain Mauna Kea on the island of Hawaii. And it's currently the East Asia Observatory operating this James Clerk Maxwell telescope that you see in the picture. Well, you actually see the shadow of it behind its protective wind blind. Okay. And we got a spectrum after about 5 hours of telescope time. And there was something there which was like the most shocking moment of my life. The white spectrum you're looking there, you can see there's a dip in the middle at the right wavelength. And that was crude, but we went, and they very kindly gave us time on the ALMA telescope network. That's actually a preliminary version, but the orange spectrum confirmed that in the same place. And so we had phosphine. Wow. So that was controversial, remains controversial, fine. I have to say now I'm like, this is routine. We look, there's phosphine again. So I'm showing you a time series of the spectra we've got over our various observing campaigns. Our really deep one is the 2022 one. The red curve is a model of the atmosphere that fits that. You can see that dip is there really nicely. And I've overlaid the red curve again on the other spectra. So you can see there's maybe a little bit of variation, but it's kind of there in all of them. Okay. Important to confirm, this is even more controversial. This spectrum was taken at a 4 times higher frequency with the Sophia Airborne Telescope, done by an independent team led by Martin Cordener. We disagree in very subtle ways on the processing of those difficult data, but you can at least process the data in a straightforward way, as I've done here, to find another of these absorption lines in the right place. Okay. Sad we don't have Sophia to try that again. And then finally, on phosphine, something I'm very proud of, we went back to the James Clerk Maxwell telescope and we managed to make use of a larger bandwidth. The significance of this is the molecules collide with each other and allow the absorption to happen at a slightly wider range of wavelengths. If they collide more, if you're at a denser, lower down, warmer part of the atmosphere, your line gets fatter. And this is what we've been able to do, and we've got this beautiful orange spectrum here. The model is fine. The model fits beautifully with no particular fancy work done. It should be nothing here. The narrow bit means high above the clouds. It should be destroyed by sunlight, and there's no line. Fine. Also, you hear, 5 sigma is a really robust standard to go for. 5 times above the noise if you are aiming to announce something exciting. When I worked out the area inside the orange spectrum, it's 50 sigma, so I'm like, okay guys, that's enough. So moving on to ammonia, so I don't take up too much of your time before coffee. The phosphine search was really my mad idea, having read some random piece of science. Ammonia was much better motivated. So in particular, my colleague at Cardiff, William Baines, in conjunction with Paul Rimmer at Cambridge University, came up with this idea that maybe the clouds don't have to be super, super acidic. If there is production of ammonia gas, it can neutralize some of that acidity. And that actually helps explain some other observations, one of which is that the droplets don't appear to be purely liquid. They might be more like a kind of slurry or sludge. But if life was making this ammonia, that could be it saving itself, essentially from corrosion. So it's kind of maintaining its own habitat. So this is the speculation in Williams' paper. And then I remembered, you can take spectra of ammonia because it absorbs strongly at a wavelength of about 1.3 centimeters. So the Green Bank Telescope people very kindly gave us time to try this. I think these are literally the first ever spectra taken at centimeter wavelengths of Venus. I couldn't find any others. So like, this is great. Okay, this is what we got. So the light blue one, we didn't really see anything. This is really difficult because it's never been done before. We got a rather scrappy spectrum in February 2022 when the telescope beam was very much on the night side of Venus, and there's not kind of anything there. But they kindly let us do it again and do a wider band in October last year, and this time the spectrum actually really does have a shape. I've done a very approximate model. There are no radio spectra. There's no code to model it. It looks like you can fit it very nicely with that red dashed line, and that looks like I drew some random squiggle, but that's not the case. That's actually a composite of approximately 10 different quantum transitions of ammonia that blend together. So I don't think it's random that the model fits the shape there. And that allows us to deduce we've got a few parts per million. This is really low abundance at these particular altitudes, and that's given to you by how wide these features are. So we're frustratingly not quite there. We're hoping to go back to Green Bank and get the instrument to go a bit wider, fatter lines. What we've got is what's sketched there. We're seeing both molecules, but just above the temperate zone. So what I'm hopeful for is that the actual source is in the temperate zone, and we're seeing a fraction of the molecules that drift upwards. So although we're finding them where it's too cold for standard liquid water, that doesn't mean that the case is hopeless for the biosignatures. I think I have a couple of slides left. We're not saying this is a sign of extant life. Like by exoplanet standards, maybe we've passed that gold standard test. You know, we have pretty good data to biosignature type molecules. But other ideas come up all the time. So for example, one of the recent ones is that these cloud sludges are broken down in some ways, and you're just getting fragments of more complex molecules, but you don't need that to be life. We really need particularly lab data before we can say how much of this stuff is there and at what height in the atmosphere is it being made? Is it being made in the nice warm clouds? We need to go back to the telescopes and do a bit more. I'm really pleased this project, Opticon RadioNet, have awarded us time just now to check out, see if we can recover an ammonia spectrum at the Sardinia Radio Telescope, which was also shown to you this morning. Okay. So, wow, now it won't change slide. There we go. Yes, that's running, amazing. Trying to do a few non-astronomer things just for variety. A very talented master's student working with me last summer, Ben Fry, has made his code available to you. He wrote a cellular automata code to see if you could have microbes thriving in droplets in a Venusian-like setup. So would they all die, or would they overfill their droplet and have no space left to move? And his simulations show very nicely. It seems they could keep going for generations under simple rules. Okay. And then finally, we had some chat about, you know, single-celled organisms, a little bit boring. Let's see, maybe they could be bigger things. So this is where your audience participation comes in. I did show you a picture at the beginning of a terrestrial airborne microbe. And we are a little thinking about what's the best kind of thing to fly? What is the best shape? So this is what you have to do. I'm going to need some people near the front to put their hands up in a moment. We have models. Okay. Based on this genuine research paper, my severe apologies to them. These are bigger and slightly more colorful. Your job, if you catch one, is to throw it behind you to another person and so on and see which is the best shape to fly to the back of the room. Please, if you're sitting near a camera or a screen, please be a little bit careful. Okay, who's got their hands up? Chris, of course you do. Whoa. I think, anyone else? I have 7 of these. This side of the room. Okay. You get the TARDIS one. I don't know what that is. There you go. Okay, we're going. Okay. If you get it to the back. Oh my God, this is actually working. If you get it to the back, please hold it up so we know the winner. Yeah, right. And also you get to keep it, so thank you very much.
Well, that was spectacular. And dear Jane has brought us right back on time so we can have the full 20-minute coffee break. Hallelujah. Be back here at 10:30. We'll start bellowing at you 5 minutes before that.
if you have some comments or anything.
Yeah, that's great.
Okay.
Yeah, what'd you do with the silly one?
The silly one here. I added that one. You think that's okay to add that?
Okay, that's perfect.
Yeah? Okay. Got me.
Suzanne, your name is Igor.
Yes, that's right. But it really doesn't matter.
Hey, you.
You can say it however you like.
Final word is in.
It wouldn't be an ambush question, or not too much of one.
But,
He's probably aware.
I mean,
Yeah. Oh, yeah, he's
yeah,
aware.
the phosphine is a really
He's a big boy.
difficult thing to interpret. Right now, what I think is more interesting is the question of what is the
All right,
sulfur
we're
chemistry.
recommencing
This is interesting
the session
proposal that
with our
aqueous
next
reaction
speaker,
destroys SO2.
Suzanne Igor, who is right here at this august university, and she's going to take us into the realm of exoplanets that kind of are Earth-like.
Kind of.
Yes. So I will wave 2 fingers at you when it's 2 minutes, and you've got 18 totally. Yeah. Thank you.
You see so many of you come to my home university to talk about such a wide yet interconnected range of topics. I'm an astronomer, and so my primary motivation for doing the work that I do is putting ourselves in context. I'm trying to progress to the next slide. There's something I should be pointing this at in particular? Sorry? I'm not good at telling jokes. There we go. No, apparently not. Oh. Well, I won. Yeah. Okay, so when you look out at the night sky, this is a picture taken by one of my postdocs at the observatory on top of La Palma of one of my graduate students whose work will actually feature later in this talk. You can see a large number of stars, and each of those is home to a planetary system. And I want you to put yourself in the position of not speculating, but knowing that many of these stars are surrounded by planets, and that a significant number of these planets are hosting life forms. This is the place we want to be. We're not there yet, but we already know that the vast majority of these stars host at least one and probably several planets, and what's more, that a significant percentage of them host planets which are sufficiently Earth-like that it makes sense to look for life around them. A significant number means anything between 2 and 50%, depending on who you ask. So it's a very broad range. And my talk is about how we're going to try and narrow that number down to a more precise value and try to tell you precisely which are the systems in our galactic neighborhood where we should be looking. So to look for exoplanets, we are reliant on observations of the star, primarily, because planets emit very little light of their own. This is a top-down view of a simulated star-planet system. It represents what we would call a hot Jupiter-type system, so the planet is around 1/10 the diameter of the star and is on a very close orbit. Now, we have to imagine that we can't see the planet at all, but as the star orbits the center of mass of the system, its motion has been greatly exaggerated here. We can measure the very tiny shift in the wavelength of the light that it emits through the Doppler effect. And we do this by taking time series of very high spectral resolution spectra. And we can use that to measure the radial velocity of the star and produce a plot that looks a little bit like this. So this is a plot of radial velocity as a function of time, and during one orbit of the planet, if the orbit is circular, you'll see a sinusoidal variation. Again, for this kind of hot Jupiter-type system, you see variations with an amplitude of several tens of meters per second. But the Earth induces in the sun a variation with a semi-amplitude of 10 centimeters per second on a year's time, okay? So that is an absolutely minute signal that we are looking for. We can also look for planets via the transit method. This is when the planet passes in front of the star. And if we monitor the brightness of the host star, then we will see a very small dip that lasts a few hours and repeats once per orbit of the planet. And again, this is actually simulating a relatively large planet around a star, a little bit smaller than the sun, so the transit is a few percent deep. For a planet like the Earth, the transit would be approximately 1 part in 10,000 of the star's light. And it would last of order 12 to 13 hours. What's more, the probability that the Earth transits, if viewed from some random location in the sky, is only 1 in 250 because it's far from its host star. So these are some of the challenges that we face. This is a representation of a schematic representation of the Sun-Earth system, seen to scale from a distance. And you can see that it would be much more challenging to detect this planet than it would the larger planet I was simulating before. But the fact of the matter is that the star doesn't really look like this. Unfortunately for us, this is what the sun actually looked like during a month in January this year. And what you're seeing is images taken every hour, and the sun is rotating. The rotation period of the sun is about 27, 28 days, depending on whether you're looking near the equator or near the pole. It varies, but you can see these large active regions. These are regions of concentrated magnetic field through the surface layers of the sun, and they cause these dark spots. We call them sunspots on the sun, star spots on other stars. And you can see I've still shown the Earth to scale up here, and you can see that some of these spots are larger than the Earth itself. So they cause variations when we monitor the light of the star, which are significantly larger than anything we can hope to detect from an Earth-like planet. So that is kind of the challenge that is at the core of what I do. And this is an example of the data set that was used to detect the first terrestrial planet to be found to transit. So the first planet which we think is made up primarily of rock. It's called Corot 7b. It was found 15 years ago now in data from a Franco-European space mission called Corot that I was involved in. In the top panel, the black curve shows the data coming from the mission. We're seeing the flux of a star observed over a period of about 5 months. The star's a bit smaller than the sun, and it has a rotation period of about 24 days. Unfortunately, I can't get the laser pointer to work, but you can see dips that repeat in a quasi-periodic fashion every 24 days or so. These are caused by large star spot groups on the surface of this star. It's much more active than our own sun, so its variability is much larger. We're talking about a few percent, whereas on the sun, it's a few tens of percent at most. But because the variations are smooth, we can filter them out and obtain the residual shown by the green curve here. The blue is the smoothed out version, and the red is just a bin version of the green curve. Now, if you run a transit search algorithm that is searching for periodic dips in that light curve, you find a very clear signal with a period of about 20 hours. This is what you get if you phase fold this signal at the detected period. And you see that we have a very clear transit with a depth of about a depth of about 4 times 1 part in 10,000. So this is a planet which is about 2 times the radius of the Earth, but with a period of around 20 hours. It's extremely hot. It's the first example of what we call a lava world. Measuring the mass of this planet was actually extremely challenging because of the activity of the host star. To measure the mass of the planet, we used the Doppler effect, as I shown you earlier, and the same star spots which cause these photometric variations also cause variations in the apparent Doppler shift of the star, because if we go back to this animation here, if I can get it to animate, there we go, then the approaching part of the stellar disk is moving towards us, the receding part is moving away from us. And so if a spot hides alternately the approaching and the receding part, it will cause an apparent signal in the radial velocity of the star. So in order to detect planets more similar to the Earth, we needed to go to space in order to reach the sensitivity, but also to be able to go out to longer periods and to find transits which last a significant amount of time. On the Earth, we're limited to transits that only last a small fraction of a night, or at least it's extremely difficult to find transits which are longer than a few hours. And so the first large-scale transit search mission after Corot was Kepler, and you've all heard of Kepler. It found thousands of exoplanets. I'm just showing this one, which is an artist's illustration of Kepler 186e, which was the first Earth-sized planet to be found in the habitable zone of its host star. The host star is a relatively small star compared to the Sun. Now, in 2015, after Kepler had completed its observation, but not after the analysis of the Kepler data was complete, that took a few more years, we had a sample of more than 1,000 transiting planets with well-determined stellar parameters. But of those, only 5 lie in what I would call a potentially habitable region, which I've defined here to be less than 1.6 Earth radii, because that's what at the time we thought was the maximum radius beyond which a planet was likely to acquire significant hydrogen and helium envelope. So this axis here shows the amount of flux the planet receives compared to the Earth. And here, this box goes from about 0.4, which was where Mars sits in our solar system, to about 2, which is where Venus sits. So we have a very small number of these stars, these planets, and they all orbit really small, faint stars, which makes it extremely difficult to follow them up in detail. So the next and current transit search mission from space is TESS, the Transiting Exoplanet Survey Satellite, which surveys the entire sky over a period of 2 years, and it scans bands of the sky for a month each. And TESS has discovered thousands of relatively small planets around stars which are also somewhat smaller than the ones that Kepler targets, but over the entire sky, enabling much more detailed characterization of these planets. But it's not sensitive to planets like the Earth because it doesn't quite have the sensitivity and it doesn't observe for long enough in general. I want to highlight a citizen science project that we're running using TESS data called Planet Hunters TESS, and where we are asking for the help of thousands of citizen scientists to examine light curves from the TESS satellite and to find this very small but significant subset of the transit events that are missed by automated pipelines. These tend to be long period events, so transits which occur only once per year or even longer than that. and which are often embedded in some significant or unusual variability of the host star, for example, young stars or evolved stars. And the latest paper from Planet Hunters is this one, where we found a transiting Neptune-sized object in the habitable zone of its host star. And actually, when we did the radio velocity follow-up, we also found a closer-in non-transiting planet that was seen only in the radio velocities. A feature of citizen science projects like Planet Hunters is that the citizen scientists who help us to discover these planets by marking the data that they see through the Zooniverse website are included as co-authors of the paper. And this is the event that they first identified here. So just to show you the kind of events that human eyes are able to identify. This event was not identified initially by the test pipelines because the test pipelines focus on events that occur multiple times within the data set that it's analyzing, which wasn't the case for this one. We since have seen repeated transits. Right, so today, thanks to both TESS, the second Kepler mission called K2, ongoing reanalysis of the Kepler data, and many ground-based projects, we now have nearly 4,000 transiting planets that are well characterized, and the number of those that are potentially habitable with the same definition has grown significantly, but they're still all around faint and small stars. And it's extremely difficult to measure their masses. In fact, there are now some very, very significant ongoing observing programs on the world's best radio velocity facilities that are aiming to confirm the masses of some of these objects, or some objects that have been found by radio velocity only that don't transit, but they each take hundreds of hours of telescope time. I'm feeling slightly ridiculous here. There we go. Okay, so this leads me to the Plato mission. So this is an artist's impression of Plato. I'm sorry if you can't see it very well, but Plato is a spacecraft on which sit 24 small aperture cameras. And so it's the European Space Agency's Cosmic Visions M3 mission. It will be launched at the end of 2026. And it does high precision, high cadence, long baseline photometry, just like Kepler and TESS, but with a precision similar to Kepler, but a field of view similar to TESS. And that allows it to find potentially Earth-like planets over a very significant part of the sky and around bright stars that are near to us. So another important feature of Plato is that it will not only find transits, but on the same stars and using the same data, it will perform what's called astroseismology, which is measuring seismic waves propagating through the interior of the stars. This allows us to probe the interior structures of the stars very precisely and to measure the masses, radii, and ages of the stars really precisely. And this is important because we only ever measure the properties of our planets relative to those of the stars. So our involvement in Oxford is to handle the stellar variability noise that I told you about in the exoplanet pipeline, and in particular to produce lots of simulated data sets on which we can test different algorithms. There's a lot of, I've not gone into technical detail here, but there's a lot of innovation going on at the moment in the different ways of treating the variability and disentangling it from planetary signals. So this slide just gives you an overview of all the different elements that go into the characterization of an exoplanet. It's a really complex process. So on the one hand, you need to detect transits. From the transits, you get a measurement of the planet radius relative to the stellar radius, and you also get a measurement of the orbital period and the inclination of the orbit. You then also, from the same data, can detect seismic oscillations in the star, and from those, initially what you get is the density profile within the star as a function of radius within the star. By comparing that to theoretical models of stellar interiors, you can convert that to an estimate of the stellar radius, the mass, and the age of the star. And I insist on the age because this is one ingredient that we've been missing from previous exoplanet characterization efforts, the age of a main sequence star, normally without astroseismology, we can usually measure with a precision of approximately 100%. It's really very imprecise. Whereas with astroseismology, we think that we can do it to a precision of about 15%. And that will be very important for understanding how planetary systems evolve. So the one missing ingredient is the planet's mass, and for that we do need radio velocity follow-up on the ground. It's probably one of the most challenging aspects of Plato, but one reason why Plato is unusual as space missions go is that the ground-based follow-up is part of the mission itself. So it's being organized, and I was very interested to hear some of the talks this morning about different kinds of alert brokers for transients, because we will face some of the same kind of problems when we're carrying out the follow-up of Plato targets, although the timescales are very different. Okay, so we know that Plato is currently being assembled in the lab. The cameras are completing their testing one by one. They're being integrated onto the spacecraft. It's on course to be launched towards the end of 2026. And a recent paper has presented some yield estimates for Plato, which I'm not quoting precise numbers because they actually depend very strongly on what you assume for the incidence of planets in different orbits and of different sizes. But essentially, based on what we know currently from the planet population, we expect to find several thousands new transiting planets around bright stars. This is planets of odd kind, but that is a very significant number compared to what we had before. So these are planetary systems which we can characterize in detail. Thank you. We also expect that a few dozen of those will be planets with radii smaller than 2 Earth radii and orbiting in the habitable zone of their host stars. And the current number of those for stars brighter than 11th magnitude is none. So this will be where this will be a sort of field-changing sample of planets. I now move to the radio velocity follow-up. I wanted to just briefly mention one of the ways in which we are bringing machine learning into the analysis of the data, particularly for measuring radio velocity masses for exoplanets. So radio velocity signals that we observe for stars are the combination of activity signals, which we don't understand very well, and planetary signals, which we do understand very well. But we have other traces, other time series we extract, which also probe the activity signals, albeit in somewhat different ways. And we've developed multi-dimensional Gaussian process models where we're essentially modeling all these time series as different combinations of latent variables which we never observe, but which are represented by a Gaussian process. And then in the case of the radio velocities, we also have the planet signal, which is what we're interested in. And this allows us to efficiently but robustly disentangle these different kinds of signal. In order to put that to good use, I mentioned at the beginning of my talk that only 1 in 250 Earth-like planet transits. And we really want to find all the Earth-like planets that are in the solar neighborhood. So we also want to perform some blind radio velocity searches. For this, we need incredibly good time sampling in order to be able to disentangle the planet signals from the stellar signals. And the survey that I'm involved in, which will do that, is called the Terra Hunting Experiment. It's got the worst acronym ever, THE. But it will sit on the Isaac Newton telescope in La Palma and monitor around 40 bright stars. We're going to put all our eggs in that basket. 40 carefully selected bright stars for 10 years, and we think that will give us enough to detect and measure the masses of any Earth-size, Earth-mass planets out to around 300-day periods that orbit those stars. So, this is my conclusions. In 10 years, when these surveys are near completion, we will have a much larger sample of well-characterized, smallish planets orbiting bright stars. a significant sample of Earth-like planets to evaluate their incidence and to know where to look for future characterization. We'll have added the age dimension to planet demographics. And we will also, I didn't mention this, but lots of different types of exoplanet observations are coming together on the same systems. Not only transit and radio velocity, but also astrometry with Gaia and increasingly direct imaging. And that will give us a much more complete view of the architectures of planetary systems. Thank you.
Thank you so much. So now we're going to come in from the exoplanets, and we're going to do a deep dive into Earth deep time and talk about complex life. This is Ross Anderson, another Oxford colleague, and I will bellow it 2 minutes.
Great, thank you very much. So just for everybody's information, I'm actually a paleontologist, so this is quite a unique crowd for me to giving a talk in. But if we take a look at our planet from space, you know, it's quite clear that our planet has life on it. The continent you see here is covered in green, and that reflects the fact that land plants are all over our planet's surface. Land plants, like animals, including ourselves, are complex life. They're not bacteria and archaea. They're members of a group called the eukaryotes, which are defined by the fact their cells have a nucleus or membrane-bounded organelles, things like the chloroplast, mitochondria. And if you think about our planet today, our planet is dominated by eukaryotes. If you look at the biosphere, eukaryotes account for most biomass, they account for most documented biodiversity, and they account for most primary productivity. They're key players in our planet today. But it hasn't always been this way. If we roll back the clock in Earth's history, over 500 million years ago, our planet was undergoing a major revolution. We were going from a planet which only had bacteria and archaea to one which had this complex life. And it's this question, when and why did eukaryotes first diversify on Earth, which occupies my mind a lot. It's what I work on. But I think it's also really important for the astrobiological community because it informs this question. In what environments might eukaryotes diversify elsewhere across the universe? So as a paleontologist, I go back in time and I look at fossils, unsurprisingly, to figure out how eukaryotes first evolved on our planet. This is the geological timescale on the top, the present is on the right, and we're going back in time through millions of years. And what you can see is I think most people in the room would think about a fossil, they'd think about a dinosaur or a trilobite or an ammonite. All those things come from the last 10% of Earth's history. But the fossil record goes back deeper. The rise of eukaryotes, we think, happened about 1 billion to 500 million years ago. This is when eukaryotes really became dominant in the biosphere. And we have fossils which can tell us about what was going on. We have single-celled eukaryotes 1.6, 1.7 billion years ago. We have examples of algae, and we even have in the Ediacarobiota across the world, including here in the UK, in Leicestershire, we have examples of the first animals. But this is a pretty broad view of things, and there are still huge outstanding questions that we don't understand about Earth's early history. We don't know the pace and the order in which eukaryotes diversified into major groups, so we don't know the time scale. We don't know when red algae or green algae or fungi first emerged. And because we don't have a robust time scale, that means we also find it really difficult to make correlations to environmental changes. We can't say whether oxygen caused the rise of eukaryotes, or whether big climatic events like Snowball Earth, which I put up here, which happened over this interval, what influence did they have on this revolution? We don't know because we don't yet have that precise, robust timescale. So what's the problem? What's the real stumbling block in this research? Well, if we think about the fossil record as most of you would recognize it, most of the things you think about are hard, they have skeletons or shells, and they're big, right? Whereas if we're going back in time, things don't have shells and skeletons, and they're all really small. And that means it's really difficult for them to be preserved. And we don't yet know the precise conditions, the precise chemical conditions in a sediment which lead to their preservation. And I think this slide here really lays the problem bare. If we go back further than 600 million years ago, there are really only 5 fossils which are preserved well enough, with enough morphological details, that we can say, yes, this is a particular group of eukaryotes. 5. So when we say we know huge amounts about early life on Earth, we don't actually, right? We're really stumbled by the amount of data that we have. So a lot of my work here in Oxford over the last few years and work in my lab has really been focused on trying to understand what are the conditions that lead to the preservation of early eukaryotes. Because if we can understand that and take a step back and do that groundwork, we're going to have a much better idea of where to go look for these fossils, and we're also going to know how the record is structured, how is it biased, where are we missing data. So today what I want to do in our talk is really talk about 2 stories. One is how we're working on the chemistry to actually refine the search image, and I'm going to talk a lot about how clay minerals might be really important to preservation. And then I'm going to talk about how we can test that search image. So can we use the search image that we've created, take it out to the field, and find new fossils? Does it work? So we'll begin with the clay-organic interactions. So if we think about where we find early fossils, the most common repository on Earth, 75% of assemblages with early fossils, regardless of what we might think they are, come from rocks between 2.5 and 500 million years old, and those rocks are mudstones. So they're rocks that used to be muddy sediment, essentially. This is a variety of fossils that you can recover from these deposits. But we know mudstones are a really common lithology on our planet. They're a really common rock type. They're across the Earth's surface. So we need to know what makes one mudstone more likely to preserve a fossil than another. It's like looking for tiny needles in a very big haystack. We need to circle in on the needles if we can. So it turns out there's actually been quite a lot of work in the paleontological research on how mudstones preserve early fossils. And a huge variety of ideas have been put forward. But what's interesting is that one factor, the mineralogy of the rock that you preserve these fossils in, comes up multiple times. So sediment composition has been suggested to be important. If your rock is rich in clays, maybe those clays change the permeability of the rock or have properties that are toxic to bacteria. And also perhaps clay minerals can actually precipitate onto your organic substrate, forming some kind of protective layer. So I became really interested in clays and mineralogy, and I started to think a little bit about this in more detail. And so what we did back in 2016 was we grew a type of bacterium, a heterotrophic bacterium that decays marine animals today in the oceans. We grew it in different sediments. And this is a chart here. On the y-axis, you've got low growth on the bottom, high growth on the top. And what you can see is that different minerals had different effects on the growth of this bacterium. And in particular, the iron-rich clay berthierine and the aluminium-rich clay kaolinite really suppressed the growth of this bacterium. And this was quite exciting because it suggested maybe if your rock was full of these iron and aluminium-rich clays, maybe you've got a chance of crashing the bacterial population and preserving your fossil. So the question was, do rocks that have these excellent fossils, do they have this mineralogy? So we went to the Cambrian, so 500 million years ago, and we looked at rocks that all had fossils. So we knew life was around and living, organisms were living and dying in those places, but we compared rocks where you only had hard tissues preserved, things like trilobites or brachiopods, to ones that had soft tissues, so you got the other soft components of those organisms preserved. And what you see here is on the y-axis, we've got the probability of finding soft tissue fossils, and on the x-axis is the percentage of the rock which is composed of your minerals. And what we found was some really stark relationships. So we found that if your rock is composed of a lot of illite, you've basically got no chance of preserving these early fossils. But interestingly, if your rock is composed of berthierine, the more berthierine you have, the better the chance you have of preserving fossils. if you've got more than 20% Berthrine in your rock, you basically guarantee that that rock is going to preserve these cool fossils. So that was really exciting because if we go back to the experiments, Berthrine was one of those minerals that actually suppressed the growth of the bacterium. So we've got a mechanistic, a potential link here where you've got a mechanism, the mineral is toxic to the bacteria that are doing decay, and that mineral is showing up in the rocks that preserve these cool fossils. We took this a bit further more recently, and we looked at more broadly microfossils across the Proterozoic and their preservation quality. So this is really looking at whether the probability of you having really nice fossils, but on a broader array of stuff, not just the most exceptional deposits. And we found actually a slightly different relationship. We found that the amount of clay in your rock was still important, but perhaps specific minerals were not. And actually we had a negative relationship with Berthrine, which was quite surprising. But I think what this suggests is that there are grades of preservation. The really exceptional stuff, that stuff where you've got all different kinds of organic matter preserved, you need the minerals of the specific type, because we need that toxicity effect of the bacteria. But if you've got organisms where you've just got cellulose cell walls, so quite resistant biopolymers, you might not only need clay of any type that just has a kind of permeability effect on the rock. So both these types of clays are going to have permeability effects, but only one is going to be toxic to the bacteria. So if we think a bit more about that exceptional kind of preservation, we can zoom in and look at where those minerals are. And this is a fossil that we've cut across with a focused ion beam, extracted a section. So we've got the fossil here in black in the center. And what you can see is directly around the fossil, you've got platy clay forming a little halo. This is your clay mineral. This is the kaolinite, a precursor of Berthrine. And it's actually binding directly and forming this halo around the fossils, protecting them. So I think this set of results is really exciting because it suggests that clays are really important to exceptional preservation, and they might help us to search systematically for these fossils for the first time, actually narrow down our search image. So for the second part of the talk, what I want to do is actually go and test this image. Can we use that clay-rich search image to find cool fossils in the Precambrian? So this is Svalbard in the Arctic, has rocks that are about 1 billion years old. They're all on their side here, so you go from the oldest rocks over there to the youngest rocks on this side. And the rocks are from this group of rocks called the Veteranen group. Now this suite of rocks is 5 kilometers thick, and it's mostly mudstones. That's a huge amount of rock to go looking for these tiny fossils. So we've got a bit of a problem, right? We need to narrow down our search image. So using our clay, what we can do is we can go look through these rocks and say how much clay is in the rock. And we get a variety of percentages. And then what we can do is we can start to work back from the highest. So we look for fossils in the highest clay abundance first and work our way back. Now we've only done this for a fraction of those samples on there so far, maybe 20% or so of those samples. So we've not got very far down into this clay abundance. And there's already cool fossils. Okay? This is probably a red algae, early seaweed. It's the oldest organism to have symmetry in the fossil record. Nothing like this has been known before. So it shows that we can recover fossils with really delicate morphologies. Morphologies that we can use to pinpoint where these things are on the tree of life. Thank you. So this is just some of the developmental data that we can get from that fossil. Actually really exciting biological results. It can tell us about how these early algae already had the developmental capacity of modern algae today, very early in their evolution. So using this search image, we can get fossils that actually tell us a huge amount about early evolution. So going forward, what is the future of this area? How can we really advance thinking about early life? So I want to return to this image. We are limited at the moment by the number of fossils we have. And it's about narrowing down that search image and knowing where to look. And I think what I hope I've shown you over the course of the last 20 minutes is that by taking a step back and thinking about that preservation, we can actually really narrow down for the first time and be systematic in our search, much more efficient. And I think it's the perfect time to be doing this kind of research. Out of Stanford recently is a new database called the Sedimentary Geochemistry and Paleoenvironments Project, very long name. But what this is basically a database of geochemical data from the early Earth. And there are tens of thousands of samples now in this database. What this means is we can go in and we can mine it and say, which of these successions that have been looked at for chemistry would be good places to go look at for fossils? You know, it's giving us the ability to go target specific time intervals. And I hope that we'll eventually get much more resolution on this diagram, be able to put the fossils in their geological context, understand which environments they evolved in, how their habitats changed through time, and that's going to be really critical for thinking about how complex life might have emerged on other planets. You know, Earth is our only, at the moment, n=1 example, so we've got to make the most of it. And I just want to finish with this. This is a picture from the Perseverance rover from Jezero Crater. And the reason why Perseverance landed in Jezero Crater is because from orbital data, we were able to show that the Jezero Crater had clay minerals. Those minerals that I've just told you are really important for preservation. So I think it can really highlight where we should go look on other planets and other planetary bodies for life in the universe. So with that, I'll say thank you very much and turn over to next speaker.
Wonderful. Thank you so much. Thank you so much. Here, Ray. So our final speaker in this session is sticking with perhaps Earth-derived thoughts, but applied to the concept of the simple-minded version of the concept of habitability zones, and how it can be enriched by the notion of a carbon cycle.
Yes, thank you very much. Welcome to Oxford. So I will be talking about just where is the habitable real estate out in our galaxy? What are the conditions under which life as we know it could conceivably emerge? Oh, good, it actually clicks. So Suzanne already introduced the term habitable zone, and actually the conventionally defined habitable zone is actually rather parochial. It's the conditions under which you could have liquid water on the surface. So by this definition, the Venus clouds are not habitable. By this definition, Enceladus is not habitable. But this is the kind of habitability we have a reasonable chance of detecting on exoplanets. The symbol went wrong. That's actually less than 400K, not up arrow 400K. So it's a good starting point. And so okay, the pointer doesn't work. But so the habitable zone is the range of orbital distances for which you could support stable liquid water on the surface of a planet. The inner edge is determined by the runaway greenhouse phenomenon. If you are getting too much absorbed radiation from your star, then water vapor will uncontrollably evaporate into the atmosphere until all of your ocean is in the atmosphere, and then it escapes to space. It generally makes a magma ocean on the surface. This is one of the things that probably happened to Venus at some point in its past. But the outer edge of the habitable zone, which is what of the conventionally defined habitable zone, which is what I'm mostly going to talk about, is determined by the condensation of carbon dioxide, which actually introduces a maximum possible greenhouse effect that you can get from carbon dioxide. Okay, there are other greenhouse gases. If I don't run out of time, I'll mention a little bit about hydrogen at the end. But this is the way the Earth has maintained its habitability. This is a system, CO2 collaborating with water vapor, that has maintained the Earth's habitability over billions of years. Now, I'm going to go through this. I'm not going to go through this in detail because time is limited, but horizontal axis, these are simple climate calculations. The horizontal axis is carbon dioxide partial pressure. That's 1 bar, 10 bars, about 20 bars there. The vertical axis is temperature, going up to 350 Kelvin down to freezing temperatures. The top panel is the one to look at. The colors on the top panel essentially represent how close you are to your star. Yellow colors, you're very close to the star. The darker colors, you're very far from the star. So that's your distance from the star. And so the point is that actually you have to have the right amount of carbon dioxide in order to actually turn a potentially habitable planet into an actually habitable planet. So if you're very close in and you happen to have 1 bar of carbon dioxide or somewhat more, 2 bars, you actually drive the temperature above 350 Kelvin, even though it is, with very low CO2 like Earth, it would be habitable. Similarly, if you're farther out in the nominal habitable zone, this is about 0.4 times the amount of irradiation the Earth is getting. Then if you had only 2 bars of CO2, that's not enough to actually keep the planet unfrozen. It would be a snowball instead. And towards the outer edge of the habitable zone, you need about 10 bars of carbon dioxide. So the conventional habitable zone just has the restriction on CO2 due to constraints from radiation and constraints from the thermodynamics. It knows nothing about geochemistry. So in fact, a current theme in thinking about exoplanet climate and habitability is that geology and geochemistry has to come together with atmospheric physics to understand habitability. We've already seen some indication of this in the talk on Enceladus, in which the generation of hydrogen through reaction with rocks is critical to understanding the chemical composition of the plumes. So the question is, geochemistry might not let you have 10 bars of CO2 towards the outer edge of the habitable zone, and in fact, I will show. I will show the indications that towards the outer edge of the habitable zone, the geochemistry, the geochemical, the deep carbon cycle actually does make problems. So this is the question I'm addressing. Does the deep carbon cycle, the geochemical processes that determine how much CO2 is in an atmosphere, does that actually allow enough CO2 to reach the maximum greenhouse limit towards the outer edge of the habitable zone? Okay, so this is what determines carbon dioxide on a planet with liquid water on the surface and a rocky crust. You have a mantle convection, which creates melt and volcanism that degasses CO2 into the atmosphere. And then you have a sink of CO2. There's a rate of outgassing, and then there's a sink of CO2, which is determined by the reaction of carbon dioxide with crustal minerals. Plate tectonics or other recycling mechanisms allow that calcium carbonate, that limestone, to be recycled back into CO2. So we have been modeling this in my group. We're using an advanced model of the CO2 sink that tracks back to work by Mayer and Chamberlain. The basic idea sketched out here for continental weathering is that when rainfall with CO2 dissolved in it, which makes carbonic acid, reacts with silicate rocks as it flows over, you dissolve the silicate, you produce divalent cations, calcium, for example, which then in the sea turns into carbonate and precipitates out. And that's the sink of carbon dioxide. But there are 2 limits. If you have lowish temperatures and very rapid flow over a surface, then the rate of the sink is determined by chemical kinetics, which has a strong temperature dependence. On the other hand, if you have if you have high temperatures with high reaction rates and sluggish flow, then you're in equilibrium. Then the chemistry comes into equilibrium, and that has very little temperature dependence. So the temperature-dependent thermostat in the sink is largely lost, except insofar as it may come in through the rate of runoff. A complication. Okay, so we sort of understand some of that continental stuff. A big stumbling block in understanding habitability and CO2 sinks is that the carbonate also forms by reaction of carbon-rich water, seawater, with silicate rocks like basalt on the seafloor. That's a carbonate vein. It's a complicated process involving flow-through fractures, reactive flow-through porous media, and we have very little ground truth for our models of how this might work. But this is a frontier area in understanding the sink. And there are many aspects of the mineralogy, what kind of rocks you have on the surface and on the seafloor, that affect the weathering sink. I'm going to put this together very shortly, but now we have to talk a little bit about the source, about the source, the volcanic source of carbon dioxide. So I've said you have to have mantle convection, that keeps things going, that produces melt and produces outgassing. That mantle convection is maintained by the decay on the Earth and probably most other rocky planets by the decay of long-lived radionuclides, like especially uranium-238 and thorium-235. Potassium-40 it has a shorter half-life, but it's very abundant, so we're still getting some of our heat from potassium-40, but that'll be mostly gone in the next billion years. And so the actual inventory of long-lived radionuclides, R-process elements like uranium and thorium, is quite important to maintaining the habitability. Otherwise, a planet will freeze out after a fairly short time. But uranium and thorium are produced in gold, for that matter, and produced in very exotic astrophysical circumstances like merging neutron stars and collapsars. You might expect differences in the rate of formation of these long-lived radionuclides depending on whether you are a spiral arm galaxy, which has frequent star formation in the arms, versus something like an elliptical galaxy where star formation proceeds in a different way. And the distance that, because of the dilution of uranium and thorium from these rare events, if you happen to be far away from that event when your giant molecular cloud forms planets, you're not going to get as much of it. And so you may wind up uninhabitable because you freeze out. Okay, now, I said I would bring this together. We put together, I'm not going to talk about the coupling to the volcanic stuff, but just the weathering thermostat, the stability of the deep carbon cycle. We put together a comprehensive model, including the full 3D dynamics and hydrological cycle of a rocky planet with the weathering model. And so this graph gives you the weathering rate in terms of the CO2 concentration. We have a little gap in our calculation here that I don't have time to talk about, but these are the low CO2 states that are rather Earth-like, that correspond to the inner edge of the habitable zone. These are the high CO2 states with CO2 surface pressure of a bar or more, corresponding to the outer edge. Now, for a good thermostat, you want for a stable deep carbon cycle, you want the weathering rate, which is the sink, to increase with concentration of CO2. Because that means that if you have an equilibrium with a certain amount of outgassing and you then have too much CO2, the weathering rate consumes extra and brings you back to equilibrium, and the other way. But what we found rather surprisingly is that for these high CO2 states, the carbon cycle actually goes unstable for reasons having to do expressly with the way precipitation distribution changes as you go to a hotter and hotter climate, which is actually related to some things that are happening as a result of global warming on Earth. The weathering rate, the CO2 sink actually decreases with carbon dioxide concentration, meaning that an equilibrium is unstable. And if you did have an equilibrium state on the right-hand side, which is the outer edge of the outer region of the habitable zone, it wouldn't stay there. It would retreat to cold states or to very, very warm states. What's more, actually, you can see that the weathering rate is small for these Earth-like low CO2 cases, but it's huge for these high CO2 states, which means that to keep a planet unfrozen, regardless of this instability, you actually need a hugely larger volcanic outgassing rate to keep the outer edge of the habitable zone actually habitable. There's no particular reason a planet farther from its star should have a higher tectonic outgassing rate. So this actually means that the actual habitable zone maintained by carbon dioxide is probably very contracted relative to what we call the nominal habitable zone. This is the cartoon of the situation. The red part this is the global weathering rate versus atmospheric CO2 partial pressure. The right-hand side is roughly the situation in the outer part of the habitable zone. In the outer part of the habitable zone, for high CO2, the weathering rate goes down with increasing CO2 so that an equilibrium on the right-hand side is unstable. It represents the division of two attractor basins. It's an attractor basin boundary. So if you actually did try to maintain a habitable state over in the right-hand side with an equilibrium amount of CO2, if you displaced it to the left, it would be attracted to a stable state, which is generally a snowball on the left-hand side. Or if you displaced it on the high CO2 side, it would be attracted to a very warm, almost a very hot, almost Venus-like state with higher CO2 than you would want for habitability. Okay, good. So I do have time to talk a little bit about hydrogen as a greenhouse gas. By the way, they converted my PDF into PowerPoints, and that's why all these symbols got messed up. Despite all of our artificial intelligence, we don't actually have an ability in here to show a PDF on the screen and actually make it work. So those of you doing AI, maybe you could save a little bit of your time for this kind of thing. But anyway, so the hydrogen is a very good greenhouse gas. An isolated hydrogen molecule doesn't have infrared lines. But when it's colliding, it acts like a more complex molecule during the collision. So at high enough pressure, hydrogen actually is a very good greenhouse gas. In fact, it's the most important greenhouse gas in the whole universe because it's so abundant. It's the main greenhouse gas that determines the vertical structure of Jupiter and Saturn, for example, which are mostly hydrogen and helium. Okay, so hydrogen is a good greenhouse gas if you have roughly a bar or more of hydrogen, partial pressure, in your atmosphere. And we've shown that hydrogen doesn't have a maximum greenhouse limit because it doesn't condense in planetary circumstances. So you can actually keep a planet habitable in the liquid water sense with very, very low sunlight. In fact, in the paper by Eric Gaidos and myself from 2011, for a sun-like star, even if you put a planet out by the orbit of Jupiter, it could still be habitable with about 10 bars of hydrogen. So that actually looks kind of encouraging. There are some problems with hydrogen maintained habitability, though. That's a misprint. That should have been 4H2. I can't blame that on the conversion, and that exclamation point should be a chemical arrow. We saw this reaction already. There's a huge amount of energy in the combination of H2 and carbon dioxide. And almost any rocky planet is going to be outgassing carbon dioxide. It's almost inevitable. And this is a metabolism that's used by methanogens on Earth. And the problem is that if your habitable planet supported by hydrogen becomes inhabited, methanogens are probably one of the most likely metabolisms to evolve there. And so it's going to turn your hydrogen atmosphere into methane, releasing a lot of energy for biology. And the problem is at these cold temperatures in the extended habitable zone, methane actually condenses. And so you convert your methanogens convert your whole atmosphere eventually into methane, which first of all is a weaker greenhouse gas and creates hazes that cool the planet. And secondly, condenses out. Convert your whole atmosphere into methane, and then everything dies. And so so the question is how can you close the ecosystem and regenerate the hydrogen? You could actually maybe keep it going through some geological source of hydrogen that regenerates things. You need an energy source to make the new hydrogen. Perhaps you could do that through something like a mineral reaction with water. But if you're trying to close the ecosystem with biology, how do you do that? And what you basically need is to regenerate hydrogen is a photosynthetic hydrogen producer, something that eats methane, uses photosynthesis to provide the energy to regenerate the hydrogen. I don't think we have any metabolisms like that on Earth, but if anybody more biologically aware than me knows of one, please do let me know, because that's just what you need in order to close the ecosystem. And the other thing, even if you leave aside the biological aspect, for carbon dioxide, we do at least know what a plausible means for CO2 to be regulated on Earth to maintain the habitability of Earth over long periods of time, and to adjust the habitability as you go for planets that are closer or farther from the star. For hydrogen, for H2, we don't have any known abiotic stabilization mechanism that sets hydrogen to be just the right value to keep the planet habitable. But that's because we've been thinking about CO2 habitability for more than 100 years. We've been thinking about hydrogen habitability for maybe 20. So finally, what are the chances of testing some of these ideas about the deep carbon cycle? And here the news is not great. What you really want in order to test these theories of the deep carbon cycle are a whole lot of planets in the nominal habitable zone that are roughly Earth-size and rocky, that have both CO2, that have some amount of CO2 and water vapor in the atmosphere. As Suzanne said, we have only a handful of even candidate planets there that are amenable to characterization, but a lot of the planets that we had hopes for, in fact, are coming back as bare rocks. They're coming back as bare rocks. Like a lot of the TRAPPIST system planets, which has several planets in the habitable zone, they don't seem to have thick atmospheres. And that's partly because these low-mass stars that Suzanne was talking about, the red dwarf stars, are very, very good at blasting away atmospheres. And so, ironically, the best cases where we have a really good atmosphere detection on rocky planets are insanely uninhabitable planets like lava planets that have a permanent dayside magma ocean, which actually outgasses various kinds of things and maintains a local atmosphere, at least on the day side. So although my group is continuing to work on these deep carbon cycle theories, I'm not very optimistic. I mean, it's too early to throw in the sponge, but I'm not very optimistic that we're going to get a good data set against which we can test these kinds of theories, not in the next 5 years, but with more advanced instrumentation, especially with the ability to detect planets around sun-like stars and characterize their atmospheres. That's the point at which we will start to have a data set where these kinds of theories can be tested. It'll be a long wait. So myself, although we're continuing on the theory because it's good to know in advance what to expect, my own hopes are pinned more on understanding the atmospheres of hot rocks instead, as well as sub-Neptunes. Thanks a lot.
Excellent. Thank you so much. That was fascinating. So we have a 15-minute break. Rest your brain cells. Come back for our last assignment, which is another opinion survey, and then the question and answer period. So. In our own solar system or in a population of exoplanets, where are we going to find life first?
Which side are you on?
Really? Ooh, I'm surprised. Ooh. You guys are really hopeful. So this puts an extra burden on NASA.
It does.
All right, we've got one left. Is your favorite alien a fabulous microbial community that uses radioactive decay as energy source? I wonder who made that up. A cute blue fuzzy alien with big eyes you could talk to and take home with you? Or someone in this room?
I think we know the correct answer to that.
I am so happy that cute blue fuzzy alien got some votes. Other than that, it's split. So. Zog the alien. All right, fantastic. Well, thanks everybody for playing along. So I'm not going to redo those for you. I'm going to ask you other questions that I think that I want to know. And I'm running the panel, so I picked the ones I like. So this is one that I've thought about a lot. I'm sure you guys have too. Pete has thought about it a lot. We've discussed it. And that is, do we need to have at least a framework definition of lifelike processes? What is life in some sense? Or can we employ anomaly detection? Like we heard about this morning, to search for weird patterns or objects that stand out and might be life. Let's go down the row. Chris, what do you think?
Ooh, okay. I think I favor anomaly detection because I think that the first approach presupposes that we know a lot more than we really do know.
Yeah.
And so I think my preferred approach for exploration would be to send very capable missions or make very detailed measurements. And then we try to understand what we see in terms of abiotic framework. So maybe focus a lot of effort on understanding what an abiotic system would look like. And then we test the abiotic possibility, and if that doesn't work, then we start scratching our heads more and entertain if life could explain it.
Thank you. Bethany, you're on. Did you hear the question, or should I repeat it?
I sure did. Okay. That's a great question.
Go for it, babe.
All right. Yeah, I mean, I think I mostly agree with Chris that anomaly detection is a great way to go. I think that realistically, it's probably going to work out that we should have some sort of like a priori models on board that we start with, and then we have these anomaly detection models on board that we can also start with. The challenge is that in many cases, I would surmise that we are not going to know what that system looks like until we get there. And so, I think that this is the power of having an a priori model that can then be updated on the fly. So, like, this is the kind of thing that we're working on right now, is that you want to start with an assumption just to get something, or you could start with nothing, in fact, and just completely build your model as you're collecting data during that mission. And then this way, because I think one of the things that we were challenging ourselves with is like, you're going to start out a mission and maybe everything looks like an anomaly because it's not what you expected. And then probably over time, you're going to start to see the similar kinds of processes and maybe chemistry. So all of these things can become characteristic. And that's when, so I would say, don't be the boy who cried wolf. Like, start learning about your environment while you're out there, and then start employing anomaly detection later.
So environment first, and then build your theories about life from what you're trying to populate. Interesting. What do you think, Ray?
Exactly.
What's your...
Oh, me. I am. Well, I'm going to finesse the whole question because I think worrying too much about just what life is and what kind of unconventional environments life could emerge in, just getting way ahead of ourselves, because I would be just, we don't even know whether any rocky M-star planets, which would be the most common kind of star in the universe, we don't know whether any of those can retain atmospheres. And that's partly because we actually don't understand the physics of loss of high molecular weight species very, very well, but just the observations are indicating, they're not very hopeful so far in terms of that, in terms of having atmospheres. And so I myself, I'm putting my eggs in trying to understand roughly habitable environments.
Yeah.
Although that does, when you say a roughly habitable environment, that does beg some question about what kind of life could survive that. But.
I remember, I forget the author's name, but there's a great paper out there that's titled Why I Stopped Worrying About the Definition of Life and Why You Should Too. I forget the author, but it's a very catchy title. You're coming at it, you know, Rob, from a very different position. You're coming at it from the earthly stance. What do you think?
I quite like Chris's approach, thinking about, you know, what are the physical processes that could create this thing, whatever it is we're measuring. Are there physical explanations for that? If not, we can defer to biology. The only issue is our own experience of that, looking at fossils on the early Earth, is actually quite tricky. The fossils I showed on the screen were all complex organisms where there's positive evidence that that is life. You know, we can recognize those morphologies, see it as some kind of organism. When you get older than that, into the Archean record, where the kinds of fossils that are preserved are very simple, there's lots of arguments back and forth about whether those things are life or not. And the principal arguments people use are this kind of negative approach, which is, you know, is there any physical way to explain this? But I wouldn't say for any of those we're certain either way. You know, even the best Archean fossils, we still. I think there is a reason. You know, there's a reason to have positive evidence.
And you, exoplanet lady, you know, the kind of data that we're going to get from exoplanets is so different.
Well, the kind of data we're going to get from exoplanets in the short term is very limited.
Yeah.
And, you know, I just gave a whole talk about looking for Earth-like planets because that's a good place to start, that we understand. I wouldn't say we understand well, but we understand better than many other kinds of environment. And so in that sense, I'm not somebody who spends my time worrying very much about what the definition of life is. I think as a physicist, it's very interesting to think about where life sits in the sort of panoply of different phenomena, from a thermodynamic sense even. I mean, you know, is life a completely ubiquitous property of any system that's complex enough? Is it, you know, its way of fulfilling the signal of thermodynamics and producing entropy? But that is it's a question that's very disjointed, I think, from how should we plan our next space mission.
Mm-hmm. Jane, what do you think?
I think some kind of framework for our search is useful. So if physics had told us microbes can't float in the air, it would have been, you know, a waste of time to look for them. But from what I'm hearing today, I'm really attracted to the idea of using AI to search for anomalies. In a lot of astronomy, we have overwhelming amounts of data, sometimes sitting in archives that nobody will ever look at. And so techniques that could say, here's a thing that's not a normal thing. I love doing that kind of stuff, going like, what the hell is this? I think we would find a lot.
So you're saying we have, you know, a whole lot of data that is moribund that we might exhume and begin to feed into this AI process.
Yeah, so even data storage is a problem for some of our branches of science, I think. You know, something, you know, maybe a spectrum of something in the solar system taken 40 years ago could be what we're looking for. Need to dig it out and take a look.
So one of the things that I've written about and I think is really important but really hard to do is that there is no silver bullet because we have no silver description. And so it means that in order to demonstrate that we're really looking at a lifelike process, whatever that means, and we haven't defined it, that we need significantly more than just a couple of lines of evidence. And in our space missions so far, because of the limits of our funding, imagination, technology, and way to get things funded, and the fact that we're really still in the baby step era, we don't have a lot of the lines of evidence that we will ultimately need. And that brings up the problem of simultaneity of measurement or time span over which a lifelike process might evidence itself, because we are trapped in, you know, a very limited spatial and temporal scale ourselves, and that colors what we do and what we think. And we escape that a bit by modeling and microscopy and science fiction. But, you know, how do we plan to add lines of evidence that we can actually correlate to make sense out of it, rather than, oh, we go on this mission and we grab this set of data, and then we go on another mission, and then we grab a data set from Earth. Yeah, you're nodding, Ray. You want to take a first crack at it?
Oh, yeah, well, actually, yes. I think the Enceladus is a good way to concentrate mind on that. So I absolutely agree. It would be great to go back to Enceladus. But if you did have the mission of your dreams, what would you actually look for in Enceladus to say that there actually was life there?
Great question. I think I would focus on very general questions because it may take more than one mission. Like you're mentioning our lack of a silver bullet. So we're hopeful that we could strike gold in our first attempt, but it may require multiple missions. And if we try to be too specific, we run the risk of not getting data that would have extra value. So rather than look for a DNA molecule, it might be more useful to first try to understand, let's say, what's the origin of organic materials on Enceladus. And so that would then include life, but it would also open the door to these abiotic possibilities we've been discussing too. And there's a whole range of those.
And we certainly need to know those, right, in order to vet the potential biosignature.
Actually, an idea just occurred to me. What if there are amino acids can be abiotic, but if there are amino acids in the plumes and they all have the same chirality, would you think that was a pretty good indicator?
That could probably at least be a bronze bullet.
Yeah.
Bethany, how do you think your AI approach could help us with this? Conflating and correlating multiple different types of data, because we have lots of different, radically different kinds of data.
That's true. Yeah, I think part of the approach is actually, I would challenge all of us to rethink how we set up mission operations, and specifically science data collection. So a lot of the time, these instruments might be separately proposed. So that, let's say, a flagship mission, for instance, you might have really no collaboration from the get-go. And I think that I would challenge all of us to try to work with each other more, even in the formulation phase of a lot of these ideas, than not only just the mission concept, but the instruments themselves and how they could collaborate. The other thing I would also challenge us for is to be creative, kind of as you said, Penny. Maybe we need to challenge ourselves to think creatively about the assets that we have in the outer solar system. Because I think ultimately we were going to fly things, especially if we're talking about current solar system missions, we're going to fly something that is low risk. And I think that we're going to have to adopt a higher level of risk to then adapt a mission to those conditions. So yes, you can send something out there, but I think that mission, basically the software has to be adaptable so that you could say, well, we've been out here for a little while. Let's try something new. Let's try a new experiment that maybe we didn't consider before. And so that doesn't require a huge level of intelligence. It requires that the system itself is adaptable. So, and then on top of that, you know, if we're still praying for Mars, I know some people really are, then I think that's the kind of thing where could we like adapt the assets we already have to a new kind of mission, so that would be an extensible mission. And I think that these are really creative challenges, and I think ones that are a great idea. Also, how can we collaborate, you know, between agencies? So could we have effectively a new mission between assets that are NASA focused and ones that are from ESA or JAXA or so on? So I think that could be another tool in the toolbox there.
So it's sort of like an international, multinational campaign, you know, to elucidate sort of one line of, you know, investigation would be interesting. Yeah.
Yeah, sorry to jump in.
Yeah, no, go ahead.
A thought came to mind. I mean, one thing that might seem not so directed towards the search for life, but this is also an AI-focused conference, is could we send a mission maybe that's not going to look for life right away, but would be used to train AI to some environment that we go to, like the surface of Europa or something, and that training experience would then be valuable for the follow-up mission that looks for the evidence for life.
Yeah, that would be an interesting approach.
Absolutely.
Yeah. I want to think about the different approaches you two ladies, you know, talked about. The exoplanet connection to what we're learning about our own planets within the solar system is kind of our great hope for trying to look for biosignatures when we have so much less data. And how much presupposition do you think we can avoid? So for example, Jane, you're talking about, you know, using radio astronomy to look for potential biosignature gases. At some level, that's tied to an earthly perspective, but maybe less so than some things, because we're really looking at disequilibrium in terms of redox conditions.
Yeah.
And residence time requiring rapid production of something. Yeah.
I think we can probably do it in a fairly agnostic way, because if we did really comprehensive surveys of spectra of bodies with atmospheres or vents, we could just look for stuff you're like, that molecule has no business being there, even if it was, I don't know, argon hydride, that's not even a molecule.
Right.
I think we could take quite an agnostic approach. You know, if we're doing stuff that's solar system related, we can do analog experiments on a lab bench and so on. We can see how, you know, maybe it's super easy to make some molecule, you know, by bubbling something through rocks or something, which we hadn't just done that experiment before, you know, to do stuff dear to my own heart. Most of the phosphine data doesn't exist because phosphine's really toxic to larger organisms like us, so nobody wants it in their lab. So we haven't persuaded too many people to go out there and risk themselves because I need to know a number today, you know. But yeah, I think we can be pretty agnostic, hopefully. It's hard to get enough telescope time to do some massive spectral survey, but if people got behind it, it'd be really cool.
Well, that's hopeful. That's hopeful. I was going to ask you, Suzanne, if somebody said, Suzanne, dear, we have this giant pot of money, and your primary goal is to look for biosignatures, and you were willing to do that, what would you do?
I think I'd do one of the big space missions that are currently under study, both at ESA and NISA and NASA. So I would do something that is capable of taking spectra of terrestrial planets in the habitable zone of nearby stars, including sun-like stars, because I wouldn't want to put all my eggs in the M-dwarf basket. But and I would. So at the moment, the big question is what is the best way to do that? And whether we should focus on thermal emission in the infrared or reflected light, invisible, and what are the best technologies to achieve that? But it's very clear that we need a large space mission to have the spatial resolving power and the sensitivity that's necessary. And so I think to some extent, actually, the community is doing that. There's a huge effort involving thousands of scientists that are working towards the Habitable World Observatory on in the States, but not just. And on the European side, ESA is investigating this mission called LIFE, the Large Interferometer for Exoplanets, which works in the mid-infrared. And so I think, you know, the answer to that question is there's a fair bit of consensus in the community about what we should be doing right now. The other thing is that these missions, both their efficiency and the number of systems they're able to observe, and therefore the, you know, how far out from the sun they can go, and the chance, because we still don't know how common life that affects its atmosphere in a detectable way is. So, and that affects how many systems we need to survey in order to find it. So, having already identified the best targets is a very important thing that we should be doing now. So I'd divert some resources towards that, but that is exactly what I was talking about today. So I think it is being done.
Big missions.
I think big missions, there's no going, I'm not convinced, I haven't come across, I would love to come across a, you know, small mission concept that could shortcut for a very specific type of star or a very specific type of planet. There are projects involving sunshades that you can fly in sync with existing telescopes, including JWST. And those are also very interesting. I just don't know enough about them to talk about them personally, cogently.
Let me finish with one question before we turn it over to the audience for you, Ross. And, you know, knowing what you know, your profound grasp of the challenges of identifying ancient life at the microbial level here on Earth, how much of a shot do you think we have on Mars?
I think of finding a fossil probably quite low.
Yeah.
These things are very rare, and you know, to have landed the rover in exactly the right place, to have found it, and to, you know, in the few tens of samples we're collecting, to put one of those pencils through a layer of rock that has a fossil, I think it's quite low. However, you know, you go to the geological record throughout Earth's history, and organic molecules are preserved quite commonly. And so we may find a chemical signature. I think there's a much higher probability of finding a chemical signature than there is of finding a fossil. The other thing to note about Mars is the essential lack of tectonics means that early history of the planet is very well preserved, unlike it is on our planet. You know, we go back to these old rocks on our planet, and they're beat up. They've been subjected to high temperatures and pressures. They've huge diagenesis to the minerals. That's unlikely, to be the case on Mars. And so there's a real opportunity there to look at a planet which has a really well-preserved early history, which our planet does not have.
Even if the life didn't last all that long. Let me now turn it over to the audience. Let's see.
Everywhere.
Let's go. Okay. All right. These are awkward. Okay, you take that one. Pete, go for it.
I'm glad you didn't throw it.
No, I wouldn't do that.
I have a general question, kind of following up some of the discussions in the presentations. You know, one of the things, and I know that Jane, you talked a little bit about it, was the alternative chemistries, and that, and of course the answer we had in the question, it seems a lot of people want to say from first principles, and just the general topic of discussion is, why don't we look more for alternative solvents, hydrocarbons, sulfuric acid, others, and alternative chemistries, because as we know, most of our solar system isn't in the habitable zone as we define it. So just a general, how would we do that? What is the chemistry, how do we make sure that there's a life possibility?
Yeah, good question. Who wants to take it? Yeah, go for it, Jane.
Yeah, so to some extent you can calculate, how much reactions would take place in other solvents. There has been some work done on this. So my colleague Janusz Petkowski has a paper out, in fact, about sulfuric acid. And some of this is surprising, like some of the organics you'd think would just, give up and die when they see it are actually quite robust. So the basic energy calculations, I think, can be done for different bodies, both hot and cold, yeah.
Cool. Anybody? Yeah, you want
Yeah,
to
so I was just on a Viva, very interesting thesis Viva at Cambridge on Jordan, where he was looking at sulfur metabolisms that are not quite like what we have on Earth, but which could potentially work on Venus. And the nice thing about this is even though there wasn't a particular organism in mind, by extracting from the metabolism, he could turn that into predictions about this SO2 abundance. And so throwing out different chemistries, different metabolisms, and then understanding them well enough to tease out observable implications is the sweet spot, I think.
Mm-hmm.
And we can do that for things that are not too far from Earth chemistry. If you want to talk about silicon-based life or something like that, I don't know to what extent we can anticipate
What about
those.
applying it to different temperature regimes?
Yeah, well,
planets with wildly different temperature regimes.
yeah, so I mean, I work on lava planets. We have magma oceans, and what kind of fish could live in magma oceans? There's lots of energy. Or on the cold side, there's been a lot of speculation about life in hydrocarbon lakes on Titan.
Right.
Even to the point where people started thinking about how do you make a cell membrane that doesn't dissolve in a hydrocarbon lake, and so there are interesting things to think about there. We actually, some colleagues of mine and I pitched an idea to NASA astrobiology, don't just follow the water, but it didn't fly. So.
There's a lot of sentiment to stop with the water thing, move on. Water's good. We kind of identified it in a lot of places. We got it nailed. Time to move on. Oh, yeah, Beth. Speak.
That's okay. I was waiting. I'd like to jump on that metabolism train because I think metabolism is probably a great way to think about it. Obviously, if we see evidence of metabolism, you're going to want a lot of other lines of evidence. But if we think about one of the principles of what is life is it's something that transforms chemicals into energy or something into something else. So, a lot of the work that I actually do, which I didn't talk about, is looking at the byproducts of life. I particularly think about stable isotopes and how life actually fractionates those isotopes. But I think that, if we want to try to think about systems that are not necessarily Earth, like we can consider the common metabolic pathways and what effects those have, but also what are the kinds of chemical reactions that could happen on a different planet or moon or system, asteroid, whatever, and then what are the kinds of alterations would you see that could result from something making a form, a body, a whatever, a biomass
structure
out of that material. So I think that that's the way that you could approach it.
Next question.
Is this working? Yeah. So I really enjoyed this discussion about how to identify a biosignature. Of course, the anomaly detection and doing it by trial and error works when you have free data flowing around and you have all the time. But in a realistic scenario where you have to build a mission, you have to convince the taxpayer that you'll have to put $10 billion into it and you want to search for life, that's not a viable strategy, right? So you want to give the public a very clear goal or a testable hypothesis, as is done in various areas of physics and other sciences, a clear narrative on this is what we're after, this is the experiment we want to build, and we'll test it, right? We don't seem to have that in planetary atmospheres, especially exoplanetary atmospheres. So my questions to the panel is, how do you navigate that situation when you want $10 billion, yet you're not prepared to say what exactly do you want to look for? And second, do you actually have an answer for what to look for in the best case scenario?
Interesting. I mean, that sort of gets into grantsmanship versus what you really want to do, right? Yeah, go ahead, Suzanne.
Well, I think, thinking specifically in the context of these big space missions I alluded to before, we do have a clear sort of, you have the null hypothesis and you have the hypothesis 1, and I think those are, the hypothesis 1 is relatively well defined. We're looking for, probably oxygen or ozone in combination with methane and perhaps CO2. And that is something that is not necessarily entirely foolproof, as I'm sure you've been part of many debates discussing this, and it's also not the only way to look. But I think that is the best first hypothesis that we want to test. And the neat thing about it is that in order to test our hypothesis, we need to collect significant numbers of spectra for habitable planets in the sense of planets with temperatures likely to sustain liquid water on their surface. And that is going to give us much better information on the kinds of environments that exist and is going to allow us to very much refine our set of hypotheses that we then want to test. In parallel with that, of course, we need to be doing a huge amount of work on cataloging the different kinds of chemical pathways and understanding the interplay between these pathways and the conditions in the atmospheres. But I think that, that there's the simple story that you tell to US Congress, and then there is the, if you like, the more open-minded survey view of these missions, which is actually provides you with an almost guaranteed science return, if you see what I mean.
I like Suzanne's answer a lot.
Okay.
I
We
think,
vote for your answer.
Yeah, because you want to have this excess or general capability, so you can take this practical perspective to address hypotheses that are important for moving the field forward. But then if you have that excess or general capability, then you open up the discovery space. And a great example of this is a story told to me by my old boss. He was the PI of the Cassini mission that detected hydrogen, but we also analyzed Titan. And Titan's atmosphere has lots of organic compounds. And he was telling me that when they were first designing the mass spectrometer, this is the instrument that measures all these molecules, he was telling me that they wanted to cut off the mass range at around like 40 mass units because all the models that were available at the time suggested like the most complex organics you'd find in Titan's atmosphere would be like C2 or C3 compounds. And then we actually went there, and true, we were able to measure the C2 and C3 compounds, so we satisfied that goal, but then we also discovered molecules that were hundreds or thousands times larger.
So make no small plans, is what you're saying.
Yes.
Yeah, please. I don't think we can hear you very well yet.
Can you hear me now?
Yes, we got it.
I think Chris touched on this a little bit, but tying it back to Strand 1 from Alexis, talk about using AI to identify geographic landscapes and how they change over time. Is this something that we could we do something similar for the surfaces of other planets and moons, like cryovolcanoes on Enceladus, and like with the existing telescopes like JWST and Vera-Rubin, do we have the resolution for that, or will the images have the resolution needed to apply AI, or if not, what would we need?
Maybe I can answer for the exoplanet component of the question. So
yeah.
Even with the wildest and most ambitious proposals to try and not only, so when I talk about direct imaging of an exoplanet, I mean the planet is in one pixel and we're just getting the light from that one pixel and possibly getting a spectrum from it. And actually, spatially resolving a distant exoplanet is beyond anything that we have current concepts for. We can use time to resolve the structures on an exoplanet. People have done this for the Earth, looking at reflected light from the Earth, trying to see if we could infer the structure of continents and oceans. And we can do it at if you're thinking in terms of circle harmonics, you can do it at the level of, we know there's 2 big continent masses and 2 big oceans on Earth, provided that we know roughly how long a day is. If we don't know how long a day is, we are actually not even able to do that.
We've known that our planet has been habitable for 4 billion years. Do we know what the Earth would look like as a single pixel 3 billion years ago, 2 billion years ago?
Oh yeah, actually, Lisa Kaltenegger has a paper laying out model atmospheres corresponding to different time slices. And of course, one of the challenges in looking for biosignatures is that oxygen often comes to mind. For the first 2.5 billion years of Earth history, there was essentially no oxygen in the atmosphere. We know that very precisely about Earth. And maybe oxygenic photosynthesis is a very rare event, given how long it took on Earth. And so finding anoxic biosignatures is a lot trickier.
Yeah.
Thought about it, but Lisa did have this paper. If the anoxic early Earth, more methane, less CO2, and it's something to look for.
Yeah, I think, oh, Bethany, did you have a comment?
Yeah.
Go for
it. I was just going to address the Enceladus part of that question. And I think that one of the things that I would ask is what do you need AI for? So the quick answer is yes, we could absolutely develop, and actually people already have, there's an undergraduate who actually developed a convolutional neural network that looks at the surface of Enceladus and identifies features. I think she just got it published. So it's these are things that we can do. It just depends on what you're looking for. So I think that I would certainly not jump to, can I machine learning my project? But I think that there are really great things, like if you wanted to look, as the person who asked the question suggested, cryovolcanism. So if you wanted to specifically look for some change in the surface of that, the challenge is that we don't have a lot of pictures over a long enough time. So I think I'm really excited to see what happens with Europa Clipper, and we get these really great images, and I'd love to see them processed really quickly so that we could potentially see things like this in real time.
Cool.
One more back here.
Yeah, one last question from the audience.
Hi, I was wondering, is the probability of life more rare over space or time? And if the answer is time, do you think that should restrict how far away we're looking?
Did you guys catch that?
I
didn't quite hear it.
The question was about whether the...
Is the probability of life more rare, in space or in time throughout the universe?
Oh, space or time.
So I think we would love to know the answer to that. I'm not sure we do, but
have any ideas?
Both, maybe.
It's true that on Earth, life has existed for most of the lifetime of the Earth, but life that we could detect from afar, I think is essentially the way we think about it coincident with the Great Oxygenation Event. So that restricts it to a much narrower range. It's also unclear how long in the future we have ahead of us, partly because our star will one day evolve into a red giant, partly because we are, maturing technologically probably faster than we are socially, and so there are challenges associated with that. So I think it's a very important question to ask what is the lifetime of life on a given planet, and in its different forms. But whether that's rare, whether that's a stronger constraint than where in space to look at. I guess an interesting point we can take your question to is to ask, what kind of stellar populations should we be looking for life around? Is it better to go around young stars? Is it better to go around metal-rich stars or metal-poor stars? There's some really interesting points about the fact that the abundance of radioactive elements in the core of a planet controls how long it can sustain plate tectonics for, because it's the radioactivity that drives that. And that might be related to how close you happen to be to a relatively recent supernova when the planet and the stars fall. So there's all sorts of really interesting questions we can ask, but I don't think we have any answers.
Yeah, we're not smart enough to answer that. In fact, I don't know if we ever will be, because we live in a heck of a big galaxy, you know, and we're itty and bitty. Yeah, Ray.
Yeah, so the sort of things Ross was talking about on how long it took for complex life to evolve on Earth, I think is one of the essential astrobiology questions. And it relates to this question of intermittent, of life in being rare in time in some planets. That for the Earth, well, we don't know why it took 2 billion years to get to complex life even after oxygen on Earth. Was that unusual? Is that unusually long, or is that unusually short? But the fact is that on Earth it was really a squeaker, because in only another 500 million years or so, because of the continuing brightening of the sun, we undergo a runaway greenhouse and turn into Venus, and maybe less than 500 million years. And so we just barely made it. If it took another 500 million years to get to complex life, we wouldn't be having this meeting. And then if you have a slightly higher mass star, you have even less time. Than that. But so that's why I think the complexification time scale is a critical thing that we need to understand better in order to understand just how prevalent complex life might be out there in the universe.
The other thing to think about is that these evolutionary events that led to things that could be a biosignature, the evolution of photosynthesis, or the evolution of eukaryotes, or the evolution of animals or land plants, things that fundamentally changed how the planet worked as a system, and may have changed its chemistry. You know, those are events that seemingly happened once. In each case, you know, if you think about animals, we have a single animal common ancestor, or land plants have a single common ancestor. They may have evolved multiple times at that time, but that lineage outcompeted other things that were around at that time. So I think, you know, there is a inherent randomness to that, in a sense. I mean, we don't fully understand why those things happened when they happened.
Yeah, it may partly depend on the stochastic nature of the planet's geological behavior itself.
Yeah, I'll mention, I'd like to emphasize, go even further back, and the origin of life is the real kicker for me. How probable is that on a so-called Earth-like planet? It seems like from the history of life on Earth that life is very tenacious. It's gone through several mass extinctions, but the origin of life is the mystery, because we just have the sample of one, right? And that's why I think it's important that whether you buy my sales pitch for Enceladus or some other sales pitch, I think we can all agree that it's important to search to get some clues to that question. The way I like to think about it is how Darwin was inspired for the theory of evolution. He wasn't just sitting in his garden in England, right, coming up with this idea, but he's out there actually exploring, getting new types of information, and I think that's where some of the value can come from, exploring our solar system and the exoplanets.
Yeah, so that argues for a little bit less constrained exploration than the tightly well-formed formulae with hypotheses where we pretend to know that we already know stuff, but that's kind of at odds with the way we get things funded. Let me ask everybody one more question, which is what we asked on the board. You get to pick and just take a couple of seconds. Are we going to likely find extraterrestrial life sooner, better, faster here in our own solar system, or in the population of exoplanets? Jane?
I'm really optimistic for solar system first. I'd love in about 20 years we've found some convincing biomarkers or things on perhaps Mars and Venus and Titan and Europa and Enceladus. And I think there's young people in the room today who are going to be doing that science. And maybe it'll be like 20 years, we'll have some really cool results. And if we had multiple, not necessarily all certain, because they're not all going to be certain, but if we had multiple solid indications of life, either extant or in the past, I think that would be something that's maybe easier to do in a shorter timescale. For example, Habitable Worlds Observatory, which I still want to have, please.
So what's your take on it, Susan? So my take on it is going to be the exoplanets, partly because I have to say this, it's kind of job description, but also because I think we're going to survey hundreds.
Yeah.
Right? And,
Numbers
you know, so even if it is relatively rare, the specific type of biosignature we're looking for, we will find it if it's there in that 100-plus sample. And and in terms of the race, I love the fact that we have a race. I mean, who would have thought, even 10 years ago or 15 years ago, that we'd be in that position, that there's a very good chance that in the next 25 years, we'll find it one way or another. So, yeah, you know, it's like betting on the football. I don't really care who wins so long as somebody wins. That's a good
I just want somebody to win, right? Yeah, what do you think, Ross?
I think if it's life living now, I think your approach, Suzanne, is the best one. If it's life in the past, we might find that first in the solar system.
Yeah. Very different approaches to figure that out, though, right? Different data, different missions. Yeah, Ray?
I think it's slightly more likely that we will find indications of life through biosignatures on exoplanets precisely because of the larger numbers, and also eventually the larger numbers of truly Earth-like conditions. But it's going to be much harder convincing people that it's truly a biosignature.
Because you can't hold it in your
Because
hand,
there's always the question, is there some unanticipated abiotic source of methane or something? If we do detect it in the solar system at any point, whether it's first or afterwards, the follow-up and making it really convincing will be much easier because you can go there and put it under a microscope and actually see it.
Good point. So exoplanets might happen sooner, but maybe not as convincing.
Yeah.
Yeah. Chris?
I like Ray's answer. I'm going to call it a wash for that reason, just to be annoying, because, yeah, we'll have huge statistics from exoplanets, so that's definitely an advantage on that side of things. But then on the other counter-argument for the solar system would be just the depth of information that we'll have will vastly exceed what we have for any given exoplanet. And ultimately, it's going to depend on what nature gives us, and can't make that prediction. I think the best we can try to do is go take a look.
Cool.
I could actually amend just quickly that biosignatures, I think, will always be hard to make really convincing. But technosignatures, this was echoing what was said, technosignatures can be made very convincing.
I'm waiting for Klingons.
Yeah, but even in terms of technosignature gases, you know, I'm much more confident that, say, sulfur hexafluoride has no geological source of any significance. Yeah. So.
Bethany, you get the last word.
Well, I will say that I'm hopeful for in our solar system, just like James. I think that would be, I'm really hopeful for Enceladus, Europa, and lava tubes on Mars.
Yep, cool. Well, thanks everybody. Thanks for your wonderful talks. Thanks for your thoughts. Thanks to the audience for your attention and your questions. And we'll be back doing it again tomorrow morning. So rest your brain cells. Thanks. This gentleman would like to get a picture of everybody.
Come on.